Reinforcement Learning _ an Introduction. Richard S. Sutton. Sutton and Bardo's Reinforcement Learning. An Introduction, 2nd edition, 2018, is a canonical textbook of the field, a learner's account of learning from interaction, built from the agent's perspective rather than from the mathematics alone. Across 3 parts and 17 chapters, the book develops a single thesis: that goal-directed learning from trial and error, grounded in the evaluation of actions rather than their instruction, can be formalized, bounded, and scaled from the simplest tabular estimates to function approximation, policy gradient, and brain scale mechanisms. This examination follows that arc in the author's own pedagogical register. Problem first, definition-driven, proof-disciplined, and quietly celebratory of the idea that temporal difference error is the field's central computational novelty. It covers the K-armed bandit, Markov decision processes and dynamic programming, Monte Carlo and temporal difference learning, in-step bootstrapping, planning and DINA, function approximation, and the deadly triad, eligibility traces, policy gradient methods, and the closing applications and frontiers that connect the framework to psychology, neuroscience, and the engineering of intelligent agents. Abstract. Reinforcement Learning. An Introduction, 2nd edition, 2018, is the field's canonical textbook, and this deep examination follows it in its own register. Problem first, definition-driven, proof-disciplined, and quietly insistent that the central and novel idea of the field is temporal difference learning. The examination spans 3 parts. Part 1 builds the tabular foundations: the K-armed bandit and exploration, Markov decision processes and the reward hypothesis, dynamic programming and generalized policy iteration, Monte Carlo methods, one-step and in-step temporal difference learning, and planning with DINA. Part 2 carries the same ideas into function approximation, semi-gradient prediction, on-policy control, the off-policy instability of the deadly triad, eligibility traces, and policy gradient methods, where the book's disclaimers become as instructive as its theorems. Part 3 crosses into psychology, TD models of classical conditioning, the goal gradient, neuroscience, dopamine as a broadcast TD error, applications TD gammon, Samuel's checkers, Watson's wagering, memory control scheduling, DQN on Atari, AlphaGo and AlphaGo Zero, Adobe LTV, thermal soaring, and the frontiers, general value functions, options, learn state, reward design, and the future of AI. The examination preserves the book's signature honesty about what is established, what is empirical, and what remains open. Executive Summary. Sutton and Bardo's Reinforcement Learning. An Introduction is the book that taught a field how to think about learning from interaction. Its governing problem is deceptively simple. How can an agent that is never told what to do, but only evaluated after the fact by a scalar reward, discover behavior that maximizes that reward over the long run? Its answer is assembled over 17 chapters and 3 parts with unusual patience and an equally unusual candor. The core commitments are the reward hypothesis, that any goal can be formalized as the maximization of expected cumulative reward, and the inductive claim that value estimation is arguably the most important thing that has been learned about reinforcement learning over the last 6 decades. From these grow the book's architecture: tabular methods first, where exact solutions are possible; function approximation second, where exactness must be traded; and the deeper scientific stakes third, where the algorithms meet the conditioning laboratory, the dopamine neuron, and the engineering of systems that play games against world champions. The book is deliberately an introduction, not an encyclopedia, and it repeatedly says so. The authors apologize for having to leave out all but a handful of the field's contributions, and they insist that applications still require as much art as science. The intellectual arc is best seen as the progressive relaxation of one assumption at a time. Chapter 1 poses the third paradigm distinction between evaluative and instructive feedback. Chapter 2 isolates exploration in the bandit. Chapter 3 formalizes delayed reward as an MDP. Chapters 4 through 8 solve the tabular problem exactly, and then integrate planning and learning in DINA. Part 2 asks what happens when the table is too large. Function approximation forces the VE objective, the semi-gradient compromise, the deadly triad and its off-policy instability, and the discovery that even the depth of bootstrapping is a dial, and lambda, rather than a fixed choice. Part 3 then shows the same machinery redescribing animal learning, neural reward processing, and the achievements of TD-gammon, DQN, and AlphaGo 0. Throughout, the books register, plain, incremental, occasionally wry, always honest about open questions, is the voice of the field's founders teaching their own subject from inside. The significance is double. Pedagogically, the book remains the single clearest entry point to reinforcement learning because it presents one coherent framework rather than a catalog. Scientifically, it supplied the computational hypothesis, the reward prediction error, that connects its own algorithms to a half-century of conditioning experiments and to the firing of dopamine neurons. And it drew the lineage from Samuel's checkers to programs that learn from no human data or guidance beyond the basic rules of the game. Its limits are equally instructive. The authors concede the off-policy theory is less satisfying than the on-policy. The online learning challenge for deep networks is one of the most pressing areas for future research, and the problem of making a reinforcement learning agent's goal, attuned to our own, remains open. For students, researchers, and engineers who want to understand where the field's ideas came from and where they're going, this book, and a deep reading of it, remains the recommended path. Central thesis. The book's governing idea is that learning what to do from evaluative feedback, trial and error search combined with delayed reward, is a single, formally tractable problem, and that its solution rests on estimating values, not just rewards. The conceptual spine is generalized policy iteration, a value function and a policy in mutual pursuit, with a value function driven toward consistency with the policy and the policy driven toward greediness with respect to the values. Every method in the book, dynamic programming, Monte Carlo, temporal difference, in-step, eligibility traces, function approximation, policy gradients, is an instantiation of or a qualification to that loop. The book's deepest methodological claim is that the field's central and novel contribution is temporal difference learning, which combines Monte Carlo's model-free sampling with DP's bootstrapping and thereby solves the credit assignment problem online, incrementally, and at a spectral range of bootstrapping depths. And its deepest scientific claim is that the same TD error is what the brain broadcasts as dopamine. Foundational observations. The reward hypothesis is load-bearing, not decorative. The framework's power comes from a single audacious reduction. Any goal can be coded as maximizing cumulative scalar reward. This converts vague aspirations into an engineering signal, but it also concentrates all of the designer's values into one place, the reward signal, which is why Chapter 17's warnings about specification gaming, the monkey's paw grants what you ask for, not what you should have asked for, follow naturally from the book's own premises. Value estimation, not reward maximization directly, is the field's core practical lesson. The book insists rewards are in a sense primary, whereas values are secondary, yet action choices are made based on value judgments. We seek actions that bring about states of highest value, not highest reward, because values already fold in future consequences. This is why nearly every algorithm in the book is a value estimation method, and why the one-step greedy with optimal values result is the beauty of the asterisk operator. Bootstrapping depth is a dial, not a binary. The book's most reusable technical insight is that Monte Carlo and one-step TD are the extremes of a continuous spectrum. In-step returns, then the lambda-weighted average, then eligibility traces as a cheap mechanical implementation. The recurring empirical lesson, an intermediate level of bootstrapping performed best, with lambda chosen to move toward Monte Carlo methods, but not all the way there, holds in the tabular case, under state aggregation, on function approximation, and even on the mountain car and Atari scale tasks. Function approximation transforms the problem structure, not merely its scale, with far more states than weights. Making one state's estimate more accurate invariably means making others less accurate, so the field must choose a distribution over states, the VE objective, accept the semi-gradient compromise, and confront the deadly triad, the off-policy version of which shows that even in simpler prediction, complete instability can arise, and whose treatment the authors concede to be less satisfying than the on-policy theory. The book's honesty about open questions is part of its method. Formal convergence of Monte Carlo ES has not yet been formally proved. Off-policy learning deals effectively with the first part of the challenge, but not at all with the second part. Deep learning struggles to learn rapidly in the incremental, online settings that are most natural for the book's algorithms. These admissions, always precise, never hand-waving, distinguish the foundational from the hoped-for and train the reader to do the same. The same algorithm family explains animals, neurons, and world champions. The TD model of classical conditioning predicts blocking, the Egger-Miller effect, temporal primacy overriding blocking, and higher-order conditioning. The reward prediction error hypothesis maps delta onto dopamine, and the lineage from Samuel's checkers through TD-gammon and DQN to AlphaGo 0 shows the same value-based, bootstrapping machinery scaling to superhuman play, a coherence across disciplines that is the book's broadest significance. Significance and recommendation. Reinforcement learning. An introduction is recommended to any reader who wants to understand, rather than merely apply, modern machine intelligence. It remains the clearest and most honest first book on the subject, and its depth rewards rereading. What looks like pedagogy on the first pass is often open research on the second. Students should read it as the field's canonical route. Chapters 1 to 8 for the tabular core, 9 to 13 for approximation, 14 to 17 for the human and engineered frontiers. Researchers will find the theory chapters, especially 11 to 13, the most honest treatment of the field's unsettled questions, and engineers will find the case studies 16 and the design cautions 17, essential context. The book is not, and does not claim to be, a cookbook or a state-of-the-art survey. It is the foundation, and the acknowledgement of what a foundation cannot yet support. Preface and notation. The prefaces. The prefaces to the second edition and to the first edition stand side by side in this book because they frame two projects at once, a field and a personal intellectual partnership. The first edition, published in 1998, grew out of a project instigated by A. Harry Klopp for the Air Force Office of Scientific Research in the late 1970s and dedicated both to his memory and to the collaboration he caused. The authors were brought together by his conviction that the brain, and any genuine intelligence, is built around systems that seek to maximize something rather than systems that seek equilibrium. That maximization insight is the quiet founding idea of the whole book. Reinforcement learning differs from homeostatic and error-correcting approaches and from supervised pattern classification because it is organized around an agent that drives toward reward. The second edition, begun in 2012, was written because 20 years of progress, much of it propelled by the very methods this book teaches, had made the 1998 text outdated. Its stated goal repeats the first edition's almost verbatim, to provide a clear and simple account of the key ideas and algorithms of reinforcement learning that is accessible to readers in all the related disciplines. The authors are explicit that this is an introduction, not an encyclopedia. They apologize for leaving out all but a handful of the field's many contributions, and they retain a deliberate focus on core, online learning algorithms. This is a point of intellectual identity as much as of scope. The book is organized around inexpensive, model-free methods that the authors believe scale well to large applications, and it never abandons that predilection even when it surveys planning, model-based, and brain-inspired alternatives. The prose registers are telling. The first edition preface sets the pedagogical contract. We chose not to produce a rigorous formal treatment of reinforcement learning, declining the highest possible level of mathematical abstraction and the theorem, proof format, and instead choosing a level of mathematical detail that points the mathematically inclined in the right directions without distracting from the simplicity and potential generality of the underlying ideas. The second edition preface adds a practical teaching apparatus, 1 and 2 semester course suggestions, starred sections, and exercises for advanced or optional material. And the statement that Chapter 6 is the most important for the subject and for the rest of the book. Both prefaces are careful to place credit. The authors thank the many colleagues whose results became examples, acknowledge the institutional support of a Foster and NSF, and attribute the entire enterprise to Klopp's original conviction. Summary of notation. Following the prefaces, the summary of notation is itself a compact argument about what the book believes matters. The notation separates random variables, written in capitals, from their instantiations, written in lowercase. The state, action, and reward at step T are S sub T, a sub T, and R sub T, while their possible values are S, A, and R. Value functions are written lowercase, V sub pi, Q sub pi, because they are functions, while tabular estimates get capital letters, V sub TS, Q sub TSA. Approximate value functions, being deterministic functions of random parameters, return to lowercase, as in hat of VSW with weight vector W sub T and feature vector X sub T in bold. This single convention already encodes the book's narrative arc. The field moves from tabular estimates to parametric function approximation, and the notation must be able to express both without confusion. 20 product pages of symbols follow. The probability P of S are given SA of transition and reward together, which the second edition adopts to capture the full stochastic dynamics of rewards rather than only their expectations. The returns G sub T, the N, step, and lambda returns. The TD error partial sub T that the authors call central and novel. The policy, the action value and state value functions, discount, and step size parameters, and the later vocabulary of weights, features, projectors, and Bellman operators that function approximation requires. Capital versus lowercase. The distinction between random variables S sub T, a sub T, R sub T, and their values S, A, R resolve some common points of confusion the authors found in teaching. Underlying true values like V sub pi stay lowercase, while their tabular estimates V sub T are capitals, and approximate functions hat of VSW return to lowercase as functions of random parameters. Joint transition probability P of S are given SA. The second edition adopts joint probability for next state and reward in place of the first edition's separate P to the A and R to the subscript notation, because the book's methods increasingly need the full reward dynamics, not just expectations. Notation as argument. The glossary's trajectory, banded estimates, then MDP values, then weights W sub T, features X sub T, eligibility traces Z sub T, and Bellman operators, quietly foreshadows the three-part structure of the book, from tabular learning through approximation to deeper theory. Quote, "Our goal for the second edition was the same as our goal for the first, to provide a clear and simple account of the key ideas and algorithms of reinforcement learning that is accessible to readers in all the related disciplines." Preface to the second edition. Quote, "He noted that systems that try to maximize something, whatever that might be, are qualitatively different from equilibrium-seeking systems, and he argued that maximizing systems hold the key to understanding important aspects of natural intelligence and for building artificial intelligences." Preface to the second edition. Chapter 1, Introduction. Reinforcement Learning as a Third Paradigm. The book opens with the claim that governs everything that follows. Learning is, first of all, learning by interacting. The idea that we learn by interacting with our environment is probably the first to occur to us when we think about the nature of learning. An infant has no explicit teacher. It has a sensory-motor connection to its environment, and exercising that connection yields information about cause and effect and about what to do to achieve goals. From driving a car to holding conversation, we are acutely aware of how our environment responds to what we do, and we seek to influence what happens through our behavior. The authors adopt the perspective of the artificial intelligence researcher or engineer, not directly theorizing about how people or animals learn, but exploring idealized learning situations and evaluating the effectiveness of methods through mathematical analysis or computational experiments. The definition is given early and stays canonical. Reinforcement learning is learning what to do, how to map situations to actions, so as to maximize a numerical reward signal. The learner is not told which actions to take, but instead must discover which actions yield the most reward by trying them. Two characteristics distinguish it from all other learning: trial and error search and delayed reward. The name has a triple life: a problem, a class of solution methods, and a field that studies them, which the authors insist must be kept conceptually separate. The problem itself is formalized as the optimal control of incompletely known Markov decision processes, capturing just three aspects of the real learning problem in their simplest, untrivialized forms: sensation, action, and goal. This opening chapter situates reinforcement learning against its two neighbors. Supervised learning is learning from a training set of labeled examples provided by a knowledgeable external supervisor, and the object is to extrapolate or generalize responses to situations not in the training set. But it is alone not adequate for learning from interaction, where it is often impractical to obtain examples of desired behavior that are both correct and representative of all the situations in which the agent has to act. In uncharted territory, an agent must be able to learn from its own experience. Unsupervised learning is typically about finding structure hidden in collections of unlabeled data, but reinforcement learning is trying to maximize a reward signal instead of trying to find hidden structure. The two well-known headings would seem to exhaustively classify machine learning paradigms, but they do not. The authors therefore designate reinforcement learning a third paradigm. This placement is more than taxonomy. It is the book's founding polemic against teaching machines only from examples, and it returns in the history section as a caution that many researchers and even textbooks minimize or blur the distinction. Elements, limitations, and scope. Four sub-elements define a reinforcement learning system: a policy, a reward signal, a value function, and, optionally, a model of the environment. The policy defines the learning agent's way of behaving at a given time, a mapping from perceived states of the environment to actions, corresponding to what psychology would call stimulus response rules. It is the core of a reinforcement learning agent in the sense that it alone is sufficient to determine behavior. The reward signal defines the goal of a reinforcement learning problem. On each time step, the environment sends a single number, and the agent's sole objective is to maximize the total reward it receives over the long run. Rewards are the immediate and defining features of the problem faced by the agent. In a biological system, analogous to the experiences of pleasure or pain. The value function is where the book makes its deepest early commitment. While the reward signal indicates what is good in an immediate sense, a value function specifies what is good in the long run. Values indicate the long-term desirability of states after taking into account the states that are likely to follow and the rewards available in those states. The authors draw the human analogy sharply. Rewards are somewhat like pleasure and pain, while values correspond to a more refined and far-sighted judgment. Rewards are primary, values secondary. Without rewards, there could be no values, and the only purpose of estimating values is to achieve more reward. Yet action choices are made on value judgments, seeking actions that bring about states of highest value, not highest reward, because these actions obtain the greatest amount of reward for us over the long run. Because rewards are given directly by the environment, but values must be estimated and re-estimated from the sequences of observations an agent makes over its entire lifetime. The central problem is value estimation, and the authors state flatly that the central role of value estimation is arguably the most important thing that has been learned about reinforcement learning over the last 6 decades. The fourth element, the model, mimics the behavior of the environment, or more generally, allows inferences to be made about how the environment will behave, and is used for planning, any way of deciding on a course of action by considering possible future situations before they are actually experienced. Methods that use models are model-based. The simpler model-free methods are explicitly trial-and-error learners, viewed as almost the opposite of planning. The book's scope on state is deliberate, The authors treat the state's signal as given, produced by some pre-processing system that is nominally part of the agent's environment, and focus entirely on deciding what action to take as a function of whatever state signal is available, not on designing the state signal. They take this not because we consider state representation to be unimportant, but in order to focus fully on the decision-making issues. Scope also draws the line against evolutionary methods, genetic algorithms, genetic programming, simulated annealing, which apply multiple static policies and never estimate value functions. Such methods never learn during an individual lifetime and ignore much of the useful structure of the reinforcement learning problem. They do not use the fact that the policy is a function from states to actions, and they do not notice which states are similar. Their place is real but narrow. Small policy spaces, games where the agent cannot sense the complete state, or searches where good policies are common or easy to find. An extended example, tic-tac-toe. The example that carries the chapter is a tic-tac-toe player built only from the rules of the game and a value function learned by self-interaction. The program keeps a numerical value for each of the 2,000 board positions it can encounter, interpreting a win, loss, draw, or stalemate as reward or punishment of the final transition. During play, it takes a greedy step in the value of positions, but with a small probability, takes exploratory moves. After each move, it backed up the value of the new position into the value of the previous position, so that values migrate backward along winning lines. After a few hundred games of self-play, the values of early positions come to predict the probability of winning, and the greedy policy derived from them plays near perfectly. The example is chosen to display the framework's reach and limits at once. It is model-free with respect to its opponent. It never forms a model of the opponent at all. Showing model-free means not needing to think about how the environment will respond to a single action. It generalizes poorly on its own, but the same idea scales. Tesoro's T-Gammon combined essentially the algorithm described above with an artificial neural network to learn backgammon, whose roughly 10 to the 20th states make it impossible ever to experience more than a small fraction of them, and learn to play far better than any previous program and eventually better than the world's best human players. The lesson is that how well a reinforcement learning system can work in problems with such large state sets is intimately tied to how appropriately it can generalize from past experience, which is in this role that we have the greatest need for supervised learning methods within reinforcement learning. The chapter's exercises probe the same pressures: learning from exploratory moves, symmetry exploitation, greedy versus exploratory play, teaching by guided puzzlement rather than by assertion. Early history of reinforcement learning. The history is told as the convergence of two long, independent threads, trial and error learning and optimal control, around a third, less distinct thread, temporal difference methods. The optimal control thread is the older and less experiential. The term came into use in the late 1950s, and Bellman extended a 19th century theory of Hamilton and Jacobi to derive the Bellman equation, the functional equation defining a value function or optimal return function over a dynamical system state. The class of methods that solve this equation became dynamic programming, and Bellman also introduced the discrete stochastic version of the problem, the Markov decision process, while Howard devised policy iteration. DP suffers from what Bellman called the curse of dimensionality, meaning that its computational requirements grow exponentially with the number of state variables, yet remains far more efficient and more widely applicable than any other general method. The connection to learning was slow in coming, delayed by the view of DP as an offline computation, dependent on accurate system models and analytic solutions to the Bellman equation, and proceeding backward in time, hard to reconcile with learning that must proceed in a forward direction. The trial and error thread is the one the authors know best and tell in most detail. It runs back to Thorndike's law of effect, quoted in full, of several responses made to the same situation. Those which are accompanied or closely followed by satisfaction to the animal will be more firmly connected with the situation, while responses followed by discomfort have their connections weakened. The term reinforcement entered the animal learning context later, in the 1927 translation of Pavlov, and a stimulus counts as a reinforcer only if the strengthening or weakening persists after the reinforcer is withdrawn. The thread runs through early electromechanical learning machines. Ross's maze-finding device, Gray-Walter's mechanical tortoise, Shannon's maze-running mouse Theseus, and Minsky's snarks, stochastic neural analog reinforcement calculators meant to resemble modifiable synaptic connections in the brain. The authors note the recurring confusion that followed. Early neural network pioneers clearly motivated by reinforcement learning. They used the language of rewards and punishments, but the systems they studied were supervised learning systems, a blurring some textbooks still perpetrate. The third thread, temporal difference learning, is smaller and less distinct, but has played a particularly important role in the field, in part because temporal difference methods seem to be new and unique to reinforcement learning. Its origins lie in secondary reinforcers in animal psychology. Samuel Checker's program was the first to implement temporal difference ideas. Klopf brought trial and error together with temporally successive predictions and generalized reinforcement, and linked it to the massive empirical database of animal learning psychology. Sutton and Bartow developed learning rules, driven by changes in temporally successive predictions, and built a psychological model of classical conditioning. Witten's 1977 paper is identified as the earliest publication of a temporal difference learning rule. The convergence came in 1989 when Chris Watkins's development of Q-learning extended and integrated prior work in all three threads, and Tesseros T.D. Gammon brought the field broad attention in 1992. The chapter closes by folding optimal control back into the definition. We must consider the solution methods of optimal control, such as dynamic programming, also to be reinforcement learning methods, because the theories and solution methods for the cases of complete and incomplete knowledge are so closely related that we feel they must be considered together as part of the same subject matter. Quote, "Reinforcement learning is learning what to do, how to map situations to actions, so as to maximize a numerical reward signal. The learner is not told which actions to take, but instead must discover which actions yield the most reward by trying them. In the most interesting and challenging cases, actions may affect not only the immediate reward, but also the next situation and, through that, all subsequent rewards. These two characteristics, trial and error search and delayed reward, are the two most important distinguishing features of reinforcement learning." Section 1.1. Quote, "Whereas the reward signal indicates what is good in an immediate sense, a value function specifies what is good in the long run. Rewards are in a sense primary, whereas values, as predictions of rewards, are secondary. Without rewards, there could be no values, and the only purpose of estimating values is to achieve more reward." Section 1.3. Quote, "The central role of value estimation is arguably the most important thing that has been learned about reinforcement learning over the last 6 decades. Section 1.3. Tabular Solution Methods. Chapter 2. Multi-armed bandits. A K-armed bandit problem. The chapter isolates the single feature that most distinguishes reinforcement learning from other kinds of learning: evaluative feedback. Purely evaluative feedback indicates how good the action taken was, but not whether it was the best or the worst action possible, whereas purely instructive feedback indicates the correct action to take independently of the action actually taken, the basis of supervised learning. Because evaluative feedback depends entirely on the action taken, it creates the need for active exploration, for an explicit search for good behavior. The authors study this evaluative aspect in its simplest setting, one that does not involve learning to act in more than one situation, the non-associative case, and the specific problem is the K-armed bandit, named by analogy to a slot machine or one-armed bandit, except that it has K levers instead of one. The problem is stated directly. You are faced repeatedly with a choice among K different options or actions, each yielding a numerical reward chosen from a stationary probability distribution that depends on the action you selected, and your objective is to maximize the expected total reward over some time period. Each action has a value, Q times A, the expected reward given that it is selected, You do not know these values with certainty, but maintain estimates Q sub TA. The deepest structural point emerges from what you would do with perfect knowledge. If you knew the value of each action, then it would be trivial. You would always select the action with highest value, and what you must do without it. Selecting a greedy action, one of those with greatest estimated value, is exploiting. Selecting a non-greedy action is exploring because it improves your estimate. Exploitation is the right thing to do to maximize the expected reward on the one step, but exploration may produce the greater total reward in the long run. Since it is not possible both to explore and to exploit with any single action selection, you face the exploration-exploitation dilemma. The authors are candid about their theoretical modesty here, and it is a signature of the book's register. In this book, we do not worry about balancing exploration and exploitation in a sophisticated way. We worry only about balancing them at all. Many sophisticated methods make strong assumptions about stationarity and prior knowledge that are either violated or impossible to verify in real applications. The guarantees of optimality or bounded loss for these methods are of little comfort when the assumptions of their theory do not apply. The path forward is therefore a small set of simple methods that are robust rather than optimal. Action value methods and the 10-arm test bed. The natural estimate is the sample average, the mean of rewards actually received by an action. As the denominator goes to infinity by the law of large numbers, Q sub T A converges to Q times A. The simplest use of these estimates is greedy selection. A sub T equals argmax A Q sub T A, which always exploits current knowledge to maximize immediate reward and spends no time at all sampling apparently inferior actions. The simple corrective, epsilon greedy selection, behaves greedily most of the time, but every once in a while, say with small probability epsilon, selects randomly among all actions with equal probability. In the limit, every action will be sampled an infinite number of times, thus ensuring that all the Q sub T A converge, and the probability of selecting the optimal action converges to greater than 1 minus epsilon. But these are just asymptotic guarantees and say little about the practical effectiveness of the methods. To compare methods empirically, the book constructs its canonical benchmark, the 10-arm test bed, 2,000 randomly generated bandit problems, each with 10 true action values drawn from a normal distribution with mean 0 and variance 1, and rewards drawn from a unit variance normal centered on the chosen action. On this test bed, greediness tells a cautionary tale. Greedy improved slightly faster than the other methods at the very beginning, but then leveled off at a lower level, achieving reward of only about 1, compared with the best possible of about 1.54, because it often got stuck performing suboptimal actions, finding the optimal action in only about a third of tasks. The epsilon greedy methods explored continuously and eventually did better. Epsilon equals 0.1 found the optimum earlier, but never selected that action more than 91% of the time, while epsilon equals 0.01 improved more slowly, but eventually would perform better. The advantage of epsilon greedy depends on the task. With noisier rewards, it widens, and even in the deterministic case, exploration is needed if the task is non-stationary, as we shall see in the next few chapters. Incremental implementation and non-stationarity. Sample averaging, done straightforwardly, would require retaining all past rewards. The book derives the incremental form that will recur throughout. The update Q sub n plus 1 equals Q sub n plus 1 over n, or sub n minus Q sub n, requires memory only for Q underscore n and n, and is immediately generalized to the book's master template. Pseudo. New estimate, old estimate plus step size, target minus old estimate. The expression target minus old estimate is an error in the estimate, reduced by taking a step toward the target, where the target may be noisy. This single shape, estimate moved a step toward a target, scaled by a step size parameter, is the verb of nearly every algorithm in the book. The step size sequence carries real content. With alpha sub NA equals 1 over NU, recover the sample average, guaranteed to converge by the law of large numbers. The classic stochastic approximation conditions, the sum over n alpha sub equals infinity, and the sum over n alpha sub n a to the second is less than infinity. Guarantee convergence with probability 1. The first condition is required to guarantee that the steps are large enough to eventually overcome any initial conditions, and the second guarantees that eventually the steps become small enough to assure convergence. A constant step size alpha in 0, 1 violates the second condition, so the estimates never completely converge but continue to vary in response to the most recently received rewards, which is actually desirable in a non-stationary environment, and problems that are effectively non-stationary are the most common in reinforcement learning. The authors note the inversion with characteristic dryness. Although sequences of step size parameters that meet these convergence conditions are often used in theoretical work, they're seldom used in applications and empirical research. The constant step size produces an exponential recency-weighted average, in which the weight on an old reward decays geometrically, exactly the behavior a learner needs when the world drifts. Optimistic initial values. Initial estimates are a source of bias, but the bias can be turned into an exploration mechanism. In the language of statistics, all methods considered are biased by their initial estimates. For sample averages, the bias disappears once an action is tried, while for constant alpha, the bias is permanent, though decreasing over time. The authors note the practical double edge. The initial values become, in effect, a set of parameters that must be picked by the user, yet they provide an easy way to supply some prior knowledge about what level of rewards can be expected. The trick of optimistic initial values exploits this bias deliberately. In the 10-arm test bed, setting all initial estimates to +5, wildly optimistic given true values near 0, encourages action value methods to explore. Whichever action is selected, the reward is less than the starting estimates, so the learner switches to other actions, being disappointed with the rewards it is receiving. The result is that the system does a fair amount of exploration even if greedy actions are selected all the time, and a purely greedy method with optimistic initialization eventually outperforms a realistic epsilon greedy method on the stationary test bed. But the authors immediately limit the trick. It is far from being a generally useful approach, unsuited to non-stationary problems because its drive for exploration is inherently temporary. The remark that follows is among the book's most quoted. The beginning of time occurs only once, and thus we should not focus on it too much. Upper confidence bound action selection. Exploration should be directed, not indiscriminate. Epsilon greedy forces the non-greedy actions to be tried, but indiscriminately, with no preference for those that are nearly greedy or particularly uncertain. The upper confidence-bound idea selects among actions according to their potential for actually being optimal, choosing a sub t equals argmax a q sub t a plus c the square root of the natural log t over n sub t a, where the square root term is a measure of the uncertainty or variance in the estimate of a's value, and c sets the confidence level. The mechanism is precise and worth reading in the author's own words. Each time it is selected, the uncertainty is presumably reduced in sub t a increments, and, as it appears in the denominator, the uncertainty term decreases. On the other hand, each time an action other than is selected, t increases, but n sub t a does not. Because t appears in the numerator, the uncertainty estimate increases. The use of a natural logarithm means that the increases get smaller over time, but are unbounded. All actions will eventually be selected, but actions with lower value estimates, or that have already been selected frequently, will be selected with decreasing frequency over time. On the test bed, UCB often performs well, and in the chapter's parameter study, it emerges as the overall best on this problem. But it is more difficult than epsilon greedy to extend beyond bandits to larger state spaces and non-stationarity, where it is usually not practical. Gradient bandit algorithms. A different strategy. Learn action preferences rather than action values. Instead of estimating q times a, the gradient bandit algorithm maintains a numerical preference h sub t a for each action. with no interpretation in terms of reward. Only relative preference matters. If we add 1,000 to all the action preferences, there is no effect on the action probabilities, which are determined by softmax, Gibbs, or Boltzmann distribution over the preferences. The natural learning rule is stochastic gradient ascent on expected reward, updating the chosen action's preference up when the reward exceeds a baseline bar of RT and down when it falls below, with non-selected actions moving in the opposite direction. The chapter proves in a shaded box that this algorithm is an instance of stochastic gradient ascent. The expected update equals the gradient of expected reward with respect to preferences. The proof is typical of the book's stance. It needs only beginning calculus, and it establishes robust convergence properties without implying practical optimality. A subtle, widely missed point follows. We did not require any properties of the reward baseline other than that it does not depend on the selected action. The baseline does not affect the expected update, but does affect the variance of the update and thus the rate of convergence. Choosing it as the average of rewards is simple and works well in practice, and omitting it measurably degrades performance on the testbed, because without a baseline, the algorithm cannot soak up a uniform shift in all rewards. Associative search. Contextual bandits. The chapter ends by taking a step closer to the full reinforcement learning problem. So far, the tasks are non-associative. No need to associate actions with situations. In an associative search task or contextual bandit, several bandit tasks are faced in turn, and a distinctive clue signals which one is at hand. The learner must learn a policy associating each task, signaled by the color you see, with the best action to take. Associative search is intermediate between the K-armed bandit problem and the full reinforcement learning problem. Like the full problem, it involves learning a policy, but each action affects only the immediate reward. The chapter's last sentence hands the baton to the next. If actions are allowed to affect the next situation as well as the reward, then we have the full reinforcement learning problem. The summary is characteristically honest about what the chapter achieved and did not. The simple methods presented can fairly be considered the state of the art for the bandit problem. The Gittins index and Bayesian approaches are more sophisticated but require complete knowledge of the prior distribution and are impractical for the full problem. Yet they are far from a fully satisfactory solution to the problem of balancing exploration and exploitation. The parameter study's inverted U-curves teach a meta-lesson about method assessment. We should attend not just to how well it does at its best parameter setting, but also to how sensitive it is to its parameter value. On the bandit problem at least, UCB performs best, and the simple methods will serve as components starting in Chapter 5. Quote, "The most important feature distinguishing reinforcement learning from other types of learning is that it uses training information that evaluates the actions taken rather than instructs by giving correct actions. This is what creates the need for active exploration, for an explicit search for good behavior." Section 2.1. Quote, "If you knew the value of each action, then it would be trivial to solve the K-armed bandit problem. You would always select the action with highest value. Exploitation is the right thing to do to maximize the expected reward on the one step, but exploration may produce the greater total reward in the long run." Section Chapter 2, verse 1 to 2.2. Quote, "The beginning of time occurs only once, and thus we should not focus on it too much." Section 2.6. Chapter 3, Finite Markov Decision Processes. The Agent-Environment Interface. The chapter introduces the formal problem the book will try to solve for the rest of its length: finite Markov decision processes. MDPs involve evaluative feedback, as in bandits, but also an associative aspect, choosing different actions in different situations, and, decisively, delayed reward. Actions influence not just immediate rewards, but also subsequent situations or states, and through those future rewards. Where the bandit estimated one value per action, the MDP requires values that are state-dependent quantities essential to accurately assigning credit for long-term consequences to individual action selections. MDPs are a mathematically idealized form of the reinforcement learning problem for which precise theoretical statements can be made, and the authors are explicit about the trade they accept. As in all of artificial intelligence, there is a tension between breadth of applicability and mathematical tractability. The interface is drawn with deliberate generality. The learner is the agent. The thing it interacts with, comprising everything outside the agent, is the environment. At each discrete time step, the agent receives a representation of the environment state S sub t, selects an action A sub t, and one time step later receives a numerical reward R sub t plus 1 and finds itself in a new state S sub t plus 1, giving trajectories S sub 0, A sub 0, R sub 1, S sub 1, A sub 1, R sub 2 dots. C. In a finite MDP, the sets of states, actions, and rewards all have finitely many elements, and the joint probability P of S are given SA equals PR S sub T equals S. R sub T equals R S sub T. 1 equals S A sub T. 1 equals A. Completely characterizes the environment's dynamics. The extraordinary reach of the framework is stressed by example. Time steps need not refer to fixed intervals of real time. Actions can be any decisions we want to learn how to make, from voltages on a robot arm to whether to have lunch or go to graduate school. And states can be low-level sensations, symbolic descriptions, memories, or even mental states like not being sure where an object is. Two conceptual boundaries deserve attention. First, the physical boundary of the body is not the agent, environment boundary. The boundary is typically drawn closer to the agent than that, so that motors, muscles, and sensory organs are part of the environment. The general rule: anything that cannot be changed arbitrarily by the agent is considered to be outside of it and thus part of its environment. Since the reward computation defines the task, it too must be beyond its ability to change arbitrarily. Yet the agent may know everything about its environment and still face a hard task, just as we may know exactly how a puzzle like Rubik's Cube works, but still be unable to solve it. The agent environment boundary represents the limit of the agent's absolute control, not of its knowledge. Second, the Markov property is best viewed as a restriction not on the decision process, but on the state. The state must include all aspects of the past agent environment interaction that make a difference for the future. The book assumes this property throughout, though Part 2 considers approximations that do not rely on it. Goals and rewards. The goal of an agent is formalized by the reward signal. The chapter's most quoted idea is its statement of the reward hypothesis. At each time step, the reward is a simple number, and the agent's goal is to maximize cumulative reward in the long run. The authors give this the status of a hypothesis, that all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal, called reward. They add that the use of a reward signal to formalize the idea of a goal is one of the most distinctive features of reinforcement learning, and they defend its flexibility with a string of examples. Reward proportional to forward motion for learning to walk, -1 per time step before escape to make a robot flee a maze quickly, +1 per collected, +1 for winning chess, -1 for losing, 0 for draws. The practical discipline follows from the hypothesis. The reward signal is your way of communicating to the agent what you want achieved, not how you want it achieved. It is not the place to impart to the agent prior knowledge about how to achieve what we want it to do. The authors sharpen this with the chess warning. Reward a chess agent only for actually winning, not for achieving sub-goals such as taking its opponent's pieces or gaining control of the center of the board. Because if achieving these sorts of sub-goals were rewarded, then the agent might find a way to achieve them without achieving the real goal. Returns and episodes. The return is the formal object the agent maximizes, and its definition must handle two kinds of tasks. In episodic tasks, the interaction breaks naturally into subsequences, which we call episodes. Plays of a game, trips through a maze, each ending in a terminal state followed by a reset. There, the return is simply the sum of rewards to the final step. G sub t equals R sub t plus 1 plus R sub t plus 2 plus dots. C'est plus R sub t. In continuing tasks, there is no natural final step, and the undiscounted sum could easily be infinite. The remedy is discounting, in which the agent maximizes the expected discounted return. G sub t equals R sub t plus 1 plus gamma, R sub t plus 2 plus gamma to the second, R sub t plus 3 plus dots. C equals the sum over k equals 0 gamma to the k, R sub t plus k plus 1. With discount rate gamma 0 is less than or equal to gamma is less than or equal to 1. The discount rate determines the present value of future rewards. A reward k steps in the future is worth gamma to the k, 1 times as much as an immediate one. With gamma equals 0, the agent is myopic, concerned only with maximizing immediate rewards. As gamma approaches 1, the return objective takes future rewards into account more strongly. The agent becomes more far-sighted. The returns at successive time steps satisfy the recursive identity G sub t equals R sub t plus 1 plus gamma G sub t plus 1, the quiet engine behind nearly all later algorithms. The book unifies the two cases with one elegant convention. Treat episode termination as entry into a special absorbing state that transitions only to itself and that generates only rewards of 0. Then a single definition of return covers episodic and continuing tasks. And we use these conventions throughout the rest of the book to simplify notation and to express the close parallels between episodic and continuing tasks. Unified notation for episodic and continuing tasks. In the end, one notation must serve both task kinds, and the absorbing state convention is what makes that possible. For episodic tasks, the time steps of each episode are numbered anew from 0, which in full form would require double indices. S sub t comma I, the state at time t of episode I. The authors allow a convenient abuse. We almost never have to distinguish between different episodes, so they drop the episode subscript and write S sub t for S sub t comma I. Combined with the absorbing state convention, the return can be written as one expression allowing t equals infinity or gamma equals 1, but not both. This convention is not cosmetic. It is the mechanism by which a single line of equations will later serve TD, Monte Carlo, and in-step methods across both formulations. Policies and value functions. Nearly all reinforcement learning algorithms estimate value functions, and value functions are defined relative to policies. A policy is a mapping from states to probabilities of selecting each possible action. Pi of a given S is the probability that a sub t equals if S sub t equals S. The state value function V sub pi of S is the expected return when starting in S and following pi thereafter. The action value function Q sub pi of S A is the expected return starting from S, taking the action A, and thereafter following policy pi. Both can be estimated from experience. Average the actual returns that have followed a state or a state action pair, and the averages converge to the true values. These are the Monte Carlo methods of Chapter 5. With very many states, averages per state become impractical and the values would have to be maintained as parameterized functions, the subject of Part 2. The chapter's theoretical centerpiece is that value functions satisfy a recursive consistency condition, the Bellman equation for V sub pi. The value of a state must equal the discounted expected value of its successor states, plus the reward expected along the way. The equation is derived carefully as an expected value over all triples, A, S, R, and the backup diagram is introduced. Open circles for states and solid circles for state. Action pairs as the graphical summary of the update or backup operations that are at the heart of reinforcement learning methods. These operations transfer value information back to a state or a state action pair from its successor states, and backup diagrams will recur throughout the book. The examples carry the abstraction into feeling. The grid world, where the value of state A is less than its immediate reward of plus 10 because it leads to A on the edge of the grid, while state B is valued more than its immediate plus 5 because B leads toward A and B. In the golf example, where putting contour lines show that a state's value is 1 less than the value of the state's one stroke can reach. Optimal policies and optimal value functions. Solving an MDP means finding a policy whose long-term return cannot be improved, and the theory hands us a remarkably local characterization. The value functions for a policy define what that policy achieves. The optimal value functions v times and q times, assigned to each state or state action pair, the largest expected return achievable by any policy. A policy whose value functions are optimal is an optimal policy. The optimal value functions are unique for a given MDP, but there could be many optimal policies. The Bellman optimality equation expresses the crucial fact that the value of a state under an optimal policy must equal the expected return for the best action from that state, with a max over actions instead of an expectation under a fixed policy. For finite MDPs, it is a system of n equations in n unknowns with a unique solution, solvable in principle if the dynamics are known. Once v times is in hand, an optimal policy is relatively easy to determine. For each state, assign non-zero probability only to actions attaining the maximum. The authors underscore the beauty of this. Any policy that is greedy with respect to the optimal evaluation function v asterisk operator is an optimal policy, because v times already takes into account the reward consequences of all possible future behavior. A one-step-ahead greedy search yields the long-term optimal actions. The long-term is made locally and immediately available. With q times, the agent does not even have to do a one-step-ahead search, because the action value function effectively caches the results of all one-step-ahead searches for every state action pair at the cost of representing a function of more arguments. Optimality and approximation. The chapter closes by managing expectations, and this management is itself doctrine. Clearly, an agent that learns an optimal policy has done very well, but in practice this rarely happens. Optimal policies can be generated only with extreme computational cost. A well-defined notion of optimality organizes the approach to learning we describe in this book and provides a way to understand the theoretical properties of various learning algorithms. But it is an ideal that agents can only approximate. Even with a perfect model, large custom-designed computers still cannot compute the optimal moves of chess. What constrains the agent is computational power per time step in memory. In most practical cases, there are far more states than could possibly be entries in a table, forcing compact, parameterized approximations. Yet the framing also presents us with some unique opportunities for achieving useful approximations. Because reinforcement learning is online, an agent can put more effort into learning to make good decisions for frequently encountered states at the expense of less effort for infrequently encountered states. The example is Tesoro's TD Gammon. It plays with exceptional skill even though it might make very bad decisions on board configurations that never occur in games against experts. It is possible that TD Gammon makes bad decisions for a large fraction of a game state set. This property, deploying approximation where it matters rather than where it is complete, distinguishes reinforcement learning from other approaches to approximately solving MDPs. Quote, that all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal, called reward. Section 3.2, the reward hypothesis. Quote, the reward signal is your way of communicating to the agent what you want achieved, not how you want it achieved. Section 3.2. Quote, the beauty of the asterisk operator is that if one uses it to evaluate the short-term consequences of actions, specifically the one-step consequences, then a greedy policy is actually optimal in the long-term sense in which we are interested because the asterisk operator already takes into account the reward consequences of all possible future behavior. Section 3.6. Chapter 4, Dynamic Programming. Policy Evaluation, Prediction. DP is the theoretical backbone of reinforcement learning, the family of algorithms that compute optimal policies given a perfect model of the environment as a Markov decision process. The authors immediately qualify its practical status. Classical DP algorithms are of limited utility in reinforcement learning both because of their assumption of a perfect model and because of their great computational expense, and then elevated they are still important theoretically. DP provides an essential foundation for the understanding of the methods presented in the rest of this book. In fact, all of these methods can be viewed as attempts to achieve much the same effect as DP, only with less computation and without assuming a perfect model of the environment. This sentence is the book's architecture in miniature, and the chapter that follows, it is deliberately classical. The key idea of DP and of reinforcement learning generally is the use of value functions to organize and structure the search for good policies. DP algorithms are obtained by turning Bellman equations into assignments, that is, into update rules for improving approximations of the desired value functions. The first such computation is policy evaluation, the prediction problem computing v sub pi for an arbitrary fixed policy pi. With the dynamics completely known, 4.4, is a system of simultaneous linear equations in S unknowns, solvable in principle but straightforward if tedious. The practical route is iterative policy evaluation. Start with any v sub 0, terminal states at 0, and repeatedly apply the Bellman equation for v sub pi as an update rule, producing v sub 1 v sub 2 dots. C that converge to v sub pi under the same conditions that guarantee its existence. Each sweep produces the same operation to each state S. Replace the old value of S with a new value, obtained from the old values of the successor states of S, and the expected immediate rewards, along all the one-step transitions possible under the policy being evaluated. The book names the operation with care, an expected update, because it is based on an expectation over all possible next states rather than on a sample next state. The contrast with sample updates will drive Chapter 8. A gentle implementation, note, foreshadows much. The in-place version, where each new value immediately overwrites the old one, usually converges faster than the two-array version, as you might expect, because it uses new data as soon as they are available. So the book usually has the in-place version in mind when we think of DP algorithms. The example: policy evaluation on a small grid world under the random policy shows values spreading backward from the goal and the corresponding greedy policies improving toward optimal by the third iteration. Policy improvement. Policy evaluation answers, how good is a given policy? Policy improvement asks how to make it better. Suppose the agent follows policy pi, but in state S considers taking action is not equal to pi of S once. The value of this one deviation is q sub pi of SA. If it is greater, that is, if it is better to select a once in S and thereafter follow pi than it would be to follow pi all the time, then one would expect it to be better still to select it every time S is encountered. This expectation is justified by the policy improvement theorem. For deterministic policies pi and pi, with q sub pi of S pi S is greater than or equal to v sub pi of S for all S, the new policy must be as good as or better than pi everywhere, strictly better at any state where the inequality is strict. The proof is given as a chain of expansions, an anadiplosis of equations in which the q side is repeatedly unwrapped with a return identity and the policy value relation, until v sub pi exceeds v sub pi of S. The natural extension is to change the policy at all states at once, selecting in each state the action that appears best, the greedy policy with respect to v sub pi. By construction, the greedy policy meets the conditions of the policy improvement theorem, so we know that it is as good as or better than the original policy. The move has a subtle point of doctrine. If the greedy policy is as good as but not better than the old one, then the greedy policy satisfies the Bellman optimality equation, and both pi and pi must be optimal policies. Thus, policy improvement must give us a strictly better policy except when the original policy is already optimal. Stochastic policies extend naturally. Ties may be apportioned arbitrarily among maximizing actions as long as submaximal actions receive zero probability. Policy iteration. Alternate evaluation and improvement until neither changes. That is policy iteration. Once a policy pi is improved to a greedy policy pi, the new policy has a new value function, which can be evaluated, then improved again. Each pass strictly improves the policy unless the current one is already optimal. And because a finite MDP has only a finite number of policies, this process must converge to an optimal policy and optimal value function in a finite number of iterations. The authors stress with the examples how few iterations are often needed. On the small grid world, policy iteration would find the optimal policy after just one iteration. In Jack's car rental problem, the sequence of policies converges in surprisingly few sweeps. Jack's car rental deserves its place in the chapter's memory. Jack manages 2 locations for a nationwide car rental company. Customers arrive at each location each day. Each rental credits Jack $10, and cars become available the day after return. Jack can move cars between the 2 locations overnight at a cost of $2 per car moved, with requests and returns modeled as Poisson random variables, at most 20 cars per location, and at most 5 cars moved nightly. The state is the number of cars at each location at day's end. The actions are the net numbers moved overnight. Policy iteration drives the value function and the sequence of policies to optimality, and the exercise variance, a free shuttle for 1 car, a $4 surcharge for a second parking lot, point to the general lesson that these sorts of nonlinearities and arbitrary dynamics often occur in real problems and cannot easily be handled by optimization methods other than dynamic programming. Value iteration. Policy iteration's evaluation step is costly. Value iteration truncates it to a single sweep. One drawback to policy iteration is that each of its iterations involves policy evaluation, which may itself be a protracted iterative computation requiring multiple sweeps through the state set. But the grid world example showed that it may be possible to truncate policy evaluation. Iterations beyond the first 3 had no effect on the corresponding greedy policy. The special case where policy evaluation is stopped after 1 sweep is value iteration. V sub k plus 1 of s equals max a er sub t plus 1 plus gamma v sub k s sub t plus 1 given s sub t equals s a sub t equals a. This is obtained simply by turning the Bellman optimality equation into an update rule, and differs from policy evaluation's update only in taking the max over actions instead of the expectation under a policy. In practice, it formally requires an infinite number of iterations to converge exactly, so it stops once the value function changes by only a small amount in sweep. The chapter's most charming worked example is the gambler's problem. A gambler with capital in integer dollars bets on fair-looking coin flips with head probability p sub h, winning a stake on heads and losing it on tails, until reaching $100 or ruin. Reward is +1 only on reaching the goal, so the state value function gives the probability of winning from each state, and the optimal policy maximizes the probability of reaching the goal. For p sub h equals 0 point for the final policy is optimal, but not unique, with a curious form. At capital 50, the gambler bets it all on 1 flip. At 51, he does not. An exercise in understanding why a losing game rewards aggressive all-in stakes at exactly the right capitals. Asynchronous dynamic programming and generalized policy iteration. DP's great practical weakness is the full sweep over the state set, and the remedy is to break evaluation and improvement into fine-grained interleaved updates. If the state set is very large, then even a single sweep can be prohibitively expensive. For example, the game of backgammon has over 10 to the 20th states. Even if we could perform the value iteration update on 1 million states per second, it would take over 1,000 years to complete a single sweep. Asynchronous DP algorithms are in-place iterative DP algorithms that are not organized in terms of systematic sweeps of the state set. They update the values of states in any order whatsoever, using whatever values of other states happen to be available. For discounted MDPs, convergence is guaranteed, given only that all states occur in the sequence an infinite number of times. This flexibility enables a repeated theme. Asynchronous algorithms also make it easier to intermix computation with real-time interaction, focusing updates onto parts of the state set that are most relevant to the agent. The chapter then names the idea that unifies almost everything that follows: generalized policy iteration, GPI, the general idea of letting policy evaluation and policy improvement processes interact, independent of the granularity and other details of the two processes. Policy iteration and value iteration are only extreme cases of one spectrum. The evaluation and improvement processes can be viewed as both competing and cooperating. Making the policy greedy typically makes the value function incorrect for the change policy, while making the value function consistent typically causes that policy no longer to be greedy in the long run. However, these two processes interact to find a single joint solution: the optimal value function and an optimal policy. The diagram the book draws two non-orthogonal constraint lines in a plane, each process driving toward one line at the cost of drifting from the other, is offered with the caveat that the real geometry is much more complicated, yet it captures the dynamic efficiency of dynamic programming. The chapter closes with an apology for DP's reputation and a precise statement of what it costs. DP may not be practical for very large problems, but compared with other methods for solving MDPs, DP methods are actually quite efficient. In the worst case, DP takes a number of computational operations that is less than some polynomial function of n and k, the numbers of states and actions, and is guaranteed to find an optimal policy in polynomial time, even though the total number of deterministic policies is k to the n. In this sense, DP is exponentially faster than any direct search in policy space could be. Linear programming can solve MDPs with better worst-case guarantees in some cases, but becomes impractical at a much smaller number of states than do DP methods, by a factor of about 100. For the largest problems, only DP methods are feasible. The book concedes the curse of dimensionality. The number of states grows exponentially with the number of state variables, but insists the difficulty is inherent to the problems, not to DP as a solution method, a distinction that will matter again in the approximation chapters. Quote, classical DP algorithms are of limited utility in reinforcement learning both because of their assumption of a perfect model and because of their great computational expense, but they are still important theoretically. DP provides an essential foundation for the understanding of the methods presented in the rest of this book. In fact, all of these methods can be viewed as attempts to achieve much the same effect as DP, only with less computation and without assuming a perfect model of the environment. Chapter 4 opening. Quote, the key idea of DP and of reinforcement learning generally is the use of value functions to organize and structure the search for good policies. Chapter 4 opening. Quote, the evaluation and improvement processes in GPI can be viewed as both competing and cooperating. In the long run, however, these two processes interact to find a single joint solution: the optimal value function and an optimal policy. Section 4.6. Chapter 5. Monte Carlo Methods. Monte Carlo Prediction. The chapter presents the first learning methods of the book. First learning methods for estimating value functions and discovering optimal policies that do not assume complete knowledge of the environment. Monte Carlo methods require only experience, sample sequences of states, actions, and reward from actual or simulated interaction with an environment. The significance is stated plainly. Learning from actual experience is striking because it requires no prior knowledge of the environment's dynamics, yet can still attain optimal behavior. And the authors add the subtler point that will recur. In surprisingly many cases, it is easy to generate experience sampled according to the desired probability distributions, but infeasible to obtain the distributions in explicit form. Monte Carlo methods are ways of solving the reinforcement learning problem based on averaging sample returns, defined here only for episodic tasks, so that well-defined returns are available and only on the completion of an episode are value estimates and policies changed. The methods sample and average returns for each state. Action pair much like the bandit methods we explore in Chapter 2 sample and average rewards for each action. The main difference being that now there are multiple states, each acting like a different bandit problem, and the return after taking an action in one state depends on the actions taken in later states in the same episode. So, the problem becomes non-stationary from the point of view of the earlier state. The answer to this non-stationarity is the same architecture Chapter 4 built. generalized policy iteration, adapted so that we learn value functions from sample returns with the MDP rather than computing them from a model. For a given policy pi and state S, the state's value is simply the average of the returns observed after visits to that state. Two flavors matter. The first visit MC method estimates V sub pi of S as the average of the returns following first visits to S, while the every visit MC method averages the returns following all visits to S. First visit MC is the one we focus on in this chapter, having been most widely studied, dating back to the 1940s. Every visit MC extends more naturally to function approximation and eligibility traces. Convergence is easy to see for a first visit. Each return is an independent, identically distributed estimate of V underscore pi, S, with finite variance. So by the law of large numbers, the averages converge, each average an unbiased estimate, and the standard deviation of its error falls as 1 over the square root of n. The worked example is blackjack, an episodic finite MDP with 200 states, the player's current sum, the dealer's showing card, and whether the player holds a usable ace. Rewards of +1, -1, 0 for win/lose/draw, and no discounting. The policy that sticks only on 20 or 21 is evaluated by simulating many blackjack games using the policy and averaging the returns following each state. The chapter draws the crucial pedagogical contrast. Even with complete knowledge of the environment in the blackjack task, it would not be easy to apply DP methods because DP requires the distribution of next events, and it is not easy to determine this for blackjack. An entire probability distribution over outcomes must be computed before DP can start. Monte Carlo estimation of action values. For control, the state value function is not enough. Action values must be estimated. If a model is not available, then it is particularly useful to estimate action values rather than state values, because with a model, state values alone are sufficient to determine a policy. One looks ahead one step. But without a model, only action values are sufficient. The formula is the one consideration that complicates action values without models. The distinction between on-policy methods, which attempt to evaluate or improve the policy that is used to make decisions, and off-policy methods, which evaluate or improve a policy different from that used to generate the data. For on-policy action value estimation, we must estimate Q underscore pi, S, A, for all state action pairs where the policy would act, which requires ensuring that all actions are selected infinitely often. And since the average over visits to a state, action pair presumes the policy states get visited. Each state, action pair, or each state must be visited a large number of times. Monte Carlo control. Applying GPI to Monte Carlo methods yields control algorithms built on experience. The obvious first version is Monte Carlo ES, exploring starts, which assumes each episode starts in a state, action pair, and that every pair has a non-zero probability of being selected as the start. Under this assumption, all the returns for each state, action pair are accumulated and averaged, irrespective of what policy was in force when they were observed, and the policy is repeatedly made greedy with respect to the current queue. The chapter is candid about the theory. It is easy to see that Monte Carlo ES cannot converge to any suboptimal policy, and stability is achieved only when both the policy and the value function are optimal. But convergence to this optimal fixed point seems inevitable as the changes to the action value function decrease over time, but has not yet been formally proved. In our opinion, this is one of the most fundamental open theoretical questions in reinforcement learning. Applied to blackjack, Monte Carlo ES recovers the same as the basic strategy of Thorpe, 1966, with the sole exception of the leftmost notch in the policy for a usable ace, a discrepancy the authors flag with humility. We are uncertain of the reason for this discrepancy, but confident that what is shown here is indeed the optimal policy for the version of blackjack we have described. The epistemic posture is worth noting. The authors trust their formal method over a famous published strategy, but admit they cannot explain the divergence. Monte Carlo control without exploring starts. Exploring starts can sometimes be arranged in applications with simulated episodes, but are unlikely in learning from real experience. The only general way to ensure that all actions are selected infinitely often is for the agent to continue to select them. And the chapter's two routes are the on-policy/off-policy distinction. The on-policy control method presented uses epsilon greedy policies. Most of the time, they choose an action that has maximal estimated action value, but with probability epsilon, they instead select an action at random. Greedy becomes a species of epsilon soft policy. All non-greedy actions are given the minimal probability of selection, epsilon/as, and the remaining bulk of the probability, 1 minus epsilon plus epsilon/as, is given to the greedy action. Notably, the epsilon greedy policies are in some sense those that are closest to greedy among epsilon soft policies. The theoretical subtlety is that GPI does not require that the policy be taken all the way to a greedy policy, only that it be moved toward a greedy policy. The policy improvement theorem still applies because for any epsilon soft policy pi, any epsilon greedy policy with respect to q_pi is guaranteed to be better than or equal pi. The proof closes a loop. Equality holds only when both policies are optimal among the epsilon soft policies, shown by embedding the epsilon randomness inside a modified environment whose transition probabilities blend the epsilon soft constraint. The honest caveat follows. Now we only achieve the best policy among the epsilon soft policies, but on the other hand, we have eliminated the assumption of exploring starts. Off-policy prediction via importance sampling. The chapter's deepest idea is that the agent can learn about one policy while behaving according to another. All learning control methods face a dilemma. They seek to learn action values conditional on subsequent optimal behavior, but they need to behave non-optimally in order to explore all actions. The on-policy approach is actually a compromise. It learns action values not for the optimal policy, but for a near-optimal policy that still explores. The more straightforward approach is to use two policies, the target policy being learned about, which becomes optimal, and a behavior policy, more exploratory and used to generate behavior. This is off-policy learning. Off-policy methods are generally of greater variance and are slower to converge, but they are more powerful in general, including on-policy methods as the special case in which the target and behavior policies are the same, and they can often be applied to learn from data generated by a conventional non-learning controller or from a human expert. Below the definitions sits a requirement and a technique. The requirement is coverage. Every action taken under pi is also taken, at least occasionally, under B, which follows that B must be stochastic in states where it is not identical to pi, while the target policy pi, on the other hand, may be deterministic. The technique is importance sampling, a general technique for estimating expected values under one distribution given samples from another. Returns are weighted by the importance sampling ratio, the relative probability of the trajectory under target and behavior policies. Because the transition probabilities appear identically in numerator and denominator, they cancel. The importance sampling ratio ends up depending only on the two policies and not on the MDP. The chapter then records an essential practical discovery, ordinary importance sampling. A simple average of the weighted returns is always v_pi s. In expectation, it is unbiased, but can be extreme, whereas weighted importance sampling, a weighted average, is biased, though the bias converges asymptotically to zero. But in the weighted estimator, the largest weight on any single return is 1, so its variance is dramatically lower. In practice, the weighted estimator usually has dramatically lower variance and is strongly preferred, though ordinary sampling is easier to extend to the approximate methods using function approximation. The infinite variance example is sobering. On a one-state MDP whose value is 1, 10 runs of first visit MC with ordinary importance sampling fail to converge to the correct value of 1, even after millions of episodes, because the scaled returns have infinite variance when the behavior and target trajectories can loop. The weighted estimator would give an estimate of exactly 1 forever after the first episode, consistent with the target. The section on the blackjack state value evaluation shows the point quantitatively. Weighted importance sampling has much lower error at the beginning, as is typical in practice. Off-policy Monte Carlo control and the discounting question. The off-policy machinery is assembled into a complete control method, then sharpened. Off-policy Monte Carlo control follows the behavior policy, while learning about and improving the target policy, which is the greedy policy with respect to Q, while the behavior policy B can be anything. But in order to assure convergence, an infinite number of returns must be obtained for each pair of state and action, ensured by choosing B to be epsilon soft. Agreed. The display of this algorithm, HC control with weighted importance sampling, learns only from the tails of episodes, when all of the remaining actions in the episode are greedy. So if non-greedy actions are common, then learning will be slow. There has been insufficient experience with off-policy Monte Carlo methods to assess how serious this problem is, and the likely remedy is incorporating temporal difference learning, the algorithmic idea developed in the next chapter. Two starred refinements close the chapter. Discounting aware importance sampling recognizes that for long episodes with gamma significantly less than 1, the return from time 0 will then be just G0 equals or 1, but its importance sampling ratio will be a product of 100 factors, most of which are all independent of the return and of expected value 1. They do not change the expected update, but they add enormously to its variance. Thinking of discounting as determining a probability of termination allows returns to be decomposed into flat partial returns, each scaled by a truncated ratio. Per decision importance, sampling goes further, factoring the scaled return so that each reward is scaled only by the ratio factors up to its own time. The non-reward factors have no effect in expectation, yet can inflate variance even without discounting. The chapter's summary gathers the case. Monte Carlo methods offer advantages over DP in learning directly from interaction without a model, in working with simulation, in focusing on a subset of states, and discussed later in the book, in being less harmed by violations of the Markov property. This is because they do not update their value estimates on the basis of the value estimates of successor states. In other words, it is because they do not bootstrap. Quote, Monte Carlo methods are ways of solving the reinforcement learning problem based on averaging sample returns. To ensure that well-defined returns are available, here we define Monte Carlo methods only for episodic tasks. Chapter 5 opening. Quote, all learning control methods face a dilemma. They seek to learn action values conditional on subsequent optimal behavior, but they need to behave non-optimally in order to explore all actions, to find the optimal actions. Section 5.5. Quote, because a state value is the expected return, this average can become a good approximation to the value. It is not enough just to select the actions currently estimated to be best, because then no returns will be obtained for alternative actions, and it may never be learned that they are actually better. Section 5.10 Summary. Chapter 6 Temporal Difference Learning. TD Prediction. The book's master claim opens the chapter. If one had to identify one idea as central and novel to reinforcement learning, it would undoubtedly be temporal difference, TD learning. TD learning is a combination of Monte Carlo ideas and dynamic programming, DP ideas. Like Monte Carlo methods, TD methods can learn directly from raw experience without a model of the environment dynamics. Like DP, TD methods update estimates based in part on other learned estimates, without waiting for a final outcome. They bootstrap. The relationship among the three is a recurring theme in the theory of reinforcement learning, and the book maps the road ahead. In-step algorithms, Chapter 7, provide a bridge from TD to Monte Carlo methods, and the TD lambda algorithm, Chapter 12, seamlessly unifies them. The chapter's own engine is the update equation. Monte Carlo methods wait until the return following the visit is known, then use that return as a target for VST. TD methods need to wait only until the next time step, immediately forming a target and making a useful update using the observed reward RT plus 1 and the estimate V, ST plus 1. V of S sub t is less than minus V of S sub t plus alpha, or sub t plus 1 plus gamma V of S sub t plus 1 minus V of S sub t. Called TD 0, or one-step TD. The bracketed quantity is the TD error. Delta sub t equals R sub t plus 1 plus gamma v of S sub t plus 1 minus v of S sub t. A sort of error, measuring the difference between the estimated value of St and the better estimate Rt plus 1 plus gamma v, St plus 1, which arises in various forms throughout reinforcement learning. Because the TD error depends on the next state and reward, it is not actually available until one time step later. The conceptual geometry is drawn precisely. Roughly, Monte Carlo methods use an estimate of the expected return as a target, whereas DP methods use an estimate of the Bellman expansion. The Monte Carlo target is an estimate because the expected value is not known. A sample return is used in place of the real expected return. The DP target is an estimate not because of the expected values, which are assumed to be completely provided by a model, but because v underscore pi, st plus 1, is not known and the current estimate v, st plus 1, is used instead. The TD target is an estimate for both reasons. Thus, TD methods combine the sampling of Monte Carlo with the bootstrapping of DP. Both TD and Monte Carlo updates are sample updates because they involve looking ahead to a sample successor state, using the value of the successor and the reward along the way to compute a backed-up value. They differ from DP's expected updates, based on a single sample successor rather than on a complete distribution of all possible successors. A key identity binds the eras together. If V does not change during the episode, the Monte Carlo error can be written as a sum of TD errors, and generalizations of this identity play an important role in the theory and algorithms of temporal difference learning. The driving home example renders the difference visceral. Each state, leaving the office, reaching the car in the rain, exiting the highway, stuck behind a truck, has a prediction of time to go. TD corrects each state's estimate one step later using the next state's estimate plus the reward along the way, while Monte Carlo waits until the actual arrival. The example makes vivid why an incremental, one-step method is natural for a learner whose predictions must serve decision-making along the way. Advantages of TD prediction methods. TD and Monte Carlo both learn from experience, but they answer different questions. The chapter lists the advantages with the care of a legal brief. First, TD methods do not require a model of the environment, of rewards, or of next states. Second, TD methods are fully incremental methods. It is not necessary to wait until the end of an episode before updating, so the learner need not wait for a terminal outcome to make good use of its experience. This matters if the episodes are very long. The delays may be substantial. In continuing tasks, there may be no episode end at all. Third, and most subtly, the predictions one makes become useful as a basis for behavior. Yet the predictions can be delayed long after the behavior that determines them has been taken. In TD, the learning and its use are interwoven. The predictions that are improved are those that are relevant to decisions. This last point is the one that most distinguishes TD from Monte Carlo as an agent-oriented method. The chapter is honest that the empirical case is strong, but the theoretical one open. In practice, however, TD methods have usually been found to converge faster than constant alpha MC methods on stochastic tasks. The random walk example, an MRP with 5 non-terminal states and termination on the extremes, reward +1 only for right termination, shows TD, 0, consistently better than the MC method on this task across step sizes, measured by RMS error averaged over 100 runs. Optimality of TD, 0. The chapter turns to batch updating to isolate what TD actually converges to, and finds it optimal in a way MC is not. Suppose there is available only a finite amount of experience. In batch updating, updates are made only after processing each complete batch of training data, presenting the experience repeatedly until convergence. Under batch updating, TD, 0, converges deterministically to a single answer independent of the step size parameter, alpha, as long as alpha is chosen to be sufficiently small, and the constant alpha MC method also converges deterministically under the same conditions, but to a different answer. The difference is the chapter's most instructive lesson. In batch training, constant alpha MC converges to values, VS, that are sample averages of the actual returns experienced after visiting each state S, which are optimal estimates in the sense that they minimize the mean square error from the actual returns in the training set. Yet batch TD was able to perform better on a random walk. How is it that batch TD was able to perform better than this optimal method? The answer: the Monte Carlo method is optimal only in a limited way, and that TD is optimal in a way that is more relevant to predicting returns. The parable is you are the predictor. After 8 episodes in a tiny MRP, everyone agrees V of B equals 3/4, because 6 out of the 8 times in state B the process terminated immediately with a return of 1. But what is V of A? The sample average MC answer is 0, because 100% of the times the process was in state, it traversed immediately to B, with a reward of 0. The TD answer is 3/4, based on modeling the Markov process and then computing the correct estimates given the model. The MC estimate is right about the observed data. The TD estimate is right about the underlying Markov chain. And in this simplest case, TD's answer is also the answer that would be obtained by a DP method if we first formed the maximum likelihood estimate of the Markov process, the certainty equivalence estimate, and then computed the corresponding value function. Thus, in the batch, unchanging case, TD0 converges to the certainty equivalence estimate, while MC converges to the minimum squared error estimate on the observed data, a distinction between fitting the model and fitting the sample. At the price of some variance, TD methods give the same answer as DP for a Markov model estimated from the data, which is usually the better prediction. SURSA on-policy TD control. By learning action values instead of state values, TD prediction becomes control. We turn now to the use of TD prediction methods for the control problem, following GPI, only this time using TD methods for the evaluation or prediction part. The on-policy method is SURSA, named for the quintuple of events, S sub t A sub t R sub t plus 1S sub t plus 1A sub t plus 1, that make up a transition from one state action pair to the next. Q of S sub t A sub t is less than minus Q of S sub t plus alpha R sub t plus 1 plus gamma Q of S sub t plus 1A sub t plus 1 minus Q of S sub t A sub t. It is straightforward to design an on-policy control algorithm based on the SURSA prediction method, continually estimating Q sub pi for the behavior policy while at the same time chong pi toward greediness with respect to Q pi. Convergence holds with probability 1 to an optimal policy and action value function, under the usual conditions on the step sizes as long as all state action pairs are visited an infinite number of times and the policy converges in the limit to the greedy policy. The windy grid world example shows SURSA learning the optimal path from star to goal under a gusting wind that displaces the agent a fixed number of cells per column. The episode-by-episode path length falls to the optimal 15 steps. The closing remark anticipates a theme the cliff-walking example will make vivid. Near-deterministic off-policy methods like Q-learning can find that some path is better in general, apparently, but online learning methods such as SURSA do not have this problem. Q-learning, off-policy TD control. One of the early breakthroughs of the field is an off-policy TD control algorithm that learns the optimal value function directly. Q-learning, Watkins, 1989, is defined by Q of S sub t A sub t is less than minus Q of S sub t plus alpha R sub t plus 1 plus gamma max A Q of S sub t plus 1 minus Q of S sub t A sub t. In this case, the learned action value function Q directly approximates Q star, the optimal action value function, independent of the policy being followed. This independence dramatically simplifies the analysis of the algorithm and enabled early convergence proofs. The policy still has an effect in that it determines which state action pairs are visited and updated, but all that is required for correct convergence is that all pairs continue to be updated. Under that condition, and a variant of the usual stochastic approximation conditions, Q has been shown to converge with probability 1 to Q star. The cliff walking example makes the on policy / off policy difference concrete and punchy. In a grid world where stepping into the cliff incurs reward -100 and sends the agent back to start, after an initial transient, Q-learning learns values for the optimal policy, that which travels right along the edge of the cliff. Unfortunately, this results in its occasionally falling off the cliff because of the epsilon greedy action selection. Sursa, on the other hand, takes the action selection into account and learns the longer but safer path through the upper part of the grid. The lesson reframes what each method optimizes. Although Q-learning actually learns the values of the optimal policy, its online performance is worse than that of Sursa, which learns the roundabout policy. Expected Sursa, maximization bias, and double learning. The chapter's final settlements make the family of one-step TD control methods complete. Expected Sursa is just like Q-learning except that instead of the maximum over next state action pairs, it uses the expected value, taking into account how likely each action is under the current policy. It subsumes and generalizes Q-learning while reliably improving over Sursa. If pi is the greedy policy while behavior is more exploratory, then expected Sursa is exactly Q-learning. In deterministic environments, expected Sursa can safely set alpha equals 1 without suffering any degradation of asymptotic performance, where Sursa cannot, and in this and other examples, there is a consistent empirical advantage of expected Sursa over Sursa, so that except for the small additional computational cost, expected Sursa may completely dominate both of the other more well-known TD control algorithms. Then comes a subtle failure mode and its remedy. All the control algorithms that we have discussed so far involve maximization in the construction of their target policies, and a maximum overestimated values is used implicitly as an estimate of the maximum value, which can lead to a significant positive bias, maximization bias. The reason is that if many actions have true value 0 but noisy estimates, the maximum of the true values is 0, but the maximum of the estimates is positive. The example MDP is brutal. Taking left leads to a state whose return is always -0.1. Yet Q-learning initially learns to strongly favor the left action because maximization bias makes the intermediate state appear positive. The remedy is double learning. One way to view the problem is that it is due to using the same samples, plays, both to determine the maximizing action and to estimate its value. By dividing the samples to learn two independent estimates, Q sub 1 and Q sub 2, and using one estimate to determine the maximizing action A star equals argmax of Q1, and the other, Q2, to provide the estimate of its value. The estimate is unbiased. Double Q-learning splits its updates by a coin flip, learning two value functions symmetrically. On the example, double learning seems to eliminate the harm caused by maximization bias. This doubles memory, but does not increase the amount of computation per step. The chapter also notes after states, value functions over positions after the agent has made its move, as in the tic-tac-toe learner, which are useful when we have knowledge of an initial part of the environment's dynamics, but not necessarily of the full dynamics, as in chess, where one knows the immediate consequences of every legal move. Quote, if one had to identify one idea as central and novel to reinforcement learning, it would undoubtedly be temporal difference, TD, learning. TD learning is a combination of Monte Carlo ideas and dynamic programming, DP, ideas. Chapter 6 Opening. Quote, the TD target is an estimate for both reasons. It samples the expected values, and it uses the current estimate V instead of the true V pi. Thus, TD methods combine the sampling of Monte Carlo with the bootstrapping of DP. Section 6.1. Quote, the answer is that the Monte Carlo method is optimal only in a limited way, and that TD is optimal in a way that is more relevant to predicting returns. Section 6.3. Chapter 7. In-step bootstrapping. In-step TD prediction. The chapter unifies Monte Carlo and one-step TD methods, and in so doing frees you from the tyranny of the time step. Neither MC methods nor one-step TD methods are always the best, and in-step methods span a spectrum with MC methods at one end and one-step TD methods at the other. The best methods are often intermediate between the two extremes. The motivating pressure is practical and precise. With one-step TD methods, the same time step determines how often the action can be changed and the time interval over which bootstrapping is done. In many applications, one wants to be able to update the action very fast, but bootstrapping works best if it is over a length of time in which a significant and recognizable state change has occurred. With one-step methods, these time intervals are the same, and so a compromise must be made. In-step methods enable bootstrapping to occur over multiple steps, freeing us from the tyranny of the single-time step. The book treats the in-step idea on its own, postponing eligibility traces, Chapter 12, so that the mechanism can be understood separately before the two are combined. The construction is elegant. Monte Carlo updates toward the complete return G sub t. One-step TD updates toward the one-step return G sub t. T plus 1 equals R sub t plus 1 plus gamma V sub ts sub t plus 1. Our point now is that this idea makes just as much sense after two steps as it does after one. The target for an arbitrary in-step update is the in-step return. G sub t. T plus n equals R sub t plus 1 plus gamma R sub t plus 2 plus dots. C plus gamma to the n. 1 R sub t plus n plus gamma to the nv sub t plus n. 1 of s sub t plus n. Truncated after n steps, and then corrected for the remaining missing terms by vt plus n minus 1 st plus n. Because the in-step return involves future rewards and states that are not available at the time of transition from t to t plus 1, no real algorithm can use the in-step return until after it has seen rt plus n and computed vt plus n minus 1. The first time these are available is t plus n. Hence, in-step TD updates only after n steps. No changes at all are made during the first n minus 1 steps of each episode. And an important property of in-step returns is that their expectation is guaranteed to be a better estimate of vpi than vt plus n minus 1 is. In-step SURSA. The identical logic applied to action values yields in-step SURSA, just as the value of a state satisfies the recursive return identity. So does the value of a state action pair, and the in-step return for actions replaces the final state value estimate with the estimated value of the nth next state. Action pair. G sub t. T plus n equals R sub t plus 1 plus gamma R sub t plus 2 plus dots. C plus gamma to the n. 1 R sub t plus n plus gamma to the n q sub t plus n. 1 of s sub t plus n a sub t plus n. With in-step SURSA updating toward it. The payoff is made vivid by a small grid world. The first panel shows the path taken by an agent in a single episode, ending at a location of high reward, where all rewards were 0 except for a positive reward at G. With one-step SURSA, only the last action of the sequence of actions that led to the high reward is strengthened. The in-step method strengthens the last n actions of the sequence, so that much more is learned from the one episode. This is the chapter's picture of why multi-step bootstrapping speeds learning. Credit propagates faster along the trajectory. In-step off-policy learning. Off-policy in-step learning weights returns by the relative probability of the in-taken actions under target and behavior policies. The natural generalization weights the in-step update by the importance sampling ratio rho sub t. T plus n. 1. The product of the ratios of the n actions from at2 at plus n minus 1. The intuition is stated crisply. If by chance an action is taken that pi would take with much greater probability than b does, then this will increase the weight. That action is characteristic of pi, and therefore we won't learn about it, but is selected only rarely by b. The off-policy version of in-step expected SURSA needs one fewer factor in its ratio, because in expected SURSA, all possible actions are taken into account in the last state. The one actually taken has no effect and does not have to be corrected for. Per decision methods with control variates. The chapter then improves the naive ratio weighting with a control variate. The recursive in-step return can be written G sub t. H equals or sub t plus 1 plus gamma g sub t plus 1. H. Weighting the whole right-hand side by rho sub t is tempting but crude. Suppose the action at time t would never be selected by pi, so that rho t is 0. Then a simple weighting would result in the in-step return being 0, which could result in high variance. The refined alternative. G sub t. H equals rho sub t r sub t plus 1 plus gamma g sub t plus 1. H plus 1 minus rho sub t v sub h, 1 of s sub t. Causes no change. Instead of shrinking the estimate when the ratio is 0, the importance sampling ratio being 0 means we should ignore the sample. So leaving the estimate unchanged seems appropriate. The added term is called a control variate, and the control variate does not change the expected update because the ratio has expected value 1 and is uncorrelated with the estimate. 4 action values. That first action is the one being learned. It does not matter if it was unlikely or even impossible under the target policy. It has been taken, and now full unit weight must be given to the reward and state that follows it. So importance sampling applies only to the actions that follow. The chapter closes this section with characteristic honesty. Importance sampling results in high variance updates, forcing the use of a small step size parameter and thereby causing learning to be slow, and it is probably inevitable that off-policy training is slower than on-policy training. After all, the data is less relevant to what is being learned. The in-step tree backup algorithm. The chapter answers a pointed question. Is off-policy learning possible without importance sampling? Q-learning and expected SURSA do this for the one-step case, and the chapter's in-step answer is tree backup. The idea is suggested by the backup diagram. Down the central spine are 3 sample states and rewards and 2 sample actions. Hanging off to the sides of each state are the actions that were not selected. Because we have no sample data for the unselected actions, we bootstrap and use the estimates of their values in forming the target. Hence, is an update from the entire tree of estimated action values. Each non-selected action contributes with a weight proportional to its probability of occurring under the target policy pi, so that each first-level action contributes with a weight of pi, st plus 1, except that the action actually taken at plus 1 does not contribute at all. Tree backup allows off-policy multi-step learning with no importance sampling ratios, at the cost of branching over all actions at every level. A unifying algorithm. In-step Q, sigma. The chapter closes by unifying its 3 action value algorithms into one. In-step SURSA has all sample transitions. The tree backup algorithm has all state-to-action transitions fully branched without sampling, and in-step expected SURSA has all sample transitions except for the last state-to-action one, which is fully branched. The unification. One might decide on a step-by-step basis whether one wanted to take the action as a sample, as in SURSA, or consider the expectation over all actions instead, as in the tree backup update. Choosing always to sample gives SURSA, never gives tree backup. Sampling, for all steps except for the last one, gives expected SURSA. Interpolating continuously, a parameter sigma sub t in 0, 1 denote s, the degree of sampling on step t, with sigma t equals 1 denoting full sampling and sigma t equals 0 denoting a pure expectation, sliding linearly in the recursion between the action's importance sampling ratio and its probability under pi. This is in-step Q, sigma. The summary places the family in the book's trajectory. All in-step methods involve a delay of n times steps before updating, involve more computation per time step, and require more memory to record the states, actions, rewards over the last n time steps. Eventually, in Chapter 12, we will see how multi-step TD methods can be implemented with minimal memory and computational complexity using eligibility traces. But there will always be some additional computation beyond one-step methods. Such costs can be well worth paying to escape the tyranny of the single-time step. And the chapter makes a strategic virtue of its own pedagogy. Although in-step methods are more complex than those using eligibility traces, they have the great benefit of being conceptually clear, which is why the book develops both approaches to off-policy learning here. Important sampling-based, conceptually simple, but high variance, and tree backup-based, the natural extension. Quote, another way of looking at the benefits of in-step methods is that they free you from the tyranny of the time step. Chapter 7 opening. Quote, in-step methods span a spectrum with MC methods at one end and one-step TD methods at the other. The best methods are often intermediate between the two extremes. Chapter 7 opening. Quote, the importance sampling ratio being 0 means we should ignore the sample, so leaving the estimate unchanged seems appropriate. Section 7.4. Chapter 8. Planning and Learning with Tabular Methods. Models and Planning. The chapter's aim is a unification symmetric to the one in-step methods achieved for TD and Monte Carlo. Model-based and model-free methods are distinct, but deeply share a common structure. In this chapter, we develop a unified view of reinforcement learning methods that require a model of the environment, such as dynamic programming and heuristic search, and methods that can be used without a model, such as Monte Carlo and temporal difference methods. The unifying claim is strong. Although there are real differences between these two kinds of methods, there are also great similarities. In particular, the heart of both kinds of methods is the computation of value functions. Moreover, all the methods are based on looking ahead to future events, computing a backed-up value, and then using it as an update target for an approximate value function. The chapter's project is a similar integration across the model/no model divide. Definitions anchor the vocabulary. A model is anything that an agent can use to predict how the environment will respond to its actions. A distribution model produces a description of all possibilities and their probabilities. A sample model produces just one of the possibilities, sampled according to the probabilities. The dozen dice example shows why sample models are often much easier to obtain than distribution models. Planning is defined with deliberate breadth. Any computational process that takes a model as input and produces or improves a policy for interacting with a modeled environment. State space planning is viewed primarily as a search through the state space for an optimal policy, while plan space planning is instead a search through the space of plans. The latter is set aside as ill-suited to the stochastic sequential problems at hand. The chapter's two basic ideas are that all state space planning methods involve computing value functions as a key intermediate step toward improving the policy, and they compute value functions by updates or backup operations applied to simulated experience. The difference from learning is only the source of experience. Whereas planning uses simulated experience generated by a model, learning methods use real experience generated by the environment. The common structure means a learning algorithm can be substituted for the key update step of a planning method, and the chapter offers random sample one-step tabular queue planning as the simplest illustration. A second theme, the benefits of planning in small, incremental steps, which enables planning to be interrupted or redirected at any time with little wasted computation. DINA, integrated planning, acting, and learning. When planning happens online, a new set of questions appears, and the book answers them with the DINA architecture. Within a planning agent, there are at least two roles for real experience: improving the model learning, and directly improving value functions and policies, direct reinforcement learning. Indirect learning, the latter in the diagram, improving values via the model, is involved in planning. The two routes have complementary virtues. Indirect methods often make fuller use of a limited amount of experience and thus achieve a better policy with fewer environmental interactions. On the other hand, direct methods are much simpler and are not affected by biases in the design of the model. DynaQ integrates all four functions in a simple, almost trivial form: act minus greedy, observe reward and next state, update queue directly by queue learning, update the model, and then repeat in planning steps in which randomly remembered state. Action pairs are replayed through the model and updated by queue learning. Learning and planning are deeply integrated in the sense that they share almost all the same machinery, differing only in the source of their experience. And the reinforcement learning method is thus the final common path for both learning and planning. The Dyna maze shows the payoff. The non-planning agent, N equals 0, pure one-step Q learning, took about 25 episodes to reach epsilon, optimal performance, whereas the N equals 5 agent took about 5 episodes, and the N equals 50 agent took only 3. The mechanism is illustrated by the policies halfway through the second episode. Without planning, each episode adds only one additional step to the policy, while with planning an extensive policy is built, while the agent is still wandering near the start state. The architecture slogan captures the ideal. The agent is always reactive and always deliberative, responding instantly to the latest sensory information and yet always planning in the background. When the model is wrong, models are fallible, and the chapter takes the consequences seriously. In general, we cannot expect to be so fortunate as a model filled only with exactly correct information. Models may be incorrect because the environment is stochastic and only a limited number of samples have been observed, or because the model was learned using function approximation that has generalized imperfectly, or simply because the environment has changed. When the model is wrong, the planning process is likely to compute a suboptimal policy. 2 experiments make the point concrete. In the blocking experiment, a short path to the goal is blocked partway through learning. Both DynaQ and the model-free method adapt, but the planning agent's learn model must catch up. In the shortcut experiment, a new shorter path opens near the goal, and here the plain DynaQ agent fails to find it because its model does not encourage exploration of untried actions, while a model-free method with persistent exploration keeps discovering the new path. The lesson is drawn in the register of an honest design problem. We want the agent to explore, to find changes in the environment, but not so much that performance is greatly degraded. There probably is no solution that is both perfect and practical, but simple heuristics are often effective. The DynaQ Plus agent uses one such heuristic. It keeps track for each state, action pair of how many time steps have elapsed since the pair was last tried in a real interaction, and gives a special bonus reward on simulated experiences involving long untried actions, a form of computational curiosity that may be well worth the extra exploration. Prioritized sweeping. Uniformly random planning replays are wasteful. The chapter focuses planning where value would actually propagate. Simulated transitions are started in state. Action pairs selected uniformly at random from all previously experienced pairs. But a uniform selection is usually not the best. Early in learning, only the state action pair leading directly into the goal has a positive value. So it is pointless to perform updates along almost all transitions. Many wasteful updates will be made before stumbling onto one of these useful ones. The remedy generalizes backward focusing. We want to work back not just from goal states, but from any state whose value has changed. Prioritized sweeping maintains a queue of every state, action pair whose estimated value would change non-trivially if updated, prioritized by the size of the change. When the top pair is updated, the effect on each predecessor is computed and reinserted with its own priority, so that the effects of changes are efficiently propagated backward until quiescence. On maze tasks, prioritized sweeping is dramatically faster, often by a factor of 5 to 10, and scales the problems probably too large to be solved with unprioritized methods, like the rod maneuvering task with 14,400 states and 4 actions. Expected versus sample updates. The chapter isolates one of its cleanest quantitative results. When computation, not experience, is the limiting resource, sample updates can beat expected updates. One-step updates vary primarily along 3 binary dimensions: state versus action values, estimating the value for the policy versus the optimum, and whether the update is an expected update based on the distribution of all possible next states or a sample update based on a single sample next state. The expected update is an exact computation, resulting in a new QS, whose correctness is limited only by the correctness of the QS at successor states, while the sample update is in addition affected by sampling error. But the sample update is cheaper computationally because it considers only one next state And for a particular starting pair, S, let B be the branching factor. An expected update of this pair requires roughly B times as much computation as a sample update. The trade-off follows. If there is enough time to complete an expected update, then the resulting estimate is generally better than that of B sample updates. But if there is insufficient time, then sample updates are always preferable. In large problems, we are often in the latter situation. So, given a unit of computational effort, the analysis suggests that sample updates win at large branching factors and when computational budgets are small. The deeper idea, backing up into smaller pieces, which then enables it to be focused more narrowly on the pieces that will have the largest impact, reaches its logical limit in small backups, updates along a single transition like a sample update, but based on the probability of the transition without sampling. Trajectory sampling and real-time dynamic programming. The classical uniform sweep is replaced by on-policy trajectory sampling with measured costs and benefits. The classical approach from dynamic programming is to perform sweeps through the entire state space, which is problematic on large tasks because there may not be time to complete even one sweep, and exhaustive sweeps implicitly devote equal time to all parts of the state space rather than focusing where it is needed. The alternative is to distribute updates according to the on-policy distribution. One simply interacts with a model following the current policy, simulating explicit individual trajectories, trajectory sampling. The chess intuition is memorable. If you're learning to play chess, you study positions that might arise in real games, not random positions of chess pieces. The empirical result is nuanced and therefore trustworthy. On randomly generated tasks, sampling according to the on-policy distribution resulted in faster planning initially and retarded planning in the long run, with the initial advantage longer at small branching factors and larger state counts. In the short term, sampling according to the on-policy distribution helps by focusing on states that are near descendants of the start state. In the long run, focusing on the on-policy distribution may hurt because the commonly occurring states all already have their correct values. Real-time dynamic programming, RTDP, carries the same idea into fully online control because it updates only states encountered on-policy trajectories. RTDP required only roughly half of the updates that DP did on a racetrack task with 9,115 reachable states, but only 599 relevant ones under an optimal policy. The value of every state was updated by DP, but RTDP updated only the value of the current state on each step, spending its computation where the agent actually goes. The quantitative comparison rewards close reading. On the racetrack, a close-to-optimal policy emerged after 15 sweeps of value iteration, or after 136,725 value iteration updates, considerably less than the 252,784 updates DP needed to converge to V** operator, but still more than the 127,600 updates RTDP required. And RTDP strongly focused on subsets of the states that were relevant to the problem's objective. This focus became increasingly narrow as learning continued, eventually only on states making up optimal paths, so that RTDP achieved nearly optimal control with about 50% of the computation required by sweep-based value iteration. The chapter credits the lineage honestly. Trajectory sampling has implicitly been a part of reinforcement learning from the outset, but was most explicitly emphasized by Bartow, Bratka, and Singh, 1995, in their introduction of RTDP, and RTDP itself generalizes Korf's learning real-time LRTA to stochastic problems. Planning a decision time. Heuristic search, rollouts, MCES. The chapter ends with decision time planning, the other way to use planning. Begin and complete it after encountering each new state ST as a computation whose output is the selection of a single action at. The chapter first marks the distinction between the two uses. Background planning, typified by dynamic programming and DYNA, gradually improves a policy or value function on the basis of simulated experience, so that well before an action is selected for any current state ST, planning has played a part in improving the table entries. It is not focused on the current state. Decision time planning, in contrast, focuses on a particular state, computing values and policy specific to the current state and the action choices available there, so much so that the values and policy created by the planning process are typically discarded after being used to select the current action. The chapter notes the practical trade. In chess playing programs, one may be permitted seconds or minutes of computation for each move, so decision time planning is most useful in applications in which fast responses are not required. Whereas if low-latency action selection is the priority, then one is generally better off doing planning in the background. The two modes can blend together in natural and interesting ways. Focus planning on the current state and store the results of planning so as to be that much farther along should one return to the same state later. Heuristic search, the classical state space planning methods in artificial intelligence, is decision time planning at scale. For each state encountered, a large tree of possible continuations is considered. The approximate value function is applied to the leaf nodes and then backed up toward the current state at the root, with the backing up within the search tree. Just the same as in the expected updates, stopping at the state action nodes for the current state, after which the best of them is chosen as the current action, and then all backed up values are discarded. The chapter reframes it in the book's own terms. Heuristic search can be viewed as an extension of the idea of a greedy policy beyond a single step, since to compute the greedy action given a model and a state value function, we must look ahead from each possible action to each possible next state, and then pick the best action. Deeper search pays when the model is good. If one has a perfect model and an imperfect action value function, then in fact deeper search will usually yield better policies. And if the search is all the way to the end of the episode, then the effect of the imperfect value function is eliminated. The worked lesson is TD Gammon's. It used TD learning to learn an after-state value function through many games of self-play, using a form of heuristic search to make its moves, and Tesoro found that the deeper the heuristic search, the better the moves made by TD Gammon, but the longer it took to make each move. Backgammon's large branching factor limited search to a few steps within the seconds per move allowed. But even so, the search resulted in significantly better action selections. The deeper reason for heuristic search's effectiveness is its focusing. You may spend more of your life playing chess than checkers, but when you play checkers, it pays to think about checkers and about your particular checker's position. Not only should your computation be preferentially devoted to imminent events, but so should your limited memory resources. And this great focusing of memory and computational resources on the current decision is presumably the reason why heuristic search can be so effective. Indeed, any state space search can be viewed as the piecing together of a large number of individual one-step updates, so the performance improvement observed with deeper searches is not due to the use of multi-step updates as such. Instead, it is due to the focus and concentration of updates on states and actions immediately downstream from the current state. Rollout algorithms estimate action values only for each current state and for a given policy, usually called the rollout policy. Using Monte Carlo returns from simulated trajectories, make immediate use of these action value estimates, then discard them. Their aim is to improve upon the rollout policy, not to find an optimal policy, and they can be surprisingly effective, as in backgammon, where Tesoro and Galperin, 1997, were surprised by the dramatic improvements in backgammon playing ability produced by the rollout method, and Abramson's expected outcome model, even with random play, was a powerful heuristic that is precise, accurate, easily estimable, efficiently calculable, and domain-independent. The trade-offs are practical. Better rollout policies typically mean that more time is needed to simulate enough trajectories, so balancing these factors is important, with remedies including parallel trials, truncat and G. The simulated trajectory short of complete episodes, correcting the truncated returns by means of a stored evaluation function, and pruning candidate actions that are unlikely to turn out to be the best. They are not ordinarily learning algorithms in the book's sense. They do not maintain long-term memories of values or policies, yet they take advantage of some of the features of reinforcement learning that we have emphasized, avoiding exhaustive sweeps by trajectory sampling, relying on sample rather than expected updates, and exploiting the policy improvement property. Monte Carlo Tree Search, MCTS, largely responsible for the improvement in computer Go from a weak amateur level in 2005 to a grandmaster level in 2015, and critical to AlphaGo's 2016 victory, is at its base a rollout algorithm, enhanced by the addition of a means for accumulating value estimates. Each execution is an iterative process that simulates many trajectories starting from the current state and running to a terminal state, and its core idea is to successively focus multiple simulations starting at the current state by extending the initial portions of trajectories that have received high evaluations from earlier simulations. Each iteration has 4 steps. Selection. A tree policy based on stored action values traverses the tree to select a leaf node. Expansion. The tree is expanded from the selected leaf node by adding one or more child nodes reached via unexplored actions. Simulation. Simulation of a complete episode is run with actions selected by the rollout policy. And backup. The return generated by the simulated episode is backed up to update the action values attached to the edges of the tree. Traversed by the tree policy. MCTS thereby effectively grows a lookup table to store a partial action value function, with memory allocated to the estimated values of state action pairs visited in the initial segments of high-yielding sample trajectories. Avoid ing. The problem of globally approximating an action value function while it retains the benefit of using past experience to guide exploration. Summary of Part 1. Dimensions. The book pauses at the close of Part 1 to name the dimensions along which every tabular learning and planning method varies. One-step updates vary primarily along 3 binary dimensions: state versus action values, whether they estimate the value for the policy being followed, on policy, or the value of the optimal policy, off policy, and whether the update is an expected update based on the distribution of all possible next states or a sample update based on a single sample next state. A 4th axis crosses the boundary between learning and planning, whether the updates are done uniformly across the state space or focused by trajectory sampling according to the on-policy distribution. The passage forward is then announced in the book's own voice. In the second part of the book, we extend the tabular methods to apply to problems with arbitrarily large state spaces, where we cannot expect to find an optimal policy or the optimal value function even in the limit of infinite time and data. Our goal instead is to find a good approximate solution using limited computational resources. The promise that the same family of update and backup operations will survive the move from tables to parametric function approximation is the hinge on which the whole text turns. Quote, although there are real differences between these 2 kinds of methods, there are also great similarities. In particular, the heart of both kinds of methods is the computation of value functions. All the methods are based on looking ahead to future events, computing a backed-up value, and then using it as an update target for an approximate value function. Chapter 8 Opening. Quote, learning and planning are deeply integrated in the sense that they share almost all the same machinery, differing only in the source of their experience. Section 8.2. Quote, the agent is always reactive and always deliberative, responding instantly to the latest sensory information and yet always planning in the background. Section 8.2. Approximate Solution Methods. Chapter 9. On-Policy Prediction with Approximation. Value Function Approximation and the Prediction Objective. Part 2 begins by replacing the table with a parametric function, and with that replacement comes the first explicit statement of a prediction objective. In this chapter, we begin our study of function approximation in reinforcement learning by considering its use in estimating the state value function from on-policy data. The approximate value function is represented not as a table, but as a parameterized functional form with weight vector w. For example, a linear function in features of the state. The function computed by a multi-layer artificial neural network, or a decision tree, where w is all the numbers defining the split points and leaf values. The defining property is that typically the number of weights, the dimensionality of w, is much less than the number of states, so changing one weight changes the estimated value of many states. Consequently, when a single state is updated, the change generalizes from that state to affect the values of many other states. Such generalization makes the learning potentially more powerful, but also potentially more difficult to manage and understand. The chapter establishes a deep structural identity. Every prediction update can be viewed as a training example. Each update has the form S arrow. Are you, state S updated and you the update target? So, it is natural to interpret each update as specifying an example of the desired input-output behavior of the value function. The table simply shifted an entry toward its target. Now we permit arbitrarily complex and sophisticated methods to implement the update, and machine learning methods that learn to mimic input-output examples in this way are called supervised learning methods. In principle, we can use any method for supervised learning from examples, but not all suit reinforcement learning. The most sophisticated artificial neural network and statistical methods all assume a static training set over which multiple passes are made, whereas reinforcement learning requires methods that are able to learn efficiently from incrementally acquired data and to handle non-stationary target functions. As in GPI, where we often seek to learn Q star while pi changes, and even with a fixed policy, the target values of training examples are non-stationary if they are generated by bootstrapping methods. A second identity follows. Function approximation also makes it applicable to partially observable problems. If the parameterized function form for V does not allow the estimated value to depend on certain aspects of the state, then it is just as if those aspects are unobservable. So all the theoretical results for methods using function approximation presented in this part of the book apply equally well to cases of partial observability, though approximation cannot augment the state representation with memories of past observations. With approximation comes the obligation the tabular case never faced. By assumption, we have far more states than weights. So making one state's estimate more accurate invariably means making others less accurate. We are obligated then to say which states we care most about. The chapter specifies a state distribution mu of S, representing how much we care about the error in each state S, and defines the mean square value error. VE of W equals the sum over S mu of SV sub pi of S minus hat of V SW to the second. Under on-policy training, often μs is chosen to be the fraction of time spent in S, the on-policy distribution, the stationary distribution under pi in continuing tasks, and in episodic tasks, a delicate quantity computed from starting state and visit count equations, with discounting treated as a form of termination. The book is candid that it is not completely clear that the VE is the right performance objective. Our ultimate purpose is to find a better policy, and the best value function for this purpose is not necessarily the best for minimizing V, but it is not yet clear what a more useful alternative goal for value prediction might be. For now, we will focus on V, stochastic gradient, and semi-gradient methods. The workhorse of approximation learning is stochastic gradient descent, and bootstrapping needs a subtle, half-corrected variant. For a gradient Monte Carlo method, each update shifts the weights in proportion to a negative gradient of the squared error, yielding a step proportional to the gradient of the value estimate times the return error G sub t minus hat of Vs sub t W sub t. The chapter explains why the step is only a small step in the direction of the gradient. We do not seek or expect to find a value function that has zero error for all states, but only an approximation that balances the errors in different states. If we completely corrected each example in one step, then we would not find such a balance. Because the Monte Carlo target GT does not depend on WT, the gradient Monte Carlo method is a true stochastic gradient, and if the target output UT is an unbiased estimate, which GT is by definition, then the generalist GD method is guaranteed to converge to a local optimum under the usual stochastic approximation conditions for decreasing alpha. Thus, the gradient descent version of Monte Carlo state value prediction is guaranteed to find a locally optimal solution. The same cannot be said for bootstrapping. Semi-gradient TD, 0 uses the same gradient but with target r sub t plus 1 plus gamma hat of vs sub t plus 1 w. W sub t plus 1 equals w sub t plus alpha r sub t plus 1 plus gamma hat of vs sub t plus 1 w sub t minus hat of vs sub t w sub t nabla hat of vs sub t w sub t. In the TD0 update, the weight vector appears in the update target. Yet this is not taken into account in computing the gradient. So the update is not a true gradient with respect to any objective, hence the name semi-gradient. The chapter locates the failure precisely. The key step from 9.4 to 9.5 relies on the target being independent of WT, and bootstrapping targets such as n-step returns GT, T plus N, or the DP target, all depend on the current value of the weight vector WT, which implies that they will be biased. A bootstrapping method takes into account the effect of changing the weight vector WT on the estimate but ignores its effect on the target. They include only a part of the gradient. The ledger of advantages is drawn nonetheless. Semi-gradient methods typically enable significantly faster learning, as we have seen in chapters 6 and 7, and they enable learning to be continual and online without waiting for the end of an episode, which enables them to be used on continuing problems and provides computational advantages. The chapter's 1000 state random walk example with state aggregation, the simplest approximation, one estimated value, one component of the weight vector W, for each group, shows the consequence in a concrete setting. Episodes begin in state 500, and state transitions are from the current state to one of the 100 neighboring states to its left, or to one of the 100 neighboring states to its right, all with equal probability. Semi-gradient TD was a worse approximator than Monte Carlo asymptotically. It converges to a different value, the TD fixed point, which is not the minimum of the V, yet even so it continued to learn throughout, and its consequence was much faster learning. The example also makes the weights of state importance visible. State 500, the episode start, is rarely visited again, yet receives about 1.37% of the time steps. And the most visible effect of the distribution is that the leftmost group's values are clearly shifted higher than the unweighted average of the true values, biased toward the true value of state 100, which is higher than the true value of state 1, because state 100 is weighted more than 3 times more strongly than state 1. The distribution matters, and it shows in the learned approximate. Semi-gradient TD, 0, is a special case of n-step semi-gradient TD, whose general update shifts weights by alpha g sub t, t plus n minus hat of vs sub tw sub t plus n, 1 nabla hat of vs sub tw sub t plus n, 1 using the n-step return. The same 1000 state random walk, done with state aggregation and n-step methods, produces results strikingly similar to those with tabular representations, the classic U-shaped error curves within, confirming that the bootstrapping parameter, not the representation, sets the bias variance trade-off. As the chapter's synthesis will put it, in practice, very high N results in very slow learning, and some degree of bootstrapping in infinity is usually preferable, just as we saw in comparisons of tabular TD and Monte Carlo methods in Chapter 6. Linear methods. Linear function approximation is the case where the theory is cleanest, and where most of this book's convergence guarantees live. If the approximate value is a linear function of the weight vector, with a feature vector x of s per state and hat of vsw equals w to the top x of s equals the sum over iw sub I x sub I of s, then the gradient, in the linear case, is simply xs, and the SGD update reduces to w sub t plus 1 equals w sub t plus alpha u sub t minus w sub t to the top x of s sub tx of s sub t. Because it is so simple, the linear SGD case is one of the most favorable for mathematical analysis. Almost all useful convergence results for learning systems of all kinds are for linear, or simpler, function approximation methods. Under linearity, there is a single global optimum. Any method that is guaranteed to converge to or near a local optimum is automatically guaranteed to converge to or near the global optimum. and even semi-gradient TD, 0, converges to its own TD fixed point, not the VE optimum. The formal proof is given in a box, built on the observation that the expectation of the update depends on a matrix A equals EX sub TX sub T minus gamma X sub T plus 1 top, whose positive definiteness can be established from the structure X to the top D of I minus gamma Px using the stationary distribution. Positive definiteness is assured if all of its columns sum to a non-negative number. The proof's intuition is developed on a diagonal special case. If any of the diagonal elements are negative, then the corresponding diagonal element of I minus alpha A will be greater than 1, and the corresponding component of Wt will be amplified, which will lead to divergence if continued. While with all diagonal elements positive, the first term of the update tends to shrink Wt, and stability is assured. The asymptotic error of linear TD euro is bounded within a finite multiple of the minimal error achieved by Monte Carlo methods, with the bound tightening as bootstrapping weakens and grows, and the semi-gradient method's virtues are conserved. They need only big O of decomputation per step are guaranteed to converge under standard conditions, and in practice work well when provided with appropriate features. Feature construction for linear methods. With linear methods, choosing features is the art. Whether or not this is so depends critically on how the states are represented in terms of features. Choosing features appropriate to the task is an important way of adding prior domain knowledge to reinforcement learning systems, and the features should correspond to the aspects of a state space along which generalization may be appropriate. If we are valuing geometric objects, for example, we might want to have features for each possible shape, color, size, or function. The chapter states the defining limitation of a linear form with a vivid example. A limitation of the linear form is that it cannot take into account any interactions between features, such as the presence of feature I being good only in the absence of feature J. For example, in the pole balancing task, high angular velocity can be either good or bad depending on the angle. If the angle is high, then high angular velocity means an imminent danger of falling, a bad state, whereas if the angle is low, then high angular velocity means the pole is righting itself, a good state. A linear value function could not represent this if its features coded separately for the angle and the angular velocity. It needs instead, or in addition, features for combinations of these two underlying state dimensions. The families that follow, polynomials, the Fourier basis coarse coding, tile coding, and radial basis functions, are precisely a variety of general ways of doing this. The chapter surveys the families. Polynomials are one of the simplest families introduced pedagogically. To capture interactions between two state dimensions, one uses features like x of s equals 1s sub 1s sub 2s sub 1s sub 2 top, with the initial one allowing affine functions and the product enable the interactions to be taken into account. But the number of order n polynomial features grows exponentially with the dimension k, and we do not recommend using polynomials for online learning. Fourier bases express features as cosines over the state dimensions. X sub I of s equals cos of pi s to the top c sub I, with each integer vector c sub I setting the frequency along each dimension. 0 and c means the feature is constant along that state dimension, and non-zero components represent an interaction between the two state variables. The Fourier basis can perform well in a range of reinforcement learning problems, with per-feature step sizes, though it has trouble with discontinuities. Ringing and its features being global can make it difficult to find good ways to represent local properties. Coarse coding represents a continuous state by overlapping receptive fields, e.g. circles, that produce binary features. Generalization from state S to state S depends on the number of their features whose receptive fields overlap. The insight is that generalization breadth is set by field size and shape, but acuity, the finest discrimination ultimately possible, is controlled more by the total number of features. So features with large receptive fields give broad generalization without necessarily limiting final discrimination. Tile coding is coarse coding with tilings of a state space by overlapping grids. Tiles, particularly computationally efficient and flexible, and generalization across dimensions can be made asymmetric so that generalization occurs primarily across one dimension. Hashing of tiles to a fixed memory frees us from the curse of dimensionality in the sense that memory requirements need not be exponential in the number of dimensions. Radial basis functions generalize coarse coding to continuous features with Gaussian responses, product and approximate functions that vary smoothly and are differentiable. Though in most cases this has no practical significance and the extra complexity can hurt above 2 dimensions. Selecting step size parameters manually. The step size is a practical craft, and the chapter admits as much. Theoretical considerations are unfortunately of little help. The stochastic approximation conditions tend to result in learning that is too slow, and the classical choice alpha t equals 1/t is not appropriate for TD methods, for non-stationary problems, or for any method using function approximation. The chapter offers intuition from the tabular case. A step size of alpha equals 1/tau would take about tau experiences to converge approximately to their mean target, and a rule of thumb for linear SGD. Alpha equals tau ex to the top x minus 1. Suppose you wanted to learn in about tau experiences with substantially the same feature vector. The rule works best if the feature vectors do not vary greatly in length. The discussion also notes that optimal matrix step sizes exist, recursive least squares, extending to LSDD, but these require d superscript 2 step size parameters. For this reason, we rule them out for use on large problems. Nonlinear function approximation, artificial neural networks. ANNs, including the deep networks behind modern systems, are nonlinear function approximators trained with variations of SGD and backpropagation. The chapter introduces feed-forward networks with input, output, and hidden layers. Real value connection weights roughly correspond ing to the efficacy of a synaptic connection, and semilinear units computing a weighted sum followed by a nonlinear activation function, sigmoid, logistic, ReLU, or a thresholding step. The universal approximation fact is stated. An ANN with a single hidden layer containing a large enough finite number of sigmoid units can approximate any continuous function on a compact region of the network's input space. But nonlinearity is essential. Training proceeds by backpropagation, the chain rule applied to the network gradient, and the gradient in this equation can be computed efficiently by the backpropagation procedure. The book places the field in its history. The introduction of the threshold logic unit as an abstract model neuron by McCulloch and Pitts, 1943, was the beginning of ANNs, followed by roughly the perceptron, Rosenblatt, 1962, and Adeline, adaptive linear element. Widrow and Hoff, 1960, single-layer stage. The error backpropagation stage, LeCun, 1985. Rumelhart, Hinton, and Williams, 1986. Of learning by multi-layer ANNs, and the current deep learning stage with its emphasis on representation learning. The book also records the long history of ANNs inside reinforcement learning. Bartow, Anderson, and Sutton, 1982, used a 2-layer ANN to learn a nonlinear control policy, and Bartow, Sutton, and Anderson, 1983, presented an actor-critic algorithm in the form of an ANN learning to balance a simulated pole, so that nonlinear methods have become very popular in recent years under the name deep reinforcement learning, a theme the case study chapter will develop. Least squares TD, memory-based, and kernel-based approximation. The chapter closes the toolkit with data-efficient and non-parametric alternatives. Least squares TD, LSTD, derives its name from estimating the least squares solution to the linear TD fixed-point equations, a batch method maintaining an estimated inverse matrix updated via the Sherman-Morrison formula at only big O of D to the second per step rather than forming full outer products. LSTD is the most data-efficient linear TD prediction method, but D superscript 2 is still significantly more expensive than the OD of semi-gradient TD, and its lack of a step size parameter means that it never forgets which is problematic if the target policy pi changes. If epsilon is chosen too small, the sequence of inverses can vary wildly. And if epsilon is chosen too large, then learning is slowed. So, in control applications, LSTD typically has to be combined with some other mechanism to induce. Mooting any initial advantage of not requiring a step size parameter. Memory-based or lazy methods simply save training examples in memory as they arrive, without updating any parameters, then compute value estimates for query states on demand. Nearest neighbor, weighted averaging, and locally weighted regression being the natural instances. These are prime examples of non-parametric methods, their form determined by the training examples themselves. Their advantages echo earlier themes. Memory-based methods allow an agent's experience to have a relatively immediate effect on value estimates in the neighborhood of the current state, and avoiding global approximation is also a way to address the curse of dimensionality. Storage linear in examples. Nothing exponential. The open question is speed of nearest neighbor search, addressed with data structures like KD trees and with forgetting rules. Kernel-based approximation generalizes the weighting idea. A kernel K of S numerically express S how relevant knowledge about any state is to any other state, and the strength of generalization resulting from linear parametric function approximation can always be described by a kernel function. So tile coding's generalization pattern, Fourier features, and kernel regression all live in one conceptual frame. The unifying insight is quiet but far-reaching. Whether one thinks in features with associated weights or in stored examples with associated kernels, any of a broad range of existing methods for supervised learning function approximation can be used simply by treating each update as a training example. The distinction between the two families is one of representational commitment, a fixed parametric class versus a growing database, rather than of underlying principle, and the choice between them is governed by the same currency of data efficiency versus computational cost that runs throughout the chapter. Looking deeper, interest and emphasis. A final refinement generalizes the notion of the on-policy distribution itself, so that approximation resources can be spent where they matter. Function approximation resources are always limited, and if they were used in a more targeted way, then performance could be improved. In discounted episodic problems, we may be more interested in accurately valuing early states in the episode than in later states, where discounting may have made the rewards much less important to the value of the start state. For an action value function, it may be less important to accurately value poor actions whose value is much less than the greedy action. Two new quantities implement the targeting. The interest I sub t is a non-negative scalar measure, indicating the degree to which we're interested in accurately valuing the state, or state, action pair, at time t. If we don't care at all about the state, then the interest should be 0. The state distribution mu in the VE is then defined as the distribution of states encountered while following the target policy, weighted by the interest. The emphasis m sub t is another non-negative scalar random variable, multiplies the learning update, and thus emphasizes or de-emphasizes the learning done at time t, determined recursively from the interest by m sub t equals I sub t plus gamma to the nm sub t1. The chapter's example 9.4 shows why this matters. In a four-state Markov reward process where episodes start on the left and transition one state right with reward plus 1 each step, the true values are 4, 3, 2, 1, but the parameterization ties the first two states to one shared weight and the last two to another, so the estimated values must be the same even though their true values are different. Suppose we are interested in accurately valuing only the leftmost state. Interest 1 there, 0 elsewhere. The standard gradient Monte Carlo algorithm will converge to the parameter vector W equals 3.5, 1.5, which balances error across all four states. The interest and emphasis version instead drives the shared first weight toward the true value of the state that matters for, spending the approximation resource where the designer actually cares. The point is not that one choice is universally right, but that the VE objective was silently treating all states as equally important, and that a family of on-policy distributions, all of them a distribution of states encountered in trajectories while following the target policy, differ only in how the trajectories are, in a sense, initiated. The summary then consolidates the chapter. The VE gives us a clear way to rank different value function approximations in the on-policy case. The most popular methods are variations of stochastic gradient descent. Gradient Monte Carlo is a true gradient, while semi-gradient TD methods are not true gradient methods, yet converge well in the linear case. Linear semi-gradient in-step TD is guaranteed to converge under standard conditions for all n to a VE that is within a bound of the optimal error, always tighter for higher n, though in practice very high n results in very slow learning, and some degree of bootstrapping in infinity is usually preferable. The same lesson the tabular chapters taught, now standing on linear function approximation ground. Quote, by assumption we have far more states than weights, so making one state's estimate more accurate invariably means making others less accurate. We are obligated then to say which states we care most about. Section 9.2. Quote, in the TD0 update, the weight vector appears in the update target, yet this is not taken into account in computing the gradient. Thus, they are semi-gradient methods. As such, they cannot rely on classical SGD results. Section 9.3/summary. Quote, generalization from one point to another is indeed controlled by the size and shape of the receptive fields, but acuity, the finest discrimination ultimately possible, is controlled more by the total number of features. Section 9.5.3. Chapter 10. On Policy Control with Approximation. Episodic Semi-Gradient Control. The chapter extends function approximation from prediction to control, beginning in the episodic case where the move is natural. In this chapter we return to the control problem, now with parametric approximation of the action value function Q, S, A, W, continuing to restrict attention to the on-policy case and featuring the semi-gradient Sursa algorithm, the natural extension of semi-gradient TD0 to action values and to on-policy control. The extension of prediction to action values is straightforward. The training examples become state. Action pairs S sub T, A sub T arrow, are U sub T, with the update target UT. Any approximation of Q star is T at, including the usual backed up values, the full Monte Carlo return, or any of the in-step Sursa returns, and the general gradient descent update becomes W sub T plus 1 equals W sub T plus alpha U sub T minus hat of QS sub T, sub TW sub T nabla hat of QS sub T, sub TW sub T. For the one-step Sursa method, this yields episodic semi-gradient one-step Sursa, which for a constant policy converges in the same way that TD0 does with the same kind of error bound. Coupling with policy improvement, however, requires care. Suitable techniques applicable to continuous actions or to actions from large discrete sets are a topic of ongoing research with as yet no clear resolution. While if the action set is discrete and not too large, the machinery of previous chapters still works. Compute hat of QS sub T plus 1AW for each action, take the greedy action, and use an epsilon greedy soft approximation for improvement and selection. The chapter's touchstone task is the mountain car, a simple example of a continuous control task where things have to get worse in a sense, farther from the goal, before they can get better, and many control methodologies have great difficulties with tasks of this kind unless explicitly aided by a human designer. The car is underpowered. The only solution is to first move away from the goal and up the opposite slope on the left, build up inertia, and then cross. Learned on two continuous state variables with tile coding and linear function approximation, semi-gradient Sursa learns to drive up the far slope and over the goal in about 9,000 episodes, with the learned cost-to-go function clearly displaying the dual actions of retreat and ascent. Semi-gradient in-step Sursa. The same in-step logic that helped the tabular case extends with little change. The chapter's in-step return for the semi-gradient case is the natural generalization of the tabular one. replacing the final table approximation with a parameterized action value function. And performance is best if an intermediate level of bootstrapping is used, corresponding to an n larger than 1. On the mountain car task, this algorithm tends to learn faster and obtain a better asymptotic performance at n equals 8 than at n equals 1. And in the parameter study, as usual, an intermediate level of bootstrapping, n equals 4, performed best. The empirical fidelity to the tabular pattern is itself a thesis. The bias, variance trade-off in bootstrapping depth survives the move to tiles and weights. Average reward, a new problem setting for continuing tasks. The chapter's substantive surprise. With genuine function approximation, the discounted formulation must be left behind for a new average reward setting. We now introduce a third classical setting alongside the episodic and discounted settings. Like discounting, average reward applies to continuing problems, but there's no discounting. The agent cares just as much about delayed rewards as it does about immediate reward. The quality of a policy is its average rate of reward. R of pi equals lim t minus is greater than 001 over t. The sum over I equals 1 ton E R sub I. Defined in the limit under the steady-state distribution, assuming ergodicity, where the starting state and any early decision can have only a temporary effect. Returns are then defined in terms of differences between rewards and the average reward. The differential return and the corresponding differential value functions satisfy Bellman equations that are exactly the old ones, with all the gamma s removed and all rewards replaced by the difference between the reward and the true average reward. The average reward bar of RT is itself adapted online by a TD-like rule. The work case is an access control queuing task in which customers of 4 priorities arrive at a queue of 10 servers, and the agent must accept or reject the head-of-line customer to maximize long-term, undiscounted reward. Differential semi-gradient SURSA recovers the natural policy. Accept high-priority customers whenever a server is free. Deprecating the discounted setting. The chapter's argument for the new setting is conceptual and blunt. It is questionable whether one should ever use this problem formulation in the approximate case. To see why, consider an infinite sequence of returns with no beginning or end, and no clearly identified states. In the extreme, all of the feature vectors may be the same, leaving only the reward sequence and the actions. The only sensible assessment is averaging. Discounting, applied and averaged, turns out to be redundant. The average of the discounted returns is proportional to the average reward. In fact, for policy pi, the average of the discounted returns is always R pi /1 minus gamma, so the discount rate gamma thus has no effect on the problem formulation. The ordering of all policies in the average discounted return setting would be exactly the same as in the average reward setting. The symmetry argument shows why. Each time step is exactly the same as every other, and the TTH reward will appear undiscounted in the TTH return, discounted once in the second return, and discounted 999 times in the T plus 1000 TH return, with the total weight 1 plus gamma to the second plus dots. C equals 1 over 1 minus gamma common to all states. The deeper diagnosis follows. The root cause of the difficulties with the discounted control setting is that with function approximation, we have lost the policy improvement theorem. It is no longer true that if we change the policy to improve the discounted value of one state, then we are guaranteed to have improved the overall policy in any useful sense. And that guarantee was key to the theory of our reinforcement learning control methods. The authors nevertheless allow a constructive rereading. The discounting parameter gamma changes from a problem parameter to a solution method parameter, though discounting algorithms with function approximation do not optimize discounted value over the on-policy distribution, and thus are not guaranteed to optimize average reward. This is one of the book's most consequential and least advertised claims. Differential semi-gradient in-step SURSA. The new setting needs its own algorithms, and they parallel the old ones closely. The differential in-step return subtracts the estimated average reward from each reward term, G sub t, t plus n equals the sum over I r sub I minus bar of r plus v to the approximate, after which we can apply our usual semi-gradient Sursa update. The summary states the ledger plainly. Surprisingly, the discounted formulation cannot be carried over to control in the presence of approximations. In the approximate case, most policies cannot be represented by a value function. The arbitrary policies that remain need to be ranked, and the scalar average reward R, pi, provides an effective way to do this. The cost is modest. The average reward formulation involves new differential versions of value functions, Bellman equations, and TD errors, but all of these parallel the old ones, and the conceptual changes are small. Quote, surprisingly, once we have genuine function approximation, we have to give up discounting and switch to a new average reward formulation of a control problem with new differential value functions. Chapter 10 opening. Quote, the root cause of the difficulties with the discounted control setting is that with function approximation, we have lost the policy improvement theorem. Section 10.4. Quote, the discounting parameter gamma changes from a problem parameter to a solution method parameter. Section 10.4. Chapter 11. Off-policy methods with approximation. Semi-gradient methods and the danger of divergence. The chapter turns to off-policy learning with function approximation, and its first sentence sets the tone. The extension turns out to be significantly different and harder than for on-policy learning. The tabular off-policy method developed in chapters 6 and 7 readily extend to semi-gradient algorithms, but these algorithms do not converge as robustly as they do under on-policy training. The challenge can be divided into two parts. One about the target of the update, handled by the important sampling techniques of chapters 5 and 7, which may increase variance but are needed in all successful algorithms, and one that arises only with function approximation, about the distribution of the updates. The semi-gradient off-policy methods address only the first part. Accordingly, these methods may diverge in some cases, and in that sense are not sound, but still they are often successfully used. The chapter catalogs the semi-gradient extensions, semi-gradient off-policy TD, 0, with the per-step importance sampling ratio rho sub t, semi-gradient expected Sursa, which does not use importance sampling in the one-step case, because the only sample action is at the n-step versions with ratio weighting and the semi-gradient tree backup algorithm that does not involve importance sampling at all. The leading warning is stated cleanly. These methods are simple and thus a good place to start, but also the first part of the challenge of off-policy learning, changing the update targets, but not the second part, changing the update distribution. Examples of off-policy divergence. The chapter earns its caution with counterexamples, beginning with the simplest possible one. Suppose, perhaps as part of a larger MDP, there are two states whose estimated values are of the functional form W and 2W, connected by a deterministic transition with reward 0. Suppose initially W equals 10. The transition will then be from a state of estimated value 10 to a state of estimated value 20. It will look like a good transition, and the update raises W, but the second state's estimated value will also be increased, so if the transition occurs again, then it will be from a state of estimated value larger, not smaller than before, and with further updates W will diverge. The mechanism is made vivid in the author's own imagery. Key to this example is that the one transition occurs repeatedly without W being updated on other transitions, which is possible off-policy because the behavior policy might select actions on those other transitions which the target policy never would, where ρt would be 0 and no update would be made. Under on-policy training, the promise balances. Each state can support the one before only by creating a higher expectation. Eventually, the piper must be paid. But off-policy, a promise can be made and then, after taking an action that the target policy never would, forgotten and forgiven. The complete example is Baird's counterexample, an episodic 7-state, 2-action MDP whose behavior policy makes the next state distribution uniform, while the target policy always takes the solid action, so the on-policy distribution for pi is concentrated in the 7th state. With 0 rewards and gamma equals 0.99, the linear semi-gradient method diverges. Stability does not depend on the specific step size, as long as alpha 0. A second counterexample, the W to 2W variant with a terminal state, shows that linear function approximation would not work with dp even if the least square solution was found at each step. And the chapter notes the one safety valve. Stability is guaranteed for function approximation methods that do not extrapolate from the observed targets. Averagers like nearest neighbor and locally weighted regression, but not popular methods such as tile coding and artificial neural networks. The deadly triad. The counterexamples distill into a named doctrine, the deadly triad. The danger of instability and divergence arises whenever we combine all of the following three elements. Function approximation, a powerful, scalable way of generalizing from a state space, much larger than the memory and computational resources. Bootstrapping, update targets that include existing estimates, rather than relying exclusively on actual rewards and complete returns. And off-policy training, training on a distribution of transitions other than that produced by the target. Policy. Two nuances matter. The danger is not due to control or to generalized policy iteration, appearing in the simpler prediction case whenever it includes all three elements. And the danger is also not due to learning or to uncertainties about the environment, because it occurs just as strongly in planning methods, such as dynamic programming. The chapter then walks through each element asking which can be given up. Function approximation most clearly cannot be given up. State aggregation or non-parametric methods are too weak or too expensive, and least squares methods are of quadratic complexity. Bootstrapping can be abandoned at the cost of computational and data efficiency, but the losses are real. Monte Carlo, non-bootstrapping, methods require memory to save everything that happens between making each prediction and obtaining the final return, whereas with bootstrapping and eligibility traces, data can be dealt with when and where it is generated, and bootstrapping allows learning to take advantage of the state property, the ability to recognize a state upon returning to it. Repeatedly shown to speed learning on the random walk in mountain car tasks. The chapter is balanced even here, noting that bootstrapping can impair learning on problems where the state representation is poor and causes poor generalization, e.g., this seems to be the case on Tetris, and that a poor state representation can also result in bias. Yet on balance, the ability to bootstrap has to be considered extremely valuable. It is an ability that we would very much like to keep in our toolkit. Off-policy learning, the third element, could be considered an appealing convenience, but not a necessity for a single learner. Yet off-policy learning is essential to learning large numbers of value functions and predictions in parallel from one stream of experience, a capability important to the larger goal of creating a powerful, intelligent agent. The chapter cites the evidence for such parallel prediction in ordinary cognition. We can be surprised by unusual events and correct our predictions about them, even if they are of neutral valence, because we predict what we will see after our movements, how long it will take to walk home, the probability of making a jump shot in basketball. The triad cannot be dodged. The chapter's second half develops algorithms that survive it. Linear value function geometry and gradient descent in the Bellman error. The chapter develops a geometric picture of approximation to understand what stability requires. To better understand the stability challenge of off-policy learning, it is helpful to think about value function approximation more abstractly and independently of how learning is done. We can imagine the space of all possible state value functions, all functions from states to real numbers v, SR, each corresponding to a vector listing the value of each state in order. Most of these value functions do not correspond to any policy, and more important for our purposes is that most are not representable by the function approximator, which by design has far fewer parameters than there are states. The illustrative case is 3 states and 2 parameters. We can then view all value functions slash vectors as points in a 3-dimensional space. The parameters provide an alternative coordinate system over a 2-dimensional subspace. In the case of linear value function approximation, the subspace is a simple plane with a true value function v sub pi, too complex to be represented exactly, depicted as being above the planar subspace. Given this picture, what representable value function is closest to it? This turns out to be a subtle question with multiple answers. The chapter uses a weighted norm v mu to the second equals the sum over s mu of sv of s to the second, of which the v is a special case, and the operation of finding its closest value function in the subspace of representable value functions is a projection operation. The representable value function that is closest to the true value function is thus its projection, which is the solution asymptotically found by Monte Carlo methods. The Bellman operator b sub pi, applied to an approximate value function, will, in general, produce a new value function that is outside the subspace, and the Bellman error vector measures how far the approximation is from satisfying the Bellman equation. Its size is the mean square Bellman error, b. In dynamic programming, without function approximation, this operator is applied repeatedly to the points outside the representable space. Eventually, that process converges to the true value function. With function approximation, the gray arrows cannot be followed because after the first update, the value function must be projected back into something representable. So the relevant quantity becomes the projected Bellman error, p to the size of this vector in the norm. With linear function approximation, there always exists an approximate value function. With 0 pb, this is the TD fixed point, WTD. The natural next attempt, gradient descent in the Bellman error, is dissected and found wanting. The naive residual gradient algorithm minimizes the TD, mean square TD error, and the A-split example shows the failure. A tabular MDP where the true values are exactly representable, yet the naive residual gradient algorithm finds different values, and these values have lower TD than do the true values. Minimizing the TD is naive. By penalizing all TD errors, it achieves something more like temporal smoothing than accurate prediction. The proper residual gradient algorithm is guaranteed to converge to a minimum of the b, a true SGD method applying to linear and nonlinear approximators alike, but it is empirically slow, and worse, it can converge to the wrong values. The A-split example shows that minimizing the b, which the residual gradient algorithm surely does, may not be a desirable goal. Because on problems where distinct underlying states share a feature, the b objective itself picks out the wrong solution. The Bellman error is not learnable. The chapter's most striking conceptual result is a notion of learnability with teeth. The Bellman error cannot be estimated from data. The concept of learnability that we introduce in this section is different from that commonly used in machine learning, not a polynomial sample bound, but the more basic question of whether the objective is literally not a function of the data. In very simple, PUM-like examples, the observable data produced by two different MDPs is identical in every respect, yet the B is different. Two Markov chains generate identical data sequences, single occurrences of a followed by a 0, then some number of apparent BS, each followed by a -1 except the last, which is followed by a 1. Then we start all over again. While one has two distinct states and the other three, with B and B sharing feature, and in both MRPs, the probability of a string of KBS is 2 to the -k. For one, the solution W equals 0 is an exact solution, and the B is 0. For the other, this solution produces a squared error in both B and B, so the two MRPs have different Bs. The B is not learnable. The chapter sharpens exactly how this failure differs from the VEs. The B is like the VE in that it can be computed from knowledge of the MDP, but is not learnable from data. But it is not like the VE in that its minimum solution is not learnable. For the two MRPs, the minimizing value of W is different, so the solution that minimizes B cannot be estimated from data alone. In this sense, it is impossible in principle to pursue the B as an objective for learning. The saving grace is tucked into the same analysis. Although the VE itself is not learnable from the data distribution, all such VEs must have the same optimal parameter vector W** operator, and this same W** operator can be determined from another objective, the RE, return error, whose relationship to the V is the same except for a variance term that does not depend on the parameter vector. So the two objectives must therefore have the same optimal parameter value. Thus, W** operator and the RE are learnable even though the VEs are not, and the PBE and TD objectives and their minima can be directly determined from data, and thus are learnable. All this directs more attention toward the PBE. Gradient TD methods. The first family of stable off-policy algorithms descends from the learnable PBE. The chapter derives gradient TD methods, GT2 and TDC, TD, 0, with gradient correction, which estimate a direction for stochastic gradient descent on the PBE using two learning processes and big O of decomputation. The key algebraic move is to rewrite the PBE gradient in terms of an unknown vector V that is a solution to a linear least squares problem that tries to approximate delta t from the features, and then use the standard SGD method, known as the least mean square LMS rule, here augmented with an important sampling ratio, to estimate that secondary vector width. Big O of D storage and per step computation. Given a stored estimate VT approximating, we can update our main parameter, vector WT, using SGD methods. This algorithm is called GT2. Note that if the final inner product is done first, then the entire algorithm is of OD complexity. A slightly better version does a few more analytic steps before substituting in VT, yielding TDC, known as either TD, 0, with gradient correction, TDC, or alternatively, as G0. On Baird's counterexample, TDC falls to 0 and the PB stability is achieved. Though the chapter is candid, the individual components of the parameter vector do not approach 0, and progress is extremely slow because the PBE is already so close to 0. The two processes form a cascade. GT2 and TDC both involve two learning processes, a primary one for W and a secondary one for V. The logic of the primary learning process relies on the secondary learning process having finished, at least approximately, whereas the secondary learning process proceeds without being influenced by the first, analyzed by two timescale proofs. The fast timescale is that of the secondary learning process, and the slower timescale is that of the primary learning process, with the step size of the primary learning process and the step size of the secondary learning process satisfying that in the limit beta/alpha 0. The chapter's summary of their standing is generous but honest. Gradient TD methods are currently the most well-understood and widely used stable off-policy methods, with extensions to control, GQ, eligibility traces, G to D, lambda, GQ, lambda, nonlinear approximation, and hybrid algorithms midway between semi-gradient TD and gradient TD that behave like gradient TD algorithms in states where the target and behavior policies are very different, and behave like semi-gradient algorithms in states where the target and behavior policies are the same. Emphatic TD methods. The second family restores stability by reweighting states back toward the on-policy distribution. Linear semi-gradient TD methods are efficient and stable when trained under the on-policy distribution. In off-policy learning, we reweight the state transitions using importance sampling, but the state distribution is still that of the behavior policy. There is a mismatch. A natural idea is to somehow reweight the states, so as to return the distribution of updates to the on-policy distribution. This is the idea of emphatic TD methods, introduced for on-policy training in Section 9.11. A subtlety in that program, the notion of the on-policy distribution is not quite right, as there are many on-policy distributions, and any one of these is sufficient to guarantee stability however the episodes start. If all state transitions are due to the target policy, then the state distribution that results is an on-policy distribution. So, you might start close to the terminal state and visit only a few states, or you might start far away and pass through many states before terminating, and training on both with a linear semi-gradient method would be guaranteed to be stable. Discounting, similarly, can be treated as partial or probabilistic termination, a general notion of pseudo-termination that does not affect the sequence of state transitions, but does affect the learning process and the quantities being learned. The one-step emphatic TD update multiplies the learning step by an emphasis m sub t that accumulates recursively from the interest function I sub t. M sub t equals gamma lambda I sub t plus 1 minus gamma lambda f sub t plus I sub t, with a follow-on trace f sub t. The chapter's report on the counterexample is unusually frank. How does this algorithm perform on Baird's counterexample? There are some oscillations, but eventually everything converges and the v goes to 0. But this is shown by iteratively computing the expectation without any of the variance due to sampling. We do not show the results of applying the emphatic TD algorithm directly because its variance on Baird's counterexample is so high that it is nigh impossible to get consistent results in computational experiments. The algorithm converges to the optimal solution in theory on this problem, but in practice it does not. The point generalizes the stability that reweighting buys is real but comes at a hard price in variance, and the chapter does not pretend otherwise. In the on-policy case, emphatic TD, lambda, is similar to conventional TD, lambda, but still significantly different, whereas emphatic TD, lambda, is guaranteed to converge for all state-dependent gamma functions. TD, lambda, is not. TD, lambda, is guaranteed convergent only for all constant target policy discounting. Reducing variance. The chapter closes with the practical problem that shadows every off-policy method: variance. Off-policy learning forces rewards and target values to be weighted by ratios that can be large or zero, and the resulting high variance forces a small step size parameter and slow learning. There are remedies, control variance, adaptive step sizes that rapidly adapt to the observed variance, invariant updates, and hybrid schemes that behave like gradient TD, where the target and behavior policies differ sharply, and like semi-gradient methods where they agree. But none dissolves the underlying difficulty because it is probably inevitable that off-policy training is slower than on-policy training. After all, the data is less relevant to what is being learned. The chapter's overall verdict is a model of scholarly candor. In the end, we will have improved methods, but the theoretical results will not be as strong, nor the empirical results as satisfying, as they are for on-policy learning. It is the one place in the book where the authors concede that their own frontier has not been fully crossed, and the concession is itself part of the book's method, separating what is established from what is hoped. Quote, "In the end, we will have improved methods, but the theoretical results will not be as strong, nor the empirical results as satisfying, as they are for on-policy learning. Along the way, we will gain a deeper understanding of approximation in reinforcement learning for on-policy learning as well as off-policy learning." Chapter 11 opening. Quote, "Eventually the piper must be paid. In the on-policy case, the promise of future reward must be kept, and the system is kept in check. But in the off-policy case, a promise can be made and then, after taking an action that the target policy never would, forgotten and forgiven." Section 11.2. Quote, "The danger of instability and divergence arises whenever we combine all of the following three elements, making up what we call the deadly triad: function approximation, bootstrapping, and off-policy training." Section 11.3. Chapter 12. Eligibility Traces. The lambda return. The chapter's subject is one of the basic mechanisms of reinforcement learning: eligibility traces, named in the very name of TD, lambda. Almost any temporal difference, TD, method, such as Q-learning or SURSA, can be combined with eligibility traces to obtain a more general method that may learn more efficiently. The scope claim is structural. Eligibility traces unify and generalize TD and Monte Carlo methods. When TD methods are augmented with eligibility traces, they produce a family of methods spanning a spectrum that has Monte Carlo methods at one end, lambda equals 1, and one-step TD methods at the other, lambda equals 0. In between are intermediate methods that are often better than either extreme method. They also provide a way of implementing Monte Carlo methods online and on continuing problems without episodes, a capability the earlier Monte Carlo chapter conspicuously lacked. The chapter distinguishes two views. The forward view is the intuitive one, Many algorithms are most naturally formulated and understood as an update of state's value based on events that follow that state over multiple future time steps, as Monte Carlo and in-step methods do. Forward views are always somewhat complex to implement because the update depends on later things that are not available at the time. The backward view achieves nearly the same updates, and sometimes exactly the same updates, with an algorithm that uses the current TD error, looking backward to recently visited states using an eligibility trace. The mechanism is precise. When a component of WT participates in producing an estimated value, then the corresponding component of ZT is bumped up and then begins to fade away. Learning will then occur in that component of WT if a non-zero TD error occurs before the trace falls back to 0, with the trace decay parameter lambda is an element of 0, 1, setting the fade rate. The primary computational advantage of eligibility traces over in-step methods is that only a single trace vector is required rather than a store of the last n feature vectors. The lambda return is the forward view target, built by averaging all n-step returns, each weighted proportionally to lambda to the n-1, normalized so the weights sum to 1. G sub t equals 1 minus lambda, the sum over n equals 100 lambda to the n, 1 g sub t, t plus n. Any set of n-step returns can be averaged in this way, even an infinite set, as long as the weights on the component returns are positive and sum to 1. And the resulting compound update possesses an error reduction property similar to that of individual n-step returns. At the extremes, the architecture is exact. For lambda equals 1, updating according to the lambda return is a Monte Carlo algorithm, and for lambda equals 0, the lambda return reduces to gt, t plus 1, a one-step TD method. The parameter's role can be characterized in terms of a time constant or half-life, rather than a rate. An exercise asks for the equation relating lambda and the half-life, tau, the time by which the weighting sequence will have fallen to half of its initial value. The chapter's first concrete algorithm is the offline lambda return algorithm. As an offline algorithm, it makes no changes to the weight vector during the episode. Then, at the end of the episode, a whole sequence of offline updates are made according to our usual semi-gradient rule, using the lambda return as the target. The chapter compares it directly with the in-step methods of Chapter 7 on the 19-state random walk. The experiment was just as described earlier, except that for the lambda return algorithm, we varied lambda instead of n, measuring the estimated root mean square error between the correct and estimated values of each state measured at the end of the episode. The lambda return, thus, gives us an alternative way of moving smoothly between Monte Carlo and one-step TD methods that can be compared with the in-step bootstrapping way developed in Chapter 7. And the two parameterizations trade off along the same bias, variance spectrum. After a terminal state is reached, all subsequent in-step returns are equal to the conventional return, gt, which is why the lambda return can be re-expressed as a weighted combination of the post-termination return terms, TD, lambda, and the mechanism of traces. The backward view is TD, lambda, proper, and it was the first algorithm for which a formal relationship was shown between a more theoretical forward view and a more computationally congenial backward view. With function approximation, the eligibility trace is a vector whose t is an element of r to the d with the same number of components as the weight vector, a short-term memory, typically lasting less time than the length of an episode, while the weight vector is a long-term memory, accumulating over the lifetime of the system. The trace update is z sub t equals gamma lambda z sub t, 1 plus nabla hata vs sub tw sub t, and the weight update is w sub t plus 1 equals w sub t plus alpha delta sub tz sub t. At each moment, we look at the current TD error and assign it backward to each prior state according to how much that state contributed to the current eligibility trace. The image of riding along the stream of states, computing TD errors, and shouting them back to the previously visited states. For lambda equals 0, the trace at t is exactly the value gradient corresponding to st, recovering one-step semi-gradient TD. This is why that algorithm was called TD0. For lambda equals 1 with gamma equals 1, the eligibility traces do not decay at all with time, yielding TD1, a way of implementing Monte Carlo algorithms that is more general than those presented earlier, applicable to discounted continuing tasks, incremental and online, and able to learn immediately and alter behavior. On that same episode, when something unusually good or bad happens during an episode, a decisive advantage over Monte Carlo methods that learn nothing from an episode until it is over. On the 19-state random walk, TD, lambda, and the offline lambda return algorithm performed virtually identically at low lambda, though TD, lambda, degrades more at high lambda, and the asymptotic error bound generalizes. The asymptotic error is no more than a factor of 1 minus lambda gamma over 1 minus gamma times the smallest possible error. In-step truncated lambda return methods and true online TD, lambda. The chapter pushes the forward view to its most refined form and then discovers an exact backward implementation. The online lambda return algorithm is fully online, determining a new weight vector WT each step, using only information available at time t. The chapter pictures its state as a triangle of weight vectors, one row produced on each time step, of which the weight vectors on the diagonal are the only ones really needed, with the first W00, the initial weight vector of the episode, the last WT, the final weight vector, and each weight vector along the way, playing a role in bootstrapping in the in-step returns of the updates. The method is computationally complex, passing over the portion of the episode experienced so far on every step. Nonetheless, it can be expected to perform better than the offline version, not only during the episode when it makes an update while the offline algorithm makes none, but also at the end of the episode because the weight vector used in bootstrapping has had a larger number of informative updates, and it is currently the best performing temporal difference algorithm. It is an ideal which online TD, lambda, only approximates. The chapter then asks the decisive question: is there a way to invert this forward view algorithm to produce an efficient backward view algorithm using eligibility traces? For linear function approximation, the answer is yes. True online TD, lambda, an exact computationally congenial implementation of the online lambda return algorithm, arrived at by finding a compact, efficient way of computing each WTT from the one before, which has been proven to produce exactly the same sequence of weight vectors as the online lambda return algorithm, while requiring the same memory as conventional TD, lambda. The memory requirements of true online TD, lambda, are identical to those of conventional TD, lambda. While the per step computation is increased by about 50%, there is one more inner product in the eligibility trace update, still OD. The chapter generalizes the tracing idea far beyond TD in a starred section, starting from an expensive Monte Carlo/least squares algorithm and using the same novel eligibility trace used in true online TD methods. One arrives at a cheap incremental non-TD algorithm. The notion of an eligibility trace, and the Dutch trace in particular, has arisen in a setting without temporal difference. TD learning. It seems eligibility traces are not specific to TD learning at all. They're more fundamental than that. The need for eligibility traces seems to arise whenever one tries to learn long-term predictions in an efficient manner. The parallel is genuine and surprising. An incremental reformulation of plain least squares Monte Carlo prediction demands exactly the mechanism that TD learning independently needed. Sursa, lambda, and Watkins Q, lambda, to tree backup, lambda. The same machinery extends to action values with only very few changes in the ideas already presented. Sursa, lambda, uses the action value form of the TD error and the eligibility trace Z sub t equals gamma lambda Z sub t. 1 plus nabla hat of QS sub t sub TW sub t, approximating the action value lambda return forward view. The grid world example shows the advantage over one-step and in-step methods. A one-step method would increment only the last action value, whereas an in-step method would equally increment the last in actions values and an eligibility trace method would update all the action values up to the beginning of the episode to different degrees, fading with recency. The fading strategy is often the best. Two trace variants matter in practice, and the pseudocode's update line makes the choice literal. Accumulating traces, z sub I arrow. El sav I plus jeden versus replacing traces, sav I arrow. L1, where the trace for the state and the actions not selected may also be set to 0, clearing in a further refinement. On the mountain car task, which uses the function approximation, action selection, and environmental details exactly as in Chapter 10, so that it is appropriate to numerically compare these results with the Chapter 10 results for in-step Sursa. The comparison is instructive. The earlier results varied the update length n, whereas here for Sursa, lambda, we vary the trace parameter lambda, which plays a similar role, and the fading trace bootstrapping strategy of Sursa, lambda, appears to result in more efficient learning on this problem. Moreover, true online Sursa, lambda, performed better than regular Sursa, lambda, with both accumulating and replacing traces. The chapter also presents the in-step truncated lambda return methods and the online variants. Watkins's Q, lambda, and the tree backup, lambda, family, complete the action value spectrum. Off-policy traces, control variates, and stable methods. The chapter extends traces to off-policy learning, confronting the two-part challenge of Chapter 11. Using per-step important sampling ratios in the trace updates yields general off-policy TD, lambda, and expected Sursa, lambda, algorithms, with control variates reducing variance as in Chapter 7. The chapter's careful accounting is worth pausing over. All these methods, even at lambda equals 1, still bootstrap in the sense that their targets depend on the current value estimates. It's just that the dependence cancels out in expected value. For lambda 1, the deadly triad applies, so they can be guaranteed stable only for the tabular case, for state aggregation, and for other limited forms of function approximation. Off-policy eligibility traces deal effectively with the first part of the challenge, the targets, but not at all with the second part, the distribution of updates. The practical verdict is honest. The practical consequences of all these new off-policy methods have not yet been established. Undoubtedly, issues of high variance will arise as they do in all off-policy methods using importance sampling. For stable algorithms, complete this section. GD, lambda, is the eligibility trace algorithm analogous to TDC. GQ, lambda, is the gradient TD algorithm for action values with eligibility traces. HTD, lambda, is a hybrid strict generalization of TD, lambda, to off-policy learning, so that if the behavior policy happens to be the same as the target policy, then HTD, lambda, becomes the same as TD, lambda, which is not true for GD, lambda, and emphatic TD, lambda, retains strong off-policy convergence guarantees while enabling any degree of bootstrapping, albeit at the cost of high variance and potentially slow convergence. And its follow-on trace, like ROT, is not really an additional memory variable. A telling precision, whereas emphatic TD, lambda, is guaranteed to converge for all state-dependent lambda functions, TD, lambda, is not. TD, lambda, is guaranteed convergent only for all constant lambda. Implementation issues and conclusions. The final section is a small lesson in computational thinking. A naive implementation would require every state to update both its value estimate and its eligibility trace on every time step, but for typical values of gamma and lambda, the eligibility traces of almost all states are almost always nearly 0. So implementations keep track of and update only the few traces that are significantly greater than 0, making the computational expense of using traces in tabular methods typically just a few times that of a one-step method. The chapter notes a subtle inversion. Note that the tabular case is in some sense the worst case for the computational complexity of eligibility traces. When function approximation is used, the computational advantages of not using traces generally decrease. For example, if ANNs and backpropagation are used, then eligibility traces generally cause only a doubling of the required memory and computation per step. The conclusions gather the practical doctrine. Eligibility traces are the first line of defense against both long-delayed rewards and non-Markov tasks. An intermediate mixture appears to be the best choice. Eligibility traces should be used to bring us toward Monte Carlo methods, but not all the way there, and the engineering rule for when traces pay. It often makes sense to use eligibility traces when data are scarce and cannot be repeatedly processed, but where data can be generated cheaply, perhaps from an inexpensive simulation. One-step methods are favored since the speed-up per datum due to traces is typically not worth their computational cost. Everything closes on the same uncertainty the field has carried since Chapter 6. Where shall we place them? We do not yet have a good theoretical answer to this question, but a clear empirical answer appears to be emerging. Quote, eligibility traces unify and generalize TD and Monte Carlo methods. When TD methods are augmented with eligibility traces, they produce a family of methods spanning a spectrum that has Monte Carlo methods at one end, lambda equals 1, and one-step TD methods at the other, lambda equals 0. Chapter 12 opening. Quote, it seems eligibility traces are not specific to TD learning at all. They are more fundamental than that. The need for eligibility traces seems to arise whenever one tries to learn long-term predictions in an efficient manner. Section 12.6. Quote, the fading strategy is often the best. Section 12.7 on the grid world comparison of one-step, in-step, and trace updates. Chapter 13. Policy gradient methods. Policy approximation and its advantages. The chapter opens with something new, methods that learn a parameterized policy directly, instead of first learning action values. So far in this book, almost all the methods have been action value methods. They learn the values of actions and then selected actions based on their estimated action values. Their policies would not even exist without the action value estimates. Here the agent learns a parameterized policy that can select actions without consulting a value function, though a value function may still be used to learn the policy parameter. These policy gradient methods seek to maximize performance, so their updates approximate gradient ascent in J, and methods that learn both policy and value functions are actor-critic methods, where actor is a reference to the learned policy, and critic refers to the learned value function. The standard discrete action parameterization is softmax in action preferences, a numerical preference H of S A theta per state, action pair, converted by an exponential softmax into action probabilities. The chapter lists the advantages with advocacy and precision. First, the approximate policy can approach a deterministic policy, whereas with epsilon greedy action selection over action values, there is always an epsilon probability of selecting a random action. Action preferences are driven to produce the optimal stochastic policy. If the optimal policy is deterministic, then the preferences of the optimal actions will be driven infinitely higher than all suboptimal actions. Second, it enables the selection of actions with arbitrary probabilities, which matters in card games with imperfect information, where the optimal play is often to do two different things with specific probabilities, such as when bluffing in poker, action value methods have no natural way of finding stochastic optimal policies. The famous short corridor with switched actions example seals the case. In a three-state corridor, where the second state's actions are reversed, all the states appear identical under the function approximation. So an action value method with epsilon greedy action selection is forced to choose between just two policies, right with high probability or left with high probability, achieving values of less than -82. A method can do significantly better if it can learn a specific probability with which to select right. The best probability is about 0.59, which achieves a value of about -11.6. A simpler advantage follows. The policy may be a simpler function to approximate than the value function, and the choice of policy parameterization is sometimes a good way of injecting prior knowledge about the desired form of the policy, often the most important reason for using a policy-based learning method. The policy gradient theorem. The chapter's theoretical core removes the apparent obstacle to gradient ascent, the unknown derivative of the state distribution. The performance gradient depends on the unknown effect of policy changes on the state distribution, but there is an excellent theoretical answer to this challenge in the form of the policy gradient theorem, which provides an analytic expression for the gradient of performance that does not involve the derivative of the state distribution. Its episodic form, nabla j of theta prop the sum over s mu of s the sum over a q sub pi of s a nabla pi of a given s theta, where the symbol is proportional to means proportional to the constant of proportionality being the average episode length in the episodic case, and 1 in the continuing case, where the policy gradient theorem remains true with values defined with respect to the differential return, and nabla j of theta equals r of pi under the average reward setting. The proof, given in a box, undoes the apparent impasse by a reorganization of the discounted visit expansion. The theorem is the chapter's load-bearing beam. Every subsequent algorithm is a way of sampling whose expectation equals or approximates this expression. Reinforce, Monte Carlo policy gradient. The first practical algorithm simply samples the theorem's gradient. Reinforce, Williams, 1992, replaces the sum over actions by the one action actually taken, a sub t, introducing the ratio that cancels the policy probability and leaving the eligibility vector nabla, the natural log pi of a sub t, given s sub t theta. Theta sub t plus 1 equals theta sub t plus alpha g sub t frac of nabla pi of a sub t, given s sub t theta sub t pi of sub t, given s sub t theta sub t. The chapter gives the updates intuition in full. Each increment is proportional to the product of a return gt and a vector, the gradient of the probability of taking the action actually taken divided by the probability of taking that action. The update increases the parameter vector in this direction proportional to the return and inversely proportional to the action probability. The first weighting causes the parameter to move most in the directions that favor actions that yield the highest return. The second ensures that actions that are selected frequently are not at an advantage and might win out even if they do not yield the highest return. Reinforce uses the complete return. In this sense, reinforce is a Monte Carlo algorithm, well defined only for the episodic case with all updates made in retrospect after the episode is completed. Reinforce with baseline. The first improvement subtracts a baseline from the return, reducing variance without bias. The general form replaces g sub t by g sub t minus b of s sub t, and the theory assures that the baseline does not change the expectation of the update. The state value function is the most natural choice for a baseline. The result can make it learn much faster. On the short corridor task, adding a baseline to reinforce can make it learn much faster. The step size used here for plain reinforce is that at which it performs best, yet the baseline version far outperforms it. The chapter also warns where tuning is easy versus hard. Choosing the step size for values is relatively easy with linear rules of thumb, while it is much less clear how to set the step size for the policy parameters. Actor-critic methods. By applying the learn value function to both states of a transition, reinforce becomes an actor-critic method, and the bias this introduces is carefully located. In reinforce with baseline, the learned state value function estimates the value of the first state of each state transition. This estimate sets a baseline, but is made prior to the transition's action and thus cannot be used to assess that action. In actor-critic methods, the state value function is applied also to the second state of the transition. The one-step return, RT plus 1 plus gamma V, street plus 1, W, is a useful estimate of the actual return and thus a way of assessing the action. The chapter's precision. The bias in the gradient estimate is not due to bootstrapping as such. The actor would be biased even if the critic was learned by a Monte Carlo method. The extensions are the now familiar spectrum, the one-step return, merely replaced by gt, t plus n or gt to the lambda, respectively, with separate eligibility traces for the actor and critic in the backward view, and for continuing problems, differential values and a running estimate of average reward, with the policy gradient theorem remain true. Policy gradient for continuing problems. The continuing version follows the pattern of Chapter 10, differential values and the average reward rate. Performance is defined as the average reward rate, and values are defined with respect to the differential return. With these definitions, the policy gradient theorem remains true for the continuing case, and the one-step actor critic becomes a fully online, incremental algorithm with states, actions, and rewards processed as they occur and then never revisited. The same epistemic virtue as one-step TD methods elsewhere. Policy parameterization for continuous actions. The chapter closes with an advantage no action value method naturally has: parameterizing distributions over continuous action spaces. Policy-based methods offer practical ways of dealing with large action spaces, even continuous spaces with an infinite number of actions. Instead of computing learned probabilities for each of the many actions, we instead learn statistics of the probability distribution. The canonical example is a normal distribution over a real-valued action, with mean and standard deviation given by parametric function approximators that depend on the state, the mean approximated linearly and the standard deviation, always positive, better approximated as the exponential of a linear function. Given this Gaussian parameterization, all the algorithms described in the rest of this chapter can be applied to learn to select real-valued actions. The summary gathers the ledger. Policy-based methods can learn specific probabilities for taking the actions, can learn appropriate levels of exploration and approach deterministic policies asymptotically, and can naturally handle continuous action spaces. All these things are easy for policy-based methods, but awkward or impossible for epsilon-greedy methods and for action value methods in general. When the policy is just simpler to represent parametrically than the value function. Policy methods are the sharper tool, and an important theoretical advantage follows from the policy gradient theorem, which does not involve the derivative of the state distribution. Quote, in this chapter, we consider methods that instead learn a parameterized policy that can select actions without consulting a value function. A value function may still be used to learn the policy parameter, but is not required for action selection. Chapter 13 opening. Quote, each increment is proportional to the product of a return GT and a vector, the gradient of the probability of taking the action actually taken divided by the probability of taking that action. The update increases the parameter vector in this direction proportional to the return and inversely proportional to the action probability. Section 13.3. Quote, action preferences are driven to produce the optimal stochastic policy. If the optimal policy is deterministic, then the preferences of the optimal actions will be driven infinitely higher than all suboptimal actions. Section 13.1. Looking deeper. Chapter 14. Psychology. Prediction and control. The chapter turns from computation to psychology, the perspective of psychology and its study of how animals learn. Its goals are twofold: to discuss ways that reinforcement learning ideas and algorithms correspond to what psychologists have discovered about animal learning, and second, to explain the influence reinforcement learning is having on the study of animal learning. The chapter is careful about its own epistemic stance from the start. Reinforcement learning explores idealized situation from the perspective of an artificial intelligence researcher or engineer, with the goal of solving computational problems with efficient algorithms, rather than to replicate or explain in detail how animals learn. Some correspondences are not surprising because the development of reinforcement learning drew inspiration from psychological learning theories, but others connect ideas that arose independently in their respective fields, and these points of contact are especially meaningful because they expose computational principles important to learning, whether it is learning by artificial or by natural systems. The chapter's organizing alignment is one of its cleanest recent contributions to psychological theory. The prediction/control distinction in reinforcement learning maps on a classical, Pavlovian, conditioning and instrumental, operant conditioning. Prediction algorithms estimate quantities that depend on how features of an agent's environment are expected to unfold over the future. Classical conditioning likewise rests on a common property of predicting upcoming stimuli, whether or not those stimuli are rewarding. Instrumental conditioning is a different situation. The experimental apparatus is set up so that an animal is given something it likes, a reward, or something it dislikes, a penalty, depending on what the animal did, and the reinforcing stimulus is said to be contingent on the animal's behavior, an arrangement that corresponds to the operation of reinforcement learning's policy improvement algorithms, and whose roots go back to experiments performed by Thorndike, the source of the law of effect first discussed in Chapter 1. The chapter concedes the mapping is a convenient first approximation. There is more to classical conditioning than prediction. It also involves action, and so is a mode of control, sometimes called Pavlovian control, and the two forms of conditioning interact in interesting ways, with both sorts of learning likely being engaged in most experimental situations. The ground is also surveyed for terminology, and here the book is careful with its own inherited words. In psychology, the term reinforcement is used to describe learning in both classical and instrumental conditioning. Originally referring only to the strengthening of a pattern of behavior, it is frequently also used for the weakening, and is stimulus considered to be the cause of the change of behavior is called a reinforcer, whether or not it is contingent on the animal's previous behavior. The book's warning stands as the chapter's ground rule. Many of the terms and phrases used in reinforcement learning are borrowed from animal learning theories, but the computational/engineering meanings do not always coincide with their meanings in psychology. The chapter also records a disciplinary caution. Although animal learning experiments came to play less of a role in psychology as the field turned cognitive, this experimentation led to the discovery of learning principles that are elemental and widespread throughout the animal kingdom. Principles that should not be neglected in designing artificial learning systems. Classical conditioning. The historical anchor is Pavlov's dogs, and Pavlov's own framing of what conditioning is for. The book quotes at length Pavlov's account of a metronome becoming able to elicit salivation, a stimulus quite alien to food, and his summary of its significance. Under natural conditions, the normal animal must respond not only to stimuli, which themselves bring immediate benefit or harm, but also to other physical or chemical agencies, waves of sound, light, and the like, which in themselves only signal the approach of these stimuli. The vocabulary unconditioned response, unconditioned stimulus, conditioned response, conditioned stimulus is introduced with a translator's caveat that better translations would have been conditional and unconditional. The chapter then builds its TD model of classical conditioning, and it is here that the book's algorithm meets the century of experimental data. The account explains blocking. If an animal has already learned that 1 CS predicts a US, then learning that a newly added second CS also predicts the US is much reduced. E is blocked because the TD model accounts for blocking because it is an error-correcting learning rule like the Rescorla-Wagner model. It goes beyond Rescorla, Wagner to the Egger-Miller effect. A well-placed CS suppresses conditioning to a better-placed one. And, most tellingly, it predicted a result that was later confirmed. Blocking is reversed if the blocked stimulus is moved earlier in time, because with the TD model, an earlier predictive stimulus takes precedence over a later predictive stimulus. The TD model is based on the backing up or bootstrapping idea. The book's account of this prediction, confirmed on the rabbit nictitating membrane preparation by Kehoe, Schreurs, and Graham, 1987, is one of its proudest moments. Non-TD models have considerable difficulty explaining their data. The predictions depend crucially on how the stimulus is represented in time. The presence, stimulus trace, or microstimulus representations produce different US prediction profiles, and on the interaction of stimulus representation with discounting and eligibility traces. What unifies them is that the model's predictions increase as the time of the US approaches and reach a maximum at the time of the US, as is seen in many animal conditioning experiments. The deepest correspondence concerns higher-order conditioning, where a previously conditioned CS can act as a US in conditioning another initially neutral stimulus. The chapter works through the second-order case in concrete terms. In the first phase, CSB is trained to predict a US so that its associative strength increases. And in the second phase, CSA is paired with CSB in the absence of the US. So CSA acquires associative strength even though it is never paired with the US. With continued training, CSA's associative strength reaches a peak and then decreases because the associative strength of CSB, the secondary reinforcer, decreases so that it loses its ability to provide secondary reinforcement. These are extinction trials for CSB, and this same pattern is seen in animal experiments. The mechanism is the bootstrapping term itself. Due to the first phase of learning, V, ST plus 1, WT, minus V, ST, WT, may differ from 0, making the TD error non-zero, a temporal difference. This difference has the same status as RT plus 1, implying that as far as learning is concerned, there is no difference between a temporal difference and the occurrence of a US. The book draws the conclusion plainly. Bootstrapping values is intimately related to second-order and higher-order conditioning, and this feature of the TD algorithm is one of the major reasons for its development, now understood through its connection to dynamic programming. The TD model, when combined with particular stimulus representations and response generation mechanisms, is able to account for a surprisingly wide range of phenomena, including the shape of conditioned responses, which increase as the time of the US approaches and reach a maximum at the time of the US. As in many animal conditioning experiments, though it is far from being a perfect model. The chapter's framing of what the model is for carries real philosophical weight. It suggests a normative account of classical conditioning in which long-term, instead of immediate, prediction is a key feature. The animal nervous system is, on this view, trying to form accurate long-term predictions consistent with the limitations imposed by the way stimuli are represented and how the nervous system works. That normative framing, that conditioning is not a reflex strengthening byproduct, but the nervous system doing prediction well, is the chapter's deepest claim, and it is what makes the psychological correspondence more than an analogy. The Rescorla, Wagner model, and TD model simulations. Blocking is the textbook phenomenon the chapter keeps returning to, and it is worth treating as its own movement. The Rescorla, Wagner model explains blocking through error correction. Once one CS already predicts the US, the prediction error available to a newly added CS has been absorbed, so the new CS acquires little strength. The TD model inherits this and adds temporal structure. Conditioned responses can be timed. Remote associations are facilitated when the trace interval between a first CS and the US is filled with a second CS, matching Kehoe's 1982 results. And the model's sensitivity to the ordering and onset of stimuli explains effects, like temporal primacy overriding blocking, that set it apart. The message is that timing, not just contingency, is computational. The timing and shape of SAR is critical to its adaptive significance. Covering the eye too early reduces vision, while covering it too late is of little protective value. And the chapter notes the broader modeling landscape. Other approaches to modeling classical conditioning depart significantly from the Rescorla, Wagner-style error correction process, including Bayesian models, and all of these models usefully contribute to our understanding. Instrumental conditioning. The chapter turns to the second great laboratory tradition, whose roots go back to experiments performed by the American psychologist Edward Thorndike 100 years before publication of the first edition. Thorndike's puzzle boxes cats to strive instinctively to escape from confinement, escaping by performing a sequence of 3 separate actions, are the ancestral scene and the law of effect its summary. Responses, closely followed by satisfaction, are strengthened, those followed by discomfort weakened. B.F. Skinner's operant conditioning is treated as a close cousin, though the book notes the two traditions differ in a number of ways. The section's central mechanism argument links delayed reward to conditioned reinforcement through both eligibility traces and TD-based value functions. Hull's theory supplies the historical vocabulary. Molar's stimulus traces account for the goal gradient, a description of how the maximum strength of an instrumentally conditioned response decreases with increasing delay of reinforcement, And the eligibility traces used in the algorithms described in this book are like Hull's traces. They're decaying traces of past state visitations or of past state. Action pairs, where delays outrun stimulus traces. Hull proposed conditioned reinforcement passing backward from the goal, with a primary gradient based on the delay of the primary reinforcement, mediated by stimulus traces, progressively modified and lengthened by conditioned reinforcement. The book finds the algorithmic echo. Algorithms presented in this book that use both eligibility traces and value functions to enable learning with delayed reinforcement correspond to Hull's hypothesis. Nowhere more clearly than in the actor-critic architecture, where the TD error produced by the critic acts as a conditioned reinforcement signal for the actor, providing an immediate evaluation of performance even when the primary reward signal itself is considerably delayed. Delayed reinforcement. The actor-critic correspondence broadens into the general claim that TD learning enables credit assignment across time. The section opens with the conceptual obstacle. The law of effect requires a backward effect on connections, and some early critics of the law could not conceive of how the present could affect something that was in the past, a worry amplified by the fact that learning can even occur when there is a considerable delay between an action and the consequent reward or penalty. This is precisely what Minsky, 1961, called the credit assignment problem for learning systems. How do you distribute credit for success among the many decisions that may have been involved in producing it? The book's answer is that its algorithms include two basic mechanisms for addressing this problem: the use of eligibility traces and the use of TD methods to learn value functions that provide nearly immediate evaluations of actions, or that provide immediate prediction targets. And both of these methods correspond to similar mechanisms proposed in theories of animal learning. The historical threads converge here. Pavlov, 1927, pointed out that every stimulus must leave a trace in the nervous system that persists for some time after the stimulus ends. To this day, conditioning under these conditions is called trace conditioning. Hull's molar stimulus traces hypothesis accounted for what he called an animal's goal gradient, and he hypothesized that the traces effectively reach zero after 30 to 40 seconds. And the eligibility traces used in the algorithms described in this book are like Hull's traces. They're decaying traces of past state visitations or of past state action pairs, with Klopp's traces, temporally extended traces of past activity at synapses. They're more complex kin. The payoff is a unified mechanism story. Value-based methods, Q-learning, SIRSA, similarly use TD learning principles to enable learning with delayed reinforcement by means of conditioned reinforcement. So the ancient problem of bridging gaps in time is solved by the same bootstrapping that drives the TD error. It is as if reward is not actually delayed because there is more immediate conditioned reinforcement. The chapter also links the framework to motivation via the value function state dependence. Some internal state components correspond to what psychologists call an animal's motivational state, which influences what is rewarding to the animal. An animal will be more rewarded by eating when it is hungry than when it has just finished a satisfying meal. For a value-based agent, a more proximal motive is to ascend the gradient of its value function, that is, to select actions expected to lead to the most highly valued next states. So, value functions are the main driving force determining the direction of their behavior. The chapter is candid that one dimension resists the mapping. Motivational state also influences the strength or vigor of the animal's behavior after learning. A hungry rat will run faster to the goal box than one that is not hungry, which does not link so cleanly to the reinforcement learning framework we present here, though it cites theories of behavioral vigor built on reinforcement learning. Cognitive maps. Model-based learning finds its psychological correlate in latent learning and the cognitive map. The chapter recounts Blodgett's early latent learning experiment. Two groups of rats were run in a maze. The experimental group, with no reward during the first stage before food was suddenly introduced, and the control group with food present throughout. Although the experimental rats did not appear to learn much during the first, unrewarded stage, as soon as they discovered the food, they rapidly caught up with the rats in the control group. Blodgett's conclusion: during the non-reward period, The rats were developing a latent learning of the maze which they were able to utilize as soon as reward was introduced. Tolman's interpretation, which became the phenomenon's name, was that animals could learn a cognitive map of the environment in the absence of rewards or penalties, usable later when they were motivated to reach a goal, and that a cognitive map could also allow a rat to plan a route to the goal that was different from any route it had previously followed. The computational translation is direct. Model-based algorithms use environment models that have elements in common with what psychologists call cognitive maps, with a state transition part and a reward model part. And the simplest kind of planning is to compare the predicted consequences of collections of imagined sequences of decisions. The section's worked example, a maze with goal boxes of different rewards, clarifies exactly why the two strategies differ. A model-free rat has to move to that state, act from it, possibly many times, and experience the consequences of its actions, whereas a model-based agent can accommodate changes in its environment without this kind of personal experience. A rewrite of one reward in the model will change even though the action choices required to find that goal box in the maze were not involved. Exactly this logic is the basis of outcome evaluation experiments, and the framework also supplies the term that ties the section to the neuroscience chapter. Such model-based processes are the computational face of what the hippocampus, critical for the state transition part of an animal's environment model, will later be seen to implement. Habitual and goal-directed behavior. The chapter's final movement answers an old question with a computational picture. When should an animal be goal-directed, and when habitual? The outcome evaluation experiment of Adams and Dickinson, 1981, is described in full. Rats trained to press a lever for sucrose, made sick with lithium chloride after non-contingent feeding, then tested in extinction, and the injected rats had significantly lower response rates than the non-injected rats right from the start, even though no lever was present when they were made sick. The explanation is cognitive. The rats associated lever pressing with consequent nausea by means of a cognitive map, linking lever pressing to pellets and pellets to nausea, so they reduced their lever pressing without ever having experienced lever pressing directly followed by being sick. The chapter notes the controversy. Not every psychologist agrees with this cognitive account, but endorses the model-based planning explanation as widely accepted. Adams's follow-up experiment, 1982, showed the converse. Overtrained rats, 500 rewarded presses, were largely insensitive to devaluation. If anything, it made pressing more vigorous, the signature of habit. The computational interpretation ties the arc back to the book's core dichotomy, an idea developed by computational neuroscientists Daw, Neve, and Diane, 2005, is that animals use both model-free and model-based processes with the action chosen for execution, the one proposed by the process judged to be the more trustworthy, using maintained measures of confidence. Early in learning, the planning process of a model-based system is more trustworthy because it chains together short-term predictions which can become accurate with less experience than long-term predictions of the model-free process. But with continued experience, the model-free process becomes more trustworthy because planning is prone to making mistakes due to model inaccuracies and shortcuts. According to this idea, one would expect a shift from goal-directed behavior to habitual behavior as more experience accumulates. The summary restates the whole chapter's posture. Reinforcement learning, as described in this book, is not intended to model details of animal behavior. It is an abstract computational framework. But many of the basic reinforcement learning algorithms were inspired by psychological theories. And in some cases, these algorithms have contributed to the development of those theories' computational descendants. Quote, "The activity of the salivary gland has thus been called into play by impulses of sound, a stimulus quite alien to food." Pavlov, 1927, quoted in section 14.2. Quote, "It is pretty evident that under natural conditions the normal animal must respond not only to stimuli which themselves bring immediate benefit or harm, but also to other physical or chemical agencies, waves of sound, light, and the like, which in themselves only signal the approach of these stimuli." Pavlov, 1927, quoted in section 14.2, quote, implying that as far as learning is concerned, there is no difference between a temporal difference and the occurrence of a U.S. Bootstrapping values is intimately related to second-order and higher-order conditioning. Section 1, 4.2.4. Chapter 15, Neuroscience. Neuroscience Basics and Reward Signals. The chapter's main objective is stated plainly: to explain the mounting evidence from neuroscience that the nervous systems of humans and many other animals implement algorithms that correspond in striking ways to reinforcement learning algorithms. The most remarkable point of contact between reinforcement learning and neuroscience involves dopamine, a chemical deeply involved in reward processing, which appears to convey temporal difference, TD, errors to brain structures where learning and decision-making take place. The reward prediction error hypothesis of dopamine neuron activity. The authors are scrupulous about their own limits. In this chapter, we do not delve very deeply into the enormous complexity of the neural systems underlying reward-based learning in animals. This chapter is too short, and we are not neuroscientists. And we also do not do justice to hypotheses and models that are alternatives to those that align so well with reinforcement learning. Yet the hope is real. A very fruitful channel has emerged connecting reinforcement learning and its theoretical underpinnings to the neuroscience of reward-based learning. The Neuroscience Basics section is a compact primer in the book's accessible register. Neurons, dendrites, axons, action potentials, also called spikes, synapses and neurotransmitters, background versus phasic versus tonic activity, synaptic efficacy, neuromodulation, and synaptic plasticity. Two structural arrangements do the heavy lifting later. A neuron's axon can branch widely so that the neuron's action potentials reach many targets, and a neuron's background activity is its level of activity. When a neuron does not appear to be driven by synaptic input related to the task, distinguishing it from phasic activity, which consists of bursts of spiking activity, usually caused by synaptic input. The statements that matter for what follows, the parameters or weights adjusted by learning algorithms correspond to synaptic efficacies, and modulation of synaptic plasticity via the neuromodulator dopamine is a plausible mechanism for how the brain might implement learning algorithms like many of those described in this book. The reward signal section sharpens the vocabulary, and its distinctions are load-bearing. To explain links that have been made between neuroscience and reinforcement learning, we have to be less abstract than the three signals of Chapter 3 and consider other reinforcement learning signals that correspond, in certain ways, to signals in the brain. The important claim is that reinforcement signals are not reward signals. A reward is the scalar emitted by the environment, whereas a reinforcement signal, like the TD error, is the internal quantity that actually drives changes in learning. Labeling a neural signal by its function means that the neural signal behaves like, and is conjectured to function like, the corresponding theoretical signal. The experimental challenge is acknowledged with honesty. Neural activity related to reward processing can be found in nearly every part of the brain, and representations of different reward-related signals tend to be highly correlated with one another. So experiments need to be carefully designed to allow one type of reward-related signal to be distinguished with any degree of certainty from others. The reward prediction error hypothesis. The chapter's centerpiece hypothesis resulted from the convergence of computational reinforcement learning and results of neuroscience experiments. The hypothesis proposes that one of the functions of the phasic activity of dopamine-producing neurons in mammals is to deliver an error between an old and a new estimate of expected future reward at target areas throughout the brain, and the chapter credits its first explicit statement, though not in these exact words, to Montague, Dian, and Sanowski, 1996, who showed how the TD error concept from reinforcement learning accounts for many features of the phasic activity of dopamine. Neurons in mammals, against the background of experiments performed in the 1980s and early 1990s in the laboratory of neuroscientist Wolfram Schultz. The comparison requires two modeling assumptions worth making explicit. First, because a TD error can be negative, but neurons cannot have a negative firing rate. Montague et al. assumed that the quantity corresponding to dopamine neuron activity is delta plus 1 plus BT, where BT is the background firing rate of the neuron. A negative TD error corresponds to a drop in a dopamine neuron's firing rate below its background rate. Second, the trial states must be represented as inputs to the learning algorithm. Montague et al. Chose a complete serial compound, CSC, representation, which allows the TD error to mimic the fact that dopamine neuron activity not only predicts a future reward, but that it is also sensitive to when after a predictive cue that reward is expected to arrive. With these assumptions, TD errors of the TD model are remarkably similar to dopamine neuron phasic activity, paralleling four features. 1. The phasic response of a dopamine neuron only occurs when a rewarding event is unpredicted. 2. Early in learning, neutral cues do not cause substantial phasic dopamine responses. But with continued learning, these cues gain predictive value and come to elicit phasic dopamine responses. 3. If an even earlier cue reliably precedes a cue that has already acquired predictive value, the phasic dopamine response shifts to the earlier cue, ceasing for the later cue. And 4. If after learning, the predicted rewarding event is omitted, a dopamine neuron's response decreases below its baseline level shortly after the expected time. The chapter's assessment is measured. Not every dopamine neuron monitored in the experiments behaved in all of these ways, yet the striking correspondence between the activities of most of the monitored neurons and TD errors lends strong support to the reward prediction error hypothesis. And there are situations in which predictions based on the hypothesis do not match what is observed, with the choice of input representation critical to how closely TD errors match some of the details of dopamine neuron activity, particularly details about the timing. Still, overall, the reward prediction error hypothesis has received wide acceptance among neuroscientists studying reward-based learning, and it has proven to be remarkably resilient in the face of accumulating results from neuroscience experiments. Dopamine and experimental support. The anatomy makes the broadcast hypothesis concrete, and the modern experiments give it causal teeth. The chapter first identifies the source. Dopamine is produced as a neurotransmitter by neurons whose cell bodies lie mainly in two clusters of neurons in the midbrain of mammals, the substantia nigra pars compacta, SMPC, and the ventral tegmental area, VE, and it plays essential roles in many processes in the mammalian brain: motivation, learning, action selection, most forms of addiction, and the disorders schizophrenia and Parkinson's disease, being called a neuromodulator because it performs many functions other than direct, fast excitation or inhibition of targeted neurons. Dopamine neurons are particularly well suited to broadcasting a reinforcement signal to many areas of the brain. These neurons have huge axonal arbors, each releasing dopamine at 100 to 1,000 times more synaptic sites than reached by the axons of typical neurons. With each axon of SMPC or VTA dopamine neuron MAC, and roughly 500,000 synaptic contacts. The target structure is the basal ganglia, a collection of neuron groups or nuclei lying at the base of the forebrain, whose main input structure is called the striatum, fed essentially all of the cerebral cortex. The striatum's main input-output neurons are medium spiny neurons, and its two main subdivisions carry the field's mapping. The dorsal striatum, primarily implicated in influencing action selection, and the ventral striatum, thought to be critical for different aspects of reward processing, including the assignment of effective value to sensations. The spine anatomy of striatal medium spiny neurons is the crucial coincidence. An axon of a VTA or SMPC dopamine neuron contacts the spine stem, while a cortical axon contacts the spine tip, an arrangement that brings together presynaptic input from cortex, postsynaptic activity of a striatal neuron, and dopamine, making possible several types of learning rules. The book notes the received simplification and its modern correction, although it has been a common belief that dopamine neurons do act together like this. Modern evidence is pointing to the more complicated picture that different subpopulations of dopamine neurons respond to input differently depending on the structures to which they send their signals, including vector-valued RPE signals. Tied to the structural credit assignment problem, how do you distribute credit for success or blame for failure of a decision among the many component structures that could have been involved in producing it? The experimental support section marshals optogenetics, the technique that made causality possible. Optogenetic methods introduce light-sensitive proteins into selected neuron types so that these neurons can be activated or silenced by means of flashes of laser light, enabling precisely control of the activity of selected neuron types at a millisecond timescale in awake, behaving animals. The key results. The first experiment using optogenetic methods to study dopamine neurons showed that optogenetic stimulation producing phasic activation of dopamine neurons in mice was enough to condition the mice to prefer the side of a chamber where they received this stimulation. Steinberg et al. 2013 used optogenetic activation to create artificial bursts at the times when rewarding stimuli were expected but omitted times when dopamine neuron activity normally pauses, and with these pauses replaced by artificial bursts, responding was sustained, and learning was enabled when it would ordinarily be blocked in the blocking paradigm. And fruit fly experiments show the surprising fact that in these animals dopamine's effect is the opposite of its effect in mammals, acting just like electric foot shock in reinforcing avoidance behavior. The summary sentence is carefully measured. Although none of these optogenetic experiments showed that phasic dopamine neuron activity is specifically like a TD error, they convincingly demonstrated that phasic dopamine neuron activity acts just like delta acts as the reinforcement signal in algorithms for both prediction and control. Causality is established where correlation alone could not reach. TD error/dopamine correspondence. The correspondence is worked out in close quantitative detail through the idealized policy evaluation task. The chapter assumes a learned policy, a trial treated as an episode, the complete serial compound CSC representation, and TD0 on a lookup table. This reduces the process to the tabular case covered in the first part of this book. The 3 stages of learning tell the whole story. Early in learning, with all value 0, the TD error is also 0 until it becomes R star at the rewarding state, analogous to a dopamine neuron responding to an unpredicted reward at the start of training. As learning proceeds, the increases spread backwards from the rewarding state until the values converge to the correct return predictions. When learning is complete, the TD errors associated with transitions from any reward predicting state are 0 because the predictions are now accurate. The TD error on a transition from any state to the earliest reward predicting state is positive, and a transition from the latest reward predicting state to the rewarding state produces a 0 TD error because the latest reward predicting state's value, being correct, cancels the reward. All 3 coincide with the phasic dopamine data. The positive error at the earliest predictor mirrors the persistence of dopamine responses to the earliest stimuli predicting reward, and the 0 error at predicted reward parallels that fewer dopamine neurons generate a phasic response to a fully predicted reward than to an unpredicted reward. If the reward is omitted, delta becomes negative, the dopamine pause. Neural actor, critic. The correspondence extends to system architecture. The neural actor critic hypothesis, Takahashi, Schoenbaum, and Neve, 2008, puts the actor and the value learning part of the critic respectively in the dorsal and ventral subdivisions of the striatum, the basal ganglia's input structure. The TD error is transmitted by dopamine neurons located in the VTA and SNPC to modulate changes in synaptic efficacies of input from cortical areas to the ventral and dorsal striatum. The algorithmic picture runs on the same broadcast signal. The TD error produced by circuitry in the critic is the reinforcement signal for changing the weights in both the critic and the actor networks, and this aspect of the network implementation, together with the reward prediction error hypothesis and the fact that the activity of dopamine neurons is so widely distributed, suggests that an actor critic network something like this may not be too far-fetched. The error line in the algorithm figure becomes the line labeled dopamine, the widely branching axons of dopamine neurons. The section draws an important conceptual caution. The dopamine signal is not the master reward signal like the scalar RT of reinforcement learning. One should not necessarily be able to probe the brain and record any signal like RT in the activity of any single neuron. Rather, what the theoretical scalar reward signal RT might correspond to is the net contribution of all reward-related information to dopamine neuron activity, a pattern across many neurons in different areas of the brain, since dopamine neurons receive information from many different brain areas. Actor and critic learning rules. The section isolates the exact computational difference between the two learning rules and locates it in the eligibility traces. The TD error, combined with eligibility traces, tells the actor how to update action probabilities in order to reach higher valued states. The actor works to keep delta as positive as possible, like instrumental conditioning with a law of effect type rule. On the other hand, the TD error tells the critic the direction and magnitude in which to change the parameters of the value function in order to improve its predictive accuracy. The critic works to reduce delta S magnitude to be as close to zero as possible, like the TD model of classical conditioning. The difference between the critic and actor learning rules is relatively simple, but this difference has a profound effect on learning and is essential to how the actor-critic algorithm works. The difference lies solely in the eligibility traces each type of learning rule uses. This is one of the book's most elegant compressed statements. A single broadcast error signal, read with different traces, becomes two different kinds of learning. The section then carries the distinction into synaptic terms, and the two-factor/three-factor vocabulary earns its keep. Unlike the non-contingent eligibility trace of a critic synapse that only accumulates the presynaptic activity XST, the eligibility trace of an actor unit synapse, in addition, depends on the activity of the actor unit itself. So it is called a contingent eligibility trace because it is contingent on this postsynaptic activity. The eligibility trace at each synapse continually decays, but increments or decrements depending on the activity of the presynaptic neuron and whether or not the postsynaptic neuron fires. The postsynaptic contingency in the eligibility traces of actor units is the only difference between the critic and actor learning rules. Both rules trace their lineage to Hebb. The critic and actor learning rules share with Hebb's proposal the idea that changes in a synapse's efficacy depend on the interaction of several factors. The critic rule is between the reinforcement signal delta and eligibility traces that depend only on presynaptic signals. Neuroscientists call this a two-factor learning rule. The actor learning rule, on the other hand, is a three-factor learning rule because, in addition to depending on delta, its eligibility traces depend on both presynaptic and postsynaptic activity. The crucial departure from Hebb is timing. Unlike Hebb's proposal, however, the relative timing of the factors is critical to how synaptic efficacies change, with eligibility traces intervening to allow the reinforcement signal to affect synapses that were active in the recent past. Hedonistic neurons and collective reinforcement learning. The chapter reaches back to Klopf, the book's dedicatee, for a theory of synaptic learning with hedonic content. Klopf's neurons are hedonistic. They view all of their inputs in reinforcement terms, excitatory inputs as rewards and inhibitory inputs as punishments, the generalized reinforcement idea introduced in the Chapter 1 history. The distinctive part of Klopf's conception is the shape of the eligibility trace. The shape and time course of an eligibility trace in Klopf's theory reflects the durations of the many feedback loops in which the neuron is embedded, so that the shape of a synaptic eligibility trace is like a histogram of the durations of the feedback loops in which the neuron is embedded, with the peak of an eligibility trace occurring at the duration of the most prevalent feedback loops in which that neuron participates. The book is explicit that its own traces are simplified versions of Klopf's original idea, being exponentially, or geometrically, decreasing functions controlled by the parameters gamma and lambda, and that we regard these simple eligibility traces as placeholders for traces closer to Klopf's original conception. which would have computational advantages in complex reinforcement learning systems by refining the credit assignment process. The section grounds the hedonistic neuron in biology with the single-cell case of E. coli, a well-studied example of a single cell that seeks some stimuli and avoids others. The bacterium's chemotaxis, it swims in its liquid environment by rotating hair-like structures called flagella, works by a little chemical memory and computation, causing the frequency of flagellar reversal to decrease when the bacterium swims toward higher concentrations of molecules it needs to survive, attractants, and increase when the bacterium swims toward harmful repellents, so that it tends to persist in swimming up attractant gradients. The behavior, called clinokinesis, is a kind of trial-and-error behavior, although it is unlikely that learning is involved. Artificial intelligence pioneer Oliver Selfridge called it run and twiddle, pointing out its utility as a basic adaptive strategy. Keep going the same way if things are getting better, and otherwise move around. Similarly, one might think of a neuron swimming in a medium composed of the complex collection of feedback loops through which it is embedded, maximizing systems at the smallest scale. The collective reinforcement learning section then shows how a multi-layer team of Bernoulli logistic reinforce units learns like a multi-layer network trained by the widely used error backpropagation method. But in this case, the backpropagation process is replaced by the broadcasted reward signal, with credit or blame assigned to individual team members, including the structural credit assignment problem addressed by contingent eligibility traces and winner-take-all arrangements. Model-based methods in the brain. The distinction between model-free and model-based algorithms becomes a tool for reading the brain, and the evidence argues against a clean separation. Inactivating different parts of the rat's dorsal striatum dissociates the systems. Inactivating one part of the dorsal striatum, the dorsolateral striatum, DLS, impairs habit learning, causing the animal to rely more on goal-directed processes, while inactivating the dorsomedial striatum, DMS, impairs goal-directed processes, requiring the animal to rely more on habit learning. The DLS in rodents is more involved in model-free processes, whereas their DMS is more involved in model-based processes, a pattern supported in humans and non-human primates. The orbitofrontal cortex, OFC, the part of the prefrontal cortex immediately above the eyes, shows strong activity related to the subjective reward value of biologically significant stimuli and may be critical for the reward part of an animal's environment model. The hippocampus, Tolman's cognitive map again, may be a critical component of our human ability to imagine new experiences. The evidence directly implicating the hippocampus in planning comes from decoding neural activity. When a rat pauses at a choice point in a maze, the representation of space in the hippocampus sweeps forward and not backwards along the possible paths, and the spatial trajectories represented by these sweeps closely correspond to the rat's subsequent navigational behavior, a form of planning. The open questions are listed as a genuine research agenda. How structurally similar DLS and DMS support modes of learning and behavior that are as different as model-free and model-based. Whether all planning is conducted at decision time via simulations, or are models sometimes engaged in the background to refine or recompute value information as illustrated by the DINA architecture. And how does the brain arbitrate between the use of the habit and goal-directed systems? The honest caveat: the evidence is not pointing to a positive answer to the clean separation question. Model-based influences appear ubiquitous more or less wherever the brain processes reward information, even in the regions thought to be critical for model-free learning, including the dopamine signals themselves. Addiction. The chapter's final movement applies the theory to a public health problem with full honesty about the model's limits. The underlying idea: addictive substances, by being intensely reinforcing, effectively co-opt our natural mechanisms of learning and decision-making. Reddish's 2004 model builds on the reward prediction error hypothesis. Administration of cocaine and some other addictive drugs produces a transient increase in dopamine, which is assumed to increase the TD error delta in a way that cannot be canceled out by changes in the value function, drug rewards cannot be predicted away. The model does this by preventing delta from ever becoming negative when the reward signal is due to an addictive drug, thus eliminating the error-correcting feature of TD learning for states associated with administration of the drug. The result is that the values of these states increase without bound, making actions leading to these states preferred above all others. The chapter is conspicuously careful about the limits. Addictive behavior is much more complicated than this result from Reddish's model, but the model's main idea may be a piece of the puzzle. Or the model might be misleading. Dopamine appears not to play a critical role in all forms of addiction. The model does not include the changes in many circuits and brain regions that accompany chronic drug taking, and it is also likely that addiction involves model-based processes. Even so, Reddish's model illustrates how reinforcement learning theory can be enlisted in the effort to understand a major health problem, and reinforcement learning theory has been influential in the development of the new field of computational psychiatry. Quote, dopamine appears to convey temporal difference, TD, errors to brain structures where learning and decision-making take place. Chapter 15 opening. Quote, the difference between the critic and actor learning rules is relatively simple, but this difference has a profound effect on learning and is essential to how the actor-critic algorithm works. The difference lies solely in the eligibility traces each type of learning rule uses. Section 15.8. Quote, model-based influences appear ubiquitous more or less wherever the brain processes reward information. Dahl, Simon, and Daw, 2012, quoted in Section 15.11. Chapter 16, Applications and Case Studies. TD Gammon. The chapter opens with one of the most impressive applications of reinforcement learning to date. Tessero's TD Gammon required little backgammon knowledge, yet learned to play extremely well, near the level of the world's strongest grandmasters, using a straightforward combination of a TD, lambda, algorithm, and nonlinear function approximation using a multi-layer artificial neural network, ANN, trained by backpropagating TD errors. The tutorial on backgammon, 15 white and 15 black pieces, 24 points, a game, in part, of chance, and a popular vehicle for waging significant sums of money, where there are probably more professional backgammon players than there are professional chess players, sets the scale. The rules include hitting, and the bar, 2 pieces on a point offering protection, and forming contiguous blocks of occupied points to block the opponent. For a typical dice roll, there might be 20 different ways of playing, and accounting for the opponent's dice rolls, the game tree has an effective branching factor of about 400, far too large to permit effective use of the conventional heuristic search methods that have proved so effective in games like chess and checkers. Why, then, did TD learning fit so well? The game is a good match to the capabilities of TD learning methods. Although the game is highly stochastic, a complete description of the game state is available at all times. The game evolves over a sequence of moves and positions until finally ending in a win for one player or the other, and the outcome can be interpreted as a final reward to be predicted. Yet the number of states is so large that a lookup table cannot be used, and the opponent is a source of uncertainty and time variation. Exactly the regime the approximation chapters had prepared. The lineage is precise, TD Gammon 0.0, whose network input was essentially a raw representation. Learn to play approximately, as well as the best previous backgammon computer programs, while adding specialized backgammon features produced TD Gammon 1.0, substantially better in the later versions, 2.0 through 3.1. Added 2-ply and 3-ply selective search and 160 hidden units, Illustrat, ing. The combination of learn value functions and decision time search, as in heuristic search, and MCTS methods. The training regime, tabulated by hidden units in training games, shows the scale. TD 0.0 played 300,000 training games and tied for best against other programs. 1.0 scored 13 points / 51 games against Roberty and Magriel. 2.1, 1 point / 40 games against Roberty, and 3.0, 1 + 6 points / 20 games against Kazaros. against whom TD Gammon 3.0 appeared to play it close to, or possibly better than, the playing strength of the best human players in the world. A subsequent rollout analysis of the move decisions and doubling decisions of TD Gammon relative to top human players concluded TD Gammon 3.1 had a lopsided advantage in piece movement decisions and a slight edge in doubling decisions. In follow-on work, Tesoro and Galperin, 1997, explored trajectory sampling methods as an alternative to full-width search, which reduced the error rate of live play by large numerical factors, 4 times, 6 times, while keeping the think time reasonable at 4 to 5 seconds per move. Most striking is the reverse influence. TD Gammon had a significant impact on the way the best human players play the game, teaching new opening positions based on TD Gammon's success and further analysis. With spin-off programs, Jellyfish, Snowy, GNU Backgammon, result in great improvements in the overall caliber of human tournament play. Samuel's checkers player. The historical root of the family tree is Arthur Samuel's checkers player, an important precursor in every sense. Samuel's 1959 program learned by self-play from a linear evaluation function over hand-selected features, and it changed its feature weights on each move based on the difference between the evaluation of the positions before and after the move, a temporal difference scheme before TD had a name, and one of the few genuine temporal difference implementations before the field was named. The first version learned the opening game by rote, with a middle game Samuel characterized as tricky but beatable, in contrast to the rote learning version. This version was able to develop a good middle game, but remained weak in opening and endgame play, and it also included an ability to search through sets of features to find those that were most useful in forming the value function. A later version, 1967, included refinements in its search procedure, such as alpha-beta pruning, extensive use of a supervised learning mode called book learning, and hierarchical lookup tables called signature tables to represent the value function instead of linear function approximation, and learned to play much better than the 1959 program, though still not at a master level. The chapter's verdict. Samuel's checkers playing program was widely recognized as a significant achievement in artificial intelligence and machine learning. And the lineage it begins, Samuel TD Gammon DQN AlphaGo, is the chapter's spine. Watson's daily double wagering. IBM Watson's Jeopardy! Victory rested on a TD Gammon-descended wagering strategy. Although the main technical achievement demonstrated by Watson was its ability to quickly and accurately answer natural language questions, its winning performance also relied on sophisticated decision-making strategies. The daily double wagering component is the component of Watson that owes the most to reinforcement learning. The chapter first explains the game's stakes. Winning or losing often depends on a contestant's DD wagering strategy, because the bet has to be greater than $5 but not greater than the contestant's current score, and must be set before the clue is revealed. The mechanism is elegantly value-based. Watson selected the bet with maximum action value. Hat of QS bet equals P sub DD hat of VS sub W plus bet dots. C plus 1 minus P sub DD hat of VS sub W minus bet dots. C, where hat of V was a state value function learned by a straightforward combination of nonlinear TD, lambda, using a multilayer ANN, from millions of simulated games against carefully crafted models of human players, not self-play, because self-play would have been something like playing poker with someone who is holding the same cards that you hold. Watson was so different from any human contestant that self-play would have led to exploration of state space regions that are not typical for play against human opponents. The in-category confidence P sub DD was estimated from Watson's actual accuracies over many thousands of historical categories. The section is a small case study in engineering judgment. Maximization incurred a frightening amount of risk, so Tesoro et al. Adjusted the equation by subtracting a small fraction of the standard deviation and prohibited bets that would cause the wrong answer after state value to decrease below a certain limit, measures that slightly reduced Watson's expectation of winning, but significantly reduced downside risk, not only in terms of average risk per DD bet, but even more so in extreme risk scenarios where a risk-neutral Watson would bet most or all of its bankroll. Optimizing memory control. The chapter turns to a scheduler's problem where reinforcement learning beat hand-designed heuristics. A draw memory controller needs to deal with dynamically changing patterns of read/write requests while adhering to a large number of timing and resource constraints, a formidable scheduling problem, especially with modern processors with multiple cores sharing the same DRAM. The control problem is genuinely a sequential decision problem. DRAM cells need to be recharged, refreshed, every few milliseconds, hence the dynamic and activate command open to row into the row buffer, reads and writes transfer words, and before a different row can be opened, a precharge command must be issued so that read and write commands to the currently open row can be carried out more quickly than accessing a different row locality. A controller has to process requests by issuing commands to the memory system while adhering to a large number of timing constraints. And the simplest scheduling strategy handles access requests in the order in which they arrive, but if the system is not ready for one of these commands, it makes sense to begin servicing a newer request before finishing the older one. IPEC, Mutlu, Martinez, and Caruana, 2008, designed a reinforcement learning memory controller and demonstrated that it can significantly improve the speed of program execution over what was possible with conventional controllers at the time, motivated by controllers that did not take advantage of past scheduling experience and did not account for long-term consequences of scheduling decisions. The design was carried out by means of simulation, but they designed the controller at the detailed level of the hardware needed to implement it, including the learning algorithm, directly on a processor chip. The lesson for the book's thesis: a scheduling policy that maximizes long-term reward, learned online, beats a hand-coded rule that only reacts to local timing constraints. Human-level video gameplay. DQN is the chapter's demonstration that a deep multi-layer ANN can automate the feature design process. Most successful applications of reinforcement learning owe much to sets of features carefully handcrafted based on human knowledge and intuition about the specific problem to be tackled. But Men et al.'s Deep Q network combined Q-learning with a deep convolutional ANN and learned to play 49 different Atari 2600 video games by interacting with a game emulator using the same raw input, network architecture, and parameter values, e.g., step size, discount rate, exploration parameters. For all the games, achieving levels of play at or beyond human level on a large fraction of these games. The chapter gives the engineering history its due. The Atari 2600 introduced or popularized many arcade video games such as Pong, Breakout, Space Invaders, and Asteroids, and the arcade learning environment, ALE, developed by Belmar, NADAF, Venice, and Bowling, 2012, made them a benchmark. The evaluation regime is worth noting for its scale. DQN learned on each game by interacting with the game emulator for 50 million frames, which corresponds to about 38 days of experience with the game, and it was reset to random values before learning on each game. The representation details carried much of the engineering weight. The frame was pre-processed and added to the 4-frame stack that became the next input to the network, and the reward signal was standardized across games. The game's reward signal indicated how a game's score changed from one time step to the next, +1 whenever it increased, -1 whenever it decreased, and 0 otherwise, which standardized the reward signal across the games and made a single step size parameter work well for all the games despite their varying ranges of scores. DQN used an epsilon greedy policy, with epsilon decreasing linearly over the first million frames and remaining at a low value, and the values of the various other parameters were selected by performing informal searches to see which values worked best for a small selection of the games, then held fixed for all of the games. DQN used the semi-gradient form of Q-learning, with backpropagation applied only to the network corresponding to AT, a mini-batch method that updated weights only after accumulating gradient information over a small batch of images. Here, after 32 images, for smoother sample gradients, and a gradient ascent algorithm called RMS-prop. that accelerates learning by adjusting the step size parameter for each weight based on a running average of the magnitudes of recent gradients. The three stabilizing modifications are the chapter's practical core. First, experience replay. From Lin, 1992, this method stores the agent's experience at each time step in a replay memory, and at each time step multiple Q-learning updates, a mini-batch, were performed based on experiences sampled uniformly at random from the replay memory, with a new unconnected experience drawn from the replay memory to supply data for the next update. Because Q-learning is an off-policy algorithm, it does not need to be applied along connected trajectories. Replay allowed DQN to learn more efficiently from its experiences, reduce the variance of the updates because successive updates were not correlated with one another, and by removing the dependence of successive experiences on the current weights, eliminated one source of instability. The second modification was a duplicate target network whose output over the next C updates of W were used as the Q-learning targets. And the third was clipping the error term to remain in the interval -1. The ablations are decisive. Each of these features alone significantly improve performance, and very dramatically improve performance when used together, and the deep convolutional version showed a particularly striking improvement over a single linear layer. The chapter is also honest about limits. DQN is not a complete solution to the problem of task-independent learning. The games all use video images, which made a deep convolutional in a natural choice. DQN's performance on some of the Atari 2600 games fell considerably short of human skill, and the games most difficult for DQN, especially Montezuma's Revenge, required deep planning beyond what DQN was designed to do. Still, DQN advanced the state-of-the-art in machine learning by impressively demonstrating the promise of combining reinforcement learning with modern methods of deep learning. Mastering the game of Go, AlphaGo, and AlphaGo Zero. The chapter's climactic case study is Go, the ancient Chinese game that challenged artificial intelligence researchers for many decades. The game's rules are simple, but they produce a very complex game that has had wide appeal for thousands of years. Two players alternately place black and white stones on unoccupied intersections, or points. Stones are captured if they're completely surrounded by the other player's stones, and the game ends when neither player wishes to place another stone. Methods that achieve human-level skill in other games have not been successful in producing strong Go programs. The difficulty is only partly search. The search space for Go is significantly larger than that of chess because Go has a larger number of legal moves per position than chess, 250 versus 35. And Go games tend to involve more moves than chess games, 150 versus 80. Yet the size of the search space is not the major factor that makes Go so difficult, since even 9x9 Go is exceedingly difficult. Rather, experts agree that the major stumbling block to creating stronger than amateur Go programs is the difficulty of defining an adequate position evaluation function. AlphaGo combined deep ANNs, supervised learning, Monte Carlo tree search, MCTS, and reinforcement learning, defeating the European Go champion Fan Hui 5-0. The first victories of a Go program over a professional human Go player without handicap, and then winning against the 18-time world champion Lee Sedol, winning 4 out of 5 games, results that made worldwide headline news because artificial intelligence researchers thought that it would be many more years, perhaps decades, before a program reached this level of play. AlphaGo's architecture is a stack of distinct policies and a value network, and the book supplies the concrete numbers. The identically structured SL and RL policy networks were similar to DQN's deep convolutional network, except that they had 13 convolutional layers with the final layer consisting of a softmax unit for each point on the 19x19 Go board, with inputs at the 19x19x48 image stack of binary or integer feature planes. For each point, one feature indicated if the point was occupied by one of AlphaGo's stones, thus providing the raw representation of the board configuration, supplemented by other features based on the rules of Go, such as the number of adjacent points that were empty, the number of opponent stones that would be captured by placing a stone there, the number of turns since a stone was placed there. Training the SL policy network took approximately 3 weeks using a distributed implementation of stochastic gradient ascent on 50 processors. The network achieved 57% accuracy, where the best accuracy achieved by other groups at the time of publication was 44.4%. The RL policy network was then trained by policy gradient reinforcement learning over simulated games between the RL policy network's current policy and opponents using policies randomly selected from policies produced by earlier iterations. Because randomizing from a pool of opponents in this way stabilizes training by preventing overfitting to the current policy. And it won more than 80% of games played against the SL policy. The value network was trained by Monte Carlo policy evaluation from data obtained from a large number of self-play games played using the RL policy to avoid overfitting and instability due to the strong correlations between positions encountered in self-play. The DeepMind team constructed a data set of 30 million positions, each chosen randomly from a unique self-play game. Then, training was done using 50 million mini-batches each of 32 positions drawn from this dataset, taking 1 week on 50 GPUs. And a fast rollout policy was learned prior to play by a simple linear network trained by supervised learning from a corpus of 8 million human moves, less complex than the deep networks and allowed approximately 1,000 complete game simulations per second. The evaluation ablations are subtle and worth preserving. AlphaGo played better against human opponents when APVMCTS used as the SL policy instead of the RL policy, because the RL policy was tuned to respond to optimal moves rather than to the broader set of moves characteristic of human play, while for the value function the situation was reversed, and the mixing parameter, lambda, in 16.4, showed the value network stronger than rollouts alone, with the best play result, ing, from setting lambda equals 0.5, because the value network evaluated the high-performance RL policy that was too slow to be used in live play, while rollouts were able to add precision for specific states that occurred during games. AlphaGo 0 is the philosophical summit of the chapter. It used no human data or guidance beyond the basic rules of the game, hence the 0 in its name, learned exclusively from self-play reinforcement learning, with input giving just raw descriptions of the placements of stones, and, crucially, used MCTS to select moves throughout self-play reinforcement learning, not merely for live play. It implemented a form of policy iteration, interleaving policy evaluation with policy improvement, using a single two-headed deep convolutional network, 41 layers followed by batch normalization with skip connections. One head fed 362 output units, producing move probabilities, one for each possible stone placement plus pass. The other head fed just one output unit producing the scalar V, whose inputs, a 19 by 17 image stack of binary feature planes, 8 for the current players. Stones in the current and 7 pass configurations, 8 for the opponents, and 1 constant plane for the color to play, had to include past board configurations in color because the current board position is not a Markov state of go. The training loop is the book's clearest picture of self-contained policy iteration. The network's weights theta were updated to move the policy vector p toward the probabilities pi returned by MCTS, and to include the winner z in the estimated win probability v. The network learns to imitate its own improved search and to predict its own outcomes on training examples that were randomly sampled steps from recent self-play games. Because AlphaGo 0's MCTS ran a simulation that ended at a leaf node of the current search tree instead of at the terminal position of a complete game simulation, it did not include rollouts of complete games, and therefore did not need a rollout policy. One more simplification towards self-contained learner. The trajectory from Samuel's checkers to TD Gammon to DQN to AlphaGo 0 is drawn as a lineage. All these programs included reinforcement learning over simulated games of self-play, and AlphaGo 0 is both higher performing and more of a pure reinforcement learning program. Personalized web services and thermal soaring. The remaining case studies carry the method into commerce and biology. In personalized web services, Theocaris et al. At Adobe formulated personalized recommendation as a Markov decision problem, MDP, optimizing a lifetime value, LTV, a long-horizon objective over short-term greedy policies that had dominated the recommendation policy practice. LTV optimization used a batch-mode reinforcement learning algorithm to learn a policy that can recommend content considered to be the best for each user over the long run. And after these probabilistic guarantees, Adobe announced in 2016 that the new LTV algorithm would be a standard component of the Adobe Marketing Cloud. The lesson is the book's core, one applied commercially. Recommendations should maximize long-term return, not immediate click-through. In thermal soaring, Reddy, Seleny, Sinowski, and Vergasela, 2016, use reinforcement learning to investigate thermal soaring policies that are effective in the strong atmospheric turbulence usually accompanying rising air currents, with the primary goal to provide insight into the cues birds sense and how they use them to achieve their impressive thermal soaring performance, while the results also contribute to technology relevant to autonomous gliders. The model was a continuing MDP. The agent interacted with a detailed model of a glider flying in turbulent air, with airflow modeled by a sophisticated physics-based set of partial differential equations involving air velocity, temperature and pressure, and glider flight, modeled by aerodynamic equations involving velocity, lift, drag, and other factors. The agent's actions were its angle of attack and bank angle. By experimenting with various possibilities, 3 actions each for the angle of attack and the bank angle were enough, so increment or decrement the current bank angle and angle of attack, or leave them unchanged, resulting in 9 possible actions. Because a goal of their study was to try to determine what minimal set of sensory cues are necessary for effective soaring, the authors tried various sets of signals as input to the reinforcement learning agent, starting from state aggregation of a 4-dimensional state space with dimensions giving local vertical wind speed, local vertical wind acceleration, torque depending on the difference between the vertical wind velocities at the left and right wing tips, and the local temperature. Each dimension was discretized into 3 bins. The minimal sensory cues agenda is a genuinely biological application of the state representation lesson that runs through the whole book and the Q Learning Update note. The update is made online and does not require any prior model of the flow or the flight. Links directly to the adaptive autonomy themes of the psychology and neuroscience chapters. Quote, several of these are substantial applications of potential economic significance. Our presentations are intended to illustrate some of the trade-offs and issues that arise in real applications. For example, we emphasize how domain knowledge is incorporated into the formulation and solution of the problem. We also highlight the representation issues that are so often critical to successful applications. Chapter 16 opening. Quote, applications of reinforcement learning are still far from routine and typically require as much art as science. Making applications easier and more straightforward is one of the goals of current research in reinforcement learning. Chapter 16 opening. Quote, T.D. Gammon had a significant impact on the way the best human players play the game. The impact on human play was greatly accelerated when several other self-teaching A&N backgammon programs inspired by T.D. Gammon became widely available. Section 16.1. Chapter 17. Frontiers. General value functions and auxiliary tasks. The final chapter, touch, is on some topics that are beyond the scope of this book, but that we see as particularly important for the future of reinforcement learning. Many of these topics bring us beyond what is reliably known, and some bring us beyond the MDP framework. The first frontier is the generalization the whole book's notation has been preparing. A value function need not predict reward. The next, and perhaps final, step is to generalize beyond rewards to permit predictions about arbitrary signals, with the sum quantity called the cumulant, a general value function, or GVF. V sub pi comma gamma comma c of s equals e the sum over k equals t o the product over I equals t plus 1 k gamma of s sub I is c sub k, plus 1 given S sub t equals S. Because a GVF has no necessary connection to reward, it is perhaps a misnomer to call it a value function. Whatever it is called, it is in the form of a value function and thus can be learned in the usual ways. These predictions are auxiliary tasks, extra, in addition to the main task of maximizing reward, and they help in 3 ways. They can require some of the same representations as are needed on the main task. So if good features can be found early on easy auxiliary tasks, then those features may significantly speed learning on the main task. If you learn to predict and control your sensors over short time scales, you might plausibly come up with part of the idea of physical objects. They can enable built-in reflexes keyed to learn predictions. By design, without learning, a self-driving car that learns to predict whether going forward will produce a collision could be given a built-in reflex to stop, or a vacuum cleaning robot that learned to predict whether it might run out of battery power before returning to the charger and that reflexively headed back. And, most importantly, they set up the book's closing move beyond the assumption that the state representation is fixed and given to the agent, the subject of section 17.3. Temporal abstraction via options. The MDP formalism can be applied usefully to tasks at many different time scales, which muscles to twitch to grasp an object, which airplane flight to take, which job to take to lead a satisfying life. The question is whether the framework can be stretched to cover all the levels simultaneously. The answer is the option, a generalized notion of action defined as a pair, a policy pi, and a state-dependent termination function, so that low-level actions are special cases of options, and the agent can either select a low-level action/option, terminating after one time step, or select an extended option that might execute for many time steps before terminating. Options are designed so that they are interchangeable with low-level actions. The action value function naturally generalizes to an option value function, and the notion of policy generalizes to a hierarchical policy that selects from options rather than actions. With these ideas, many of the algorithms in this book can be generalized to learn approximate option value functions and hierarchical policies. Observations and state. This is the most important role for auxiliary tasks, moving beyond the assumption that the state representation is fixed and given. The argument is staged in 4 steps. First, state update functions. A Markov state can be incrementally updatable. It is only necessary to make accurate one-step predictions, because accurate one-step predictions are informationally sufficient, together with the state update function, to accurately predict the probability of any test of any length. The chapter's caveat is sharp. Determining long-term predictions from single-step predictions is exponentially complex in the length of the predictions. And if there is any error or approximation in the one-step predictions, then it can compound to make the long-term predictions wildly inaccurate. Second, the PUMDP approach. The environment is assumed to have a well-defined latent state xt, but is never available to the agent, and the natural Markov state is the distribution over the latent states given the history, called the belief state, updated by Bayes' rule. This approach is popular in theoretical work and has many significant applications, but its assumptions and computational complexity scale poorly, and we do not recommend it as an approach to artificial intelligence. Third, predictive state representations, PSRs. The semantics of the agent state is instead grounded in predictions about future observations and actions, which are readily observable, a d-vector of the probabilities of d specially chosen core tests, arguably MAC, easier to learn. Fourth, approximation itself. We must accept and work with an approximate notion of state, the kth order history, being the simplest instance. The binding heuristic is stated with refreshing humility. The guarantee provided by the perfect but impractical Markov property is replaced by the heuristic that what's good for some predictions may be good for others. Designing reward signals. The reward signal, a critical part of any application of reinforcement learning, is itself a design object, and a hard one. The parts of our brains that generate these signals evolved over millions of years, so we should therefore not think that designing a good reward signal is always an easy thing to do. The chapter names two classic pathologies. Sparse reward. The agent may wander aimlessly for long periods of time. What Minsky, 1961, called the plateau problem. And specification gaming. Reinforcement learning agents can discover unexpected ways to make their environments deliver reward, some of which might be undesirable or even dangerous. The Sorcerer's Apprentice, Wiener's Monkey's Paw. It grants what you ask for, not what you should have asked for, and Bostrom's Modern Warnings. Two principled remedies are presented. Inverse reinforcement learning infers a reward function from an expert's behavior, and bi-level optimization of the reward signal itself treats the reward as a parameter of the learning algorithm, with one level analogous to evolution and the other due to reinforcement learning by individual agents. The chapter's conclusion from these experiments is subtle and anti-folk. An agent's goal should not always be the same as the goal of the agent's designer. When there are constraints like these, learning to achieve a goal that is different from the designer's goal can sometimes end up getting closer to the designer's goal than if that goal were pursued directly. Evolution gave us a reward signal that makes us seek certain tastes, precisely because we cannot directly assess the nutritional value of most foods. Remaining issues. The penultimate section is a candid research agenda. 6 further issues still need to be addressed by future research. First, powerful parametric function approximation methods that work well in fully incremental and online settings. Current deep learning methods are not well suited to online learning, suffering from catastrophic interference and correlated data, so that when something new is learned, it tends to replace what has previously been learned. Second, methods for learning features such that subsequent learning generalizes well. The old problem, variously called representation learning, constructive induction, and meta-learning, whose intractability should give one pause. Perhaps there is no solution, though reinforcement learning brings some new possibilities to this old issue, such as the auxiliary tasks. Third, scalable methods for planning with learned environment models. Cases of full model-based reinforcement learning are rare, and the learning of the model needs to be selective because the scope of a model strongly affects planning efficiency. Fourth, automating the choice of tasks on which an agent works. Fifth, in the full text, the engineering of general competence rather than per-task solutions. Sixth, designing reward signals already treated. The common thread is that the book's own foundations, online, incremental, model-free plus model-based, are not yet matched by the tools the field currently uses. Reinforcement learning and the future of artificial intelligence. The final section returns to Simon's call for us to recognize that we are designers of our own, and of agents toward a world worth inhabiting. The chapter opens on the field's own recent history. When we were writing the first edition of this book in the mid-1990s, artificial intelligence was making significant progress and was having an impact on society, though it was mostly still the promise of artificial intelligence that was inspiring developments. By today, that promise has transitioned to applications that are changing the lives of millions of people, and some of the most remarkable developments in artificial intelligence have involved reinforcement learning, most notably deep reinforcement learning. Reinforcement learning with function approximation by deep artificial neural networks. We are at the beginning of a wave of real-world applications. The note of sobriety follows immediately. An abundance of successful real-world applications does not mean that true artificial intelligence has arrived. The gulf between artificial intelligence and the intelligence of humans and other animals remains great. Superhuman performance can be achieved in some domains, even formidable domains like Go, but it remains a significant challenge to develop systems that are like us in being complete, interactive agents having general adaptability and problem-solving skills, emotional sophistication, creativity, and the ability to learn quickly from experience. Reinforcement learning, as it develops over the future, will be a critical component of agents with these abilities. The chapter then enumerates 3 futures. The scientific one, reinforcement learning's connections to psychology and neuroscience, underscore its relevance to another long-standing goal of artificial intelligence. Shedding light on fundamental questions about the mind and how it emerges from the brain, and through its links to computational psychiatry, Reinforcement learning theory will contribute to methods for treating mental disorders, including drug abuse and addiction. The decision support future. Policies derived by reinforcement learning in simulated environments can advise human decision makers in such areas as education, healthcare, transportation, energy, and public sector resource allocation. And the property that makes this fit is exactly the book's core commitment. Particularly relevant is the key feature of reinforcement learning that it takes long-term consequences of decisions into account. This is very clear in games like backgammon and Go, but it is also a property of many high-stakes decisions that affect our lives and our planet. And the embedded agent future. Embedding reinforcement learning agents in the real world can be transformative in realizing the promises of artificial intelligence to amplify and extend human abilities. But it is here that the warnings need to be heeded, because reinforcement learning is based on optimization, and it inherits the pluses and minuses of all optimization methods, including the problem of devising objective functions or reward signals, so that optimization produces the desired results while avoiding undesirable results. The chapter is equally firm about safe learning during learning. Another challenge if reinforcement learning agents are to act and learn in the real world is not just about what they might learn eventually, but about how they will behave while they are learning. How do you make sure that an agent gets enough experience to learn a high-performing policy, all the while not harming its environment, other agents, or itself? The answer borrows from a mature discipline. Risk management and mitigation for embedded reinforcement learning is similar to what control engineers have had to confront from the beginning of using automatic control, which relies on careful system modeling, model validation, and extensive testing. And one of the most pressing areas for future reinforcement learning research is to adapt and extend methods developed in control engineering with the goal of making it acceptably safe to fully embed reinforcement learning agents into physical environments. The closing note is neither triumphal nor alarmed. Optimization has been used for hundreds of years by engineers, architects, and others whose designs have positively impacted the world. There are many approaches, such as adding hard and soft constraints, restricting optimization to robust and risk-sensitive policies, and optimizing with multiple objective functions. And the problem of ensuring that a reinforcement learning agent's goal is attuned to our own remains a challenge. It is the right note for a text that has spent 17 chapters teaching exactly how hard and how promising it is to make a machine that drives itself toward a goal. Quote, because a GVF has no necessary connection to reward, it is perhaps a misnomer to call it a value function. Whatever it is called, it is in the form of a value function, and thus can be learned in the usual ways using the methods developed in this book. Section 17.1. Quote, the agent may wander aimlessly for long periods of time, what Minsky, 1961, called the plateau problem. Section 17.4. Quote, the problem of ensuring that a reinforcement learning agent's goal is attuned to our own remains a challenge. Section 17.6. Conclusion. Reinforcement learning, in Sutton and Barto's presentation, is less a collection of algorithms than a single idea held firmly in view. That an agent seeking to maximize a scalar reward over time can discover good behavior entirely from the evaluation of its own actions, provided it can solve the two ancient problems of credit and exploration. The book's great achievement is to have made that idea precise and teachable. From the K-armed bandits' exploration-exploitation dilemma to the MDP's formal account of delayed reward, from dynamic programming's exact value functions to the semi-gradient approximations that make large state spaces tractable, each method is presented as a variation on one architecture, generalized policy iteration, in which a value function and a policy chase one another toward consistency. The reward hypothesis, stated once early and carried everywhere, is that all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal. The whole three-part structure of the book, tabular learning, function approximation, and the deeper connections to psychology, neuroscience, and applications, is the working out of what that sentence commits us to. The argument's arc is remarkably uniform. which is itself the book's central methodological claim. Chapter after chapter, the same sequence recurs: state the problem, present the simplest method that addresses it, identify its bias and variance, then generalize along the dimensions the authors have trained the reader to see. The depth of bootstrapping, N and lambda, the source of experience, real or simulated, on policy or off policy, and the representation, table, features, or network. Temporal difference learning is elevated to the field's central and novel idea precisely because it occupies the middle of the MC/DP spectrum. In-step methods then reveal that the whole spectrum is one line. Eligibility traces make the line computationally cheap, and function approximation shows that the line survives the move from tables to parameters, though only at the price of the deadly triad and its instability. The Monty Python-like patience with which the book develops each of these moves, always first the prediction problem, then control, is not pedantry but evidence. The ideas genuinely build. What the book is not, it says so plainly. It is not a survey of the exploding field, not a rigorous theorem proof treatment, not an account of how to make applications routine, as much art is science. Its own limits are declared at the hardest points. The formal open question of Monte Carlo ES convergence, the concession that off-policy learning will not be as strong, nor the empirical results as satisfying as on-policy. The admission that current deep learning methods are not well suited to online learning. These declarations of uncertainty are part of the register. The book teaches not a body of settled results, but a way of thinking about learning from interaction, one in which the honest statement of what is not known is as much a demonstration of mastery as the proof of what is. The significance crosses the boundaries the book itself crosses. For computer science and engineering, it provided the vocabulary and the algorithms behind systems from TD Gammon to AlphaGo, a lineage the case study chapter draws explicitly. For psychology and neuroscience, it offered a computational hypothesis, the reward prediction error, that turned a century of conditioning experiments into predictions testable at the level of single dopamine neurons. And for the philosophy of learning, it supplied the cleanest formulation yet of the difference between being told and being evaluated, and of why an agent that seeks its own return can be trusted to learn what its designer only hoped to express. The stakes are practical as well as intellectual. The problem of ensuring that a reinforcement learning agent's goal is attuned to our own remains a challenge, and the book's closing gesture is to hand that challenge to the future. The deepest image the book leaves is the agent, always reactive and always deliberative, responding instantly to the latest sensory information and yet always planning in the background. The Dyna diagram in which learning, planning, acting, and model building run in parallel and share one final common path. That image reconciles the book's two poles: model-free speed and model-based foresight, habit and goal-directedness, the dopamine neuron and deadlines reward prediction error. Sutton and Bardo's second edition is the mature statement of a project that began with Klopp's conviction that maximizing systems, not equilibrium-seeking ones, hold the key to intelligence, and that learning, from the simplest bandit to the deepest network, is learning what to do. Key persons discussed: A. Harry Klopp, the book's dedicatee and the figure who instigated the research program for which it grew, an Air Force Office of Scientific Research scientist who argued that systems that try to maximize something are qualitatively different from equilibrium-seeking systems, brought Sutton and Bardo together, and contributed the generalized reinforcement and eligibility trace ideas that run through chapters 12 and 15. Richard S. Sutton, co-author and principal architect of temporal difference learning, Sutton, 1988, separated TD from control as a general prediction method. The book's voice is substantially his, problem-first, proof-disciplined, and candid about open questions. Andrew G. Bartow, co-author, Sutton's PhD advisor, and co-developer of the actor, critic architecture, classical conditioning TD models, and the early machine learning experiments showing reinforcement learning differs from supervised learning. Gerald Tissereau, creator of TD Gammon, recognized by the book as one of the most impressive applications of reinforcement learning to date. His program's success revived the field, and its methods form the case study chapter's core. Chris Watkins, developer of Q-Learning, 1989, one of the early breakthroughs in reinforcement learning, which integrated the trial and error, optimal control, and TD threads and enabled the first convergence proofs. Dmitry Bertsikas and John Tsitsiklis, theoreticians who connected dynamic programming to learning, neurodynamic programming. Their counterexample, with Van Roy, and convergence theory anchor the linear function approximation analysis. Arthur Samuel, creator of the first checkers program to include temporal difference ideas, 1959, the historical root of the TD-Gammon DQN AlphaGo lineage. Harry Klopp's intellectual heirs, briefly the psychology cast, Pavlov, Thorndike, Hull, Tolman, Rescorla, and Wagner, whose experiments and theories the psychology chapter reads through the TD lens, and the neuroscience cast, Schultz, Dian, Montague, Sanowski, Reddish, Daw, Neve, whose experiments ground the dopamine story. David Silver and DeepMind, developers of DQN, AlphaGo, and AlphaGo Zero. Closing the case study chapters are from Samuel's checkers to a program learning go from no human data or guidance beyond the basic rules. Key works discussed. Reinforcement Learning, An Introduction, Sutton and Bartow, 1998. Second edition, 2018. The book itself. The canonical textbook the summary reconstructs. Bellman, 1957a. 1957b introduced dynamic programming and the discrete stochastic version of the optimal control problem, now called Markov decision processes. The Bellman equation and its optimality form are the theoretical backbone of chapters 3 to 4. Howard, 1960 devised policy iteration for MDPs. Gale and Shapley, 1962, the stable matching problem that opens the book's treatment, referenced in the Kleinberg exemplar tradition. Not this book, and the algorithm family standing behind the Bandit chapter's framing of evaluative feedback. Watkins, 1989, Q-Learning, one of the early breakthroughs in reinforcement learning. Sutton, 1988, learning to predict by the methods of temporal differences, separated TD from control, introduced TD, zero, and TD, lambda, and proved convergence results used throughout Part 1. Tesoro, 1992, 1994, 1995, TD-Gammon. Witten, 1977, identified by the book as the earliest publication of a temporal difference learning rule. Rummery and Narunjan, 1994, introduced the Sursa algorithm as modified connectionist Q-Learning. Van Siegen et al., 2016, True Online TD, Lambda, the exact backward implementation of the online lambda return. Montague, Dian, and Sanowski, 1996, and Schultz, Dian, and Montague, 1997, the reward prediction error hypothesis linking TD errors to dopamine. Reddish, 2004, the model of aspects of addiction built on the reward prediction error hypothesis. Adams and Dickinson, 1981, and Adams, 1982, the outcome evaluation experiments distinguishing habitual from goal-directed behavior. Daw, Neve, and Dian, 2005, the arbitration account of model-free versus model-based control. Min et al., 2013, 2015, DQN, human-level Atari play through deep Q-learning. Silver et al., 2016, 2017, AlphaGo and AlphaGo Zero. Index of key concepts. Reward hypothesis. All of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal, called reward. The whole framework hangs on this single commitment. It converts goals into a signal an agent can optimize, and it rules out imparting to the agent prior knowledge about how to achieve a goal through the reward itself that belongs in initial policy or value functions. Evaluative versus instructive feedback. Evaluative feedback indicates how good the action taken was, but not whether it was the best or the worst, whereas instructive feedback indicates the correct action to take, independently of the action actually taken. This is the founding distinction that separates reinforcement learning, evaluative, from supervised learning, instructive, and generates the need for exploration. Exploration, exploitation dilemma. the demand to exploit what it has already experienced in order to obtain reward, but also to explore in order to make better action selections in the future, with neither pursued exclusively without failing at the task. It is unresolved in general, and the book is candid that its simple methods worry only about balancing them at all. Markov decision process. MDP, the formalization of the reinforcement learning problem as states, actions, rewards, and the joint transition dynamics P. S. RSA. Its defining assumption. The Markov property is a restriction not on the decision process, but on the state, which must include information about all aspects of the past agent, environment interaction that make a difference for the future. Value function. The expected return from a state or state-action pair under a policy. Rewards are in a sense primary, whereas values, as predictions of rewards, are secondary. And the central role of value estimation is arguably the most important thing that has been learned about reinforcement learning over the last 6 decades. Bellman equation/Bellman optimality equation. Consistency conditions relating the value of a state to the values of its successors, and, in the optimal form, to the best action from a state. The beauty of E** operator is that if one uses it to evaluate the short-term consequences, then a greedy policy is actually optimal in the long-term sense, because the optimal value function has already folded in all future consequences. Generalized policy iteration, GPI. The general idea of letting policy evaluation and policy improvement processes interact, independent of the granularity and other details of the two processes. Nearly every control method in the book is a GPI instantiation. The processes compete. Each makes the other's current state invalid, yet interact to find a single joint solution. Temporal difference, TD, learning from the difference between temporally successive estimates of the same quantity, combining the sampling of Monte Carlo with the bootstrapping of DP. The TD error delta T is central and novel to reinforcement learning. It drives prediction, conditioning models, and the dopamine reward prediction error alike. Bootstrapping, updating estimates based in part on other learned estimates, without waiting for a final outcome. It enables online, incremental learning and a state property, but its use in targets makes the deadly triad dangerous. The depth of bootstrapping in lambda tunes the bias, variance trade-off. Monte Carlo methods. Averaging complete sample returns to estimate values. They do not bootstrap, hence are less harmed by violations of the Markov property, but require episode ends and wait until the return following the visit is known. Importance sampling. Weighting returns by the relative probability of the trajectory under target and behavior policies, thereby transforming their expectations from the behavior policy to the target policy. Ordinary sampling is unbiased with possibly infinite variance. Weighted sampling has bounded variance and is strongly preferred in practice. In-step bootstrapping. Methods whose targets are truncated after n steps and then corrected for the remaining missing terms by a value estimate, freeing you from the tyranny of the time step. The full spectrum from one-step TD, n equals 1, to Monte Carlo, n equals infinity. Eligibility traces a short-term memory vector that accumulates gradients of past states and fades by gamma lambda, letting a single current TD error credit all the action values up to the beginning of the episode to different degrees, fading with recency. They are the first line of defense against both long-delayed rewards and non-Markov tasks. The deadly triad. The danger of instability and divergence arises whenever function approximation, bootstrapping, and off-policy training are combined. If any two elements are present but not all three, then instability can be avoided, though none of the three can be simply given up. Semi-gradient methods. Updates that take the gradient of the value estimate but ignore the appearance of the weights in the target, since the weight vector appears in the update target. Yet this is not taken into account in computing the gradient. They lack classical SGD guarantees, but converge well for linear approximation to the TD fixed point and are extremely efficient. On-policy versus off-policy learning. On-policy methods evaluate or improve the policy that is used to make decisions. Off-policy methods evaluate or improve a policy different from that used to generate the data, separating the target from the behavior policy. Essential for parallel learning of many predictions and a source of the deadly triad's distribution mismatch. Average reward setting and differential value functions. In continuing problems with function approximation, the discounted formulation cannot be carried over, so the agent maximizes the average reward rate, or pi, and learns differential value functions with rewards replaced by the difference between the reward and the true average reward. The discount rate changes from a problem parameter to a solution method parameter. Policy gradient methods. Learning a parameterized policy directly by stochastic gradient ascent on a performance measure. So the policy may be a simpler function to approximate than the value function. Specific action probabilities can be learned, and continuous action spaces become natural. The policy gradient theorem removes the need to differentiate the state distribution. The reward prediction error hypothesis. The claim that dopamine appears to convey temporal difference, TD, errors to brain structures where learning and decision-making take place, so that dopamine phasic activity encodes delta, positive at unpredicted reward, transferred to the earliest predictor, negative at omitted reward. It resulted from the convergence of computational reinforcement learning and results of neuroscience experiments. Model-free versus model-based learning. Model-free methods are explicitly trial-and-error learners, storing values or policies. Model-based methods learn an environment model and plan by simulation. The distinction aligns with habitual versus goal-directed behavior and with the DLS versus DMS of the striatum, and the Dyna architecture integrates them, so the agent is always reactive and always deliberative. Options and temporal abstraction. Generalized actions consisting of a policy and a state-dependent termination function, letting the MDP framework be stretched to cover all the levels simultaneously. Low-level actions are a special case, and value functions and policies generalized to option values and hierarchical policies. General value functions, GVFs, and auxiliary tasks. Predictions of the future sum of any signal, cumulant, not just reward, learned in the usual ways using the methods developed in this book. Their auxiliary tasks can furnish shared representations, support built-in reflexes keyed to predictions, and move the agent beyond a fixed given state representation. Reading comprehension questions. Scaffold/recall. What are the 4 main sub-elements of a reinforcement learning system, and which one is optional? Give the book's definition of each. Scaffold/recall. State the reward hypothesis exactly, and explain why the reward signal is your way of communicating to the agent what you want achieved, not how you want it achieved. Scaffold/recall. What is the distinction between the reward signal and the value function? And why does action selection depend on values rather than rewards? Mechanism. Trace how the TD error changes over the course of learning in the idealized policy evaluation task of Chapter 15, and explain why each stage, early learning, learning complete, reward omitted, matches a phasic dopamine response. Mechanism. Why do off-policy semi-gradient TD methods diverge on Baird's counterexample while on-policy methods converge? Use the eventually the piper must be paid argument. Mechanism. Explain how true online TD, lambda, achieve exactly the same sequence of weight vectors as the online lambda return algorithm while retaining OD per step complexity. Why does this matter? Mechanism. What is the deadly triad? Why is each element hard to give up? And how do gradient TD and emphatic TD methods each sidestep the instability rather than removing a triad element? Relationship. In what sense does the extension to function approximation also make it applicable to partially observable problems? What can function approximation not do? Relationship. Compare the prediction/control distinction in reinforcement learning with the classical/instrumental conditioning distinction in psychology. Where does the analogy break down per the book? Relationship. Why did T.D. Gammon learn by self-play, while Watson's wagering value function was learned by playing against models of human players? What does the difference teach about when self-play works? Critical thinking, value assumption. The book asserts that in the batch, unchanging case TD0, converges to the certainty equivalence estimate, which is a better estimate of V-pi than the MC fit to observe data. What must be true about the world and about the learner's objective for better at predicting returns to be the right criterion rather than better at fitting the data? Critical thinking, wishful thinking. The authors call the reward hypothesis a statement that all of what we mean by goals and purposes can be well thought of as the maximization of the expected value of the cumulative sum of a received scalar signal. Is this a definition, a claim about how goals actually arise, or a research program? Or might the book itself supply counterexamples to its universal scope? Critical thinking, omitted information. The DQN chapter concedes the games are all played by observing video images, which made a deep convolutional NN a natural choice. What would it take for the claim that deep learning can reduce and possibly eliminate the need for problem-specific design to survive tasks that do not arrive as images? Critical thinking, rival causes. The Adams and Dickinson outcome evaluation result is read as evidence for a cognitive map and model-based planning, with the book noting not every psychologist agrees with this cognitive account. What rival explanation would you seek, and what experiment could distinguish them? Critical thinking, gray conclusions. The authors conclude eligibility traces should be used to bring us toward Monte Carlo methods, but not all the way there, and that they pay off when data are scarce. Under what conditions, task structure, reward delay, representation quality, would traces be worse than one-step methods, and how does the book's own Tetris caveat bear on the answer?